What does this mean? In a run-of-the-mill synapse, a little bit of neurotransmitter comes out of the first neuron and causes the second neuron to get a little excited. If a smidgen more neurotransmitter is released, there is a smidgen more excitation, and so on. In glutamatergic synapses, some glutamate is released, and nothing happens. A larger amount is released. Nothing happens. It isn't until a certain threshold of glutamate concentration is passed that suddenly all hell breaks loose in the second neuron, and there is a massive wave of excitation. This is what learning something is about. A professor drones on incomprehensibly in a lecture. A fact goes in one ear and out the other. It is repeated again, and again. It fails to sink in. Finally, the 100th time it is repeated, a light bulb goes on. Aha! And you get it. On a simplistic level, when you finally get it, that nonlinear threshold of glutamate excitation has just been reached. The second feature is even more important. Under the right conditions, when a synapse has just had a sufficient number of superexcitatory glutamate-driven ahas, something happens. The synapse becomes persistently more excitable, so that next time it takes less of an excitatory signal to get the aha. That synapse just learned something. It was potentiated, or strengthened. The most amazing thing is that this strengthening of the synapse can persist for a long time. A huge number of neuroscientists flail away at figuring out how this process of long-term potentiation works. There's increasing evidence that the formation of new memories might also sometimes arise from the formation of new connections between neurons, in addition to the potentiating of pre-existing ones. Or, even more radically, the formation of new neurons themselves. This latter controversial idea is discussed shortly. For the moment, this is all you need to know about how your brain remembers anniversaries and sports statistics and the color of someone's eyes and how to waltz. We can now see what stress does to the process. Improving your memory during stress. The first point, of course, is that mild to moderate short-term stressors enhance memory. This makes sense, in that this is the sort of optimal stress that we would call stimulation, alert and focused. This effect has been shown in laboratory animals and in humans. One particularly elegant study in this realm was carried out by Larry Cahill and James McGaugh at the University of California at Irvine. Read a fairly unexciting story to a group of control subjects. A boy and his mother walk through their town, pass this store and that one, cross the street and enter the hospital where the boy's father works, are shown the X-ray room, and so on. Meanwhile, the experimental subjects are read a story that differs in that the central core of it contains some emotionally laden material. A boy and his mother walk through their town, pass this store and that one, cross the street where the boy is hit by a car. He's rushed to the hospital and taken to the X-ray room. Tested weeks later, the experimental subjects remember their story better than do the controls, but only the middle, exciting part. This fits with the picture of flashbulb memory, in which people vividly remember some highly aroused scene, such as a crime they witnessed. Memory for the emotional components is enhanced, although the accuracy isn't necessarily all that good, whereas memory for the neutral details is not. This study also indicated how this effect on memory works. Here the stressful story and a stress response is initiated. As we by now well know, this includes the sympathetic nervous system kicking into gear, pouring epinephrine and norepinephrine into the bloodstream. Sympathetic stimulation appears to be critical, because when Cahill and McGaugh gave subjects a drug to block that sympathetic activation, the beta blocker propranolol, the same drug used to lower blood pressure, the experimental group did not remember the middle portion of their story any better than the controls remembered theirs. Importantly, it's not simply the case that propranolol disrupts memory formation. Instead, It disrupts stress-enhanced memory formation. In other words, the experimental subjects did as well as the controls on the boring parts of the story, but simply didn't have the boost in memory for the emotional middle section. The sympathetic nervous system pulls this off by indirectly arousing the hippocampus into a more alert, activated state, facilitating memory consolidation. This involves an area of the brain that is going to become central to understanding anxiety when we get to Chapter 15, namely the amygdala. The sympathetic nervous system has a second route for enhancing cognition. Tons of energy are needed for all that explosive, non-linear, long-term potentiating, that turning on of light bulbs in your hippocampus with glutamate. The sympathetic nervous system helps those energy needs to be met by mobilizing glucose into the bloodstream and increasing the force with which blood is being pumped up into the brain. These changes are quite adaptive. When a stressor is occurring, it is a good time to be at your best in memory retrieval. How did I get out of this mess last time? And memory formation. If I survive this, I'd better remember just what I did wrong so I don't get into a mess like this again. So stress acutely causes increased delivery of glucose to the brain, making more energy available to neurons, and therefore better memory formation and retrieval. Thus, the sympathetic arousal during stress indirectly fuels the expensive process of remembering the faces of the crowd chanting ecstatically about classic Coke. In addition, a mild elevation in glucocorticoid levels, the type you would see during a moderate short-term stressor, helps memory as well. This occurs in the hippocampus, where those moderately elevated glucocorticoid levels facilitate long-term potentiation. Finally, there are some obscure mechanisms by which moderate short-term stress makes your sensory receptors more sensitive. Your taste buds, your olfactory receptors, the cochlear cells in your ears, all require less stimulation to get excited under moderate stress and pass on the information to your brain. In that special circumstance, you can pick up the sound of a can of soda being opened hundreds of yards away. Anxiety. Some foreshadowing. What we've just seen is how moderate and transient stress can enhance the sort of explicit memories that are the purview of the hippocampus. It turns out that stress can enhance another type of memory. This is one relevant to emotional memories, a world apart from the hippocampus and its dull concern with factoids. This alternative type of memory, and its facilitation by stress, revolves around that brain area mentioned before, the amygdala. The response of the amygdala during stress is going to be critical to understanding anxiety and post-traumatic stress disorder in Chapter 15. And when stress goes on for too long. With our sprinting across the savannah versus worrying about a mortgage dichotomy, loaded and ready, we can now look at how the formation and retrieval of memories goes awry when stressors become too big or too prolonged. People in the learning and memory business refer to this as an inverse U relationship. As you go from no stress to a moderate transient amount of stress, the realm of stimulation, memory improves. As you then transition into severe stress, memory declines. The decline has been shown in numerous studies with lab rats and with an array of stressors: restraint, shock, exposure to the odor of a cat. The same has been shown when high levels of glucocorticoids are administered to rats instead. But this may not tell us anything interesting. Lots of stress or of glucocorticoids may just be making for a generically messed up brain. Maybe the rats would now be lousy at tests of muscle coordination, or responsiveness to sensory information, or what have you. But careful control studies have shown that other aspects of brain function, such as implicit memory, are fine. Maybe it's not so much that learning and memory are impaired, as much as the rat being so busy paying attention to that cat smell, or so agitated by it, that it doesn't make much headway solving whatever puzzle is in front of it. And within that realm of explicit memory problems, the retrieval of prior memories seems more vulnerable to stress than the formation of new ones. Similar findings have been reported with non-human primates. What about humans? Much the same. In a disorder called Cushing's syndrome, people develop one of a number of types of tumors that result in a secretion of tons of glucocorticoids. Understand what goes wrong next in a Cushingoid patient, and you understand half of this book. High blood pressure, diabetes, immune suppression, reproductive problems, the works. And it's been known for decades that they get memory problems, specifically explicit memory problems, known as Cushingoid dementia. As we saw in Chapter 8, synthetic glucocorticoids are often administered to people to control autoimmune or inflammatory disorders. With prolonged treatment, you see explicit memory problems as well. But maybe this is due to the disease rather than to the glucocorticoids that were given for the disease. Pamela Keenan of Wayne State University has studied individuals with these inflammatory diseases, comparing those treated with steroidal anti-inflammatory compounds, that is, glucocorticoids, and those getting non-steroidals. Memory problems were a function of getting the glucocorticoids, not of the disease. As the clearest evidence, just a few days of high doses of synthetic glucocorticoids impairs explicit memory in healthy volunteers. As one problem in interpreting these studies, these synthetic hormones work a bit differently from the real stuff, and the levels administered produce higher circulating glucocorticoid levels than the body normally produces, even during stress. Importantly, stress itself, or infusion of stress levels of the type of glucocorticoid that naturally occurs in humans, disrupts memory as well. As with the non-human studies, implicit memory is fine, and it's the recall, the retrieval of prior information, that is more vulnerable than the consolidation of new memories. There are also findings, although fewer in number, showing that stress disrupts something called executive function. This is a little different from memory. Rather than this being the cognitive realm of storing and retrieving facts, this concerns what you do with the facts, whether you organize them strategically, how they guide your judgments and decision-making. This is the province of a part of the brain called the prefrontal cortex. We'll be returning to this in considerable detail in Chapter 16, when we consider what stress may have to do with decision-making and impulse control. The damaging effects of stress in the hippocampus. How does prolonged stress disrupt hippocampal-dependent memory? A hierarchy of effects have been shown in laboratory animals. First, hippocampal neurons no longer work as well. Stress can disrupt long-term potentiation in the hippocampus, even in the absence of glucocorticoids, as in a rat whose adrenal glands have been removed, and extreme arousal of the sympathetic nervous system seems responsible for this. Nonetheless, most of the research in this area has focused on the glucocorticoids. Once glucocorticoid levels go from the range seen for mild or moderate stressors to the range typical of big-time stress, the hormone no longer enhances long-term potentiation, that process by which the connection between two neurons remembers by becoming more excitable. Instead, glucocorticoids now disrupt the process. Furthermore, similarly high glucocorticoid levels enhance something called long-term depression, which might be a mechanism underlying the process of forgetting, the flip side of hippocampal ahaing. How can it be that increasing glucocorticoid levels a little bit during moderate stressors does one thing, enhances the potentiation of communication between neurons, while increasing glucocorticoid levels a lot does the opposite? In the mid-1980s, Ron de Kloot of the University of Utrecht in the Netherlands discovered the very elegant answer. It turns out that the hippocampus has large amounts of two different types of receptors for glucocorticoids. Critically, the hormone is about 10 times better at binding to one of the receptors, thus termed a high-affinity receptor, than the other. What that means is that if glucocorticoid levels only rise a little bit, most of the hormone effect in the hippocampus will be mediated by that high-affinity receptor. In contrast, it is not until you are dealing with a major stressor that the hormone activates a lot of the low-affinity receptor. And, logically, it turns out that activation of the high-affinity receptor enhances long-term potentiation, while activation of the low-affinity one does the opposite. This is the basis of the inverse U property just mentioned. In the previous section, I noted that the brain region called the amygdala plays a central role in the types of emotional memories involved in anxiety. But the amygdala is relevant here as well. The amygdala gets highly activated during major stressors and sends a large, influential neuronal projection to the hippocampus. Activation of this pathway seems to be a prerequisite for stress to disrupt hippocampal function. Destroy a rat's amygdala, or sever its connection to the hippocampus, and stress no longer impairs the kind of memory that the hippocampus mediates, even amid the usual high glucocorticoid levels. This explains a finding that harks back to the subject of stress signatures, and also demonstrates that some activities can represent a challenge to physical allostasis without being psychologically aversive. For example, sex raises glucocorticoid levels in a male rat without activating the amygdala and without disrupting hippocampal function. Second, neural networks get disconnected. If you look back at Figure 14 on your PDF companion, the impressionism neuron, you'll see that there are symbols indicating how one neuron talks to another, projects to it. As mentioned a few paragraphs after that, those projections are quite literal. Long, multi-branched cables coming out of neurons that form synapses with the multi-branched cables of other neurons. These cables, known as axons and dendrites, are obviously at the heart of neuronal communication and neuronal networks. Bruce McEwen has shown that in a rat, after as little as a few weeks of stress or of exposure to excessive glucocorticoids, those cables begin to shrivel, to atrophy and retract a bit. Moreover, the same can occur in the primate brain. When that happens, synaptic connections get pulled apart, and the complexity of your neural networks declines. Fortunately, it appears that at the end of the stressful period, the neurons can dust themselves off and regrow those connections. This transient atrophy of neuronal processes probably explains a characteristic feature of memory problems during chronic stress. Destroy vast acres of neurons in the hippocampus after a massive stroke or late terminal stage Alzheimer's disease, and memory is profoundly impaired. Memories can be completely lost, and never again will these people remember, for example, something as vital as the names of their spouses. Weaken a neural network during a period of chronic stress by retracting some of the complex branches in those neuronal trees, and the memories of Toulouse-Lautrec's name are still there. You simply have to tap into more and more associative cues to pull it out, because any given network is less effective at doing its job. Memories are not lost, just harder to access. Third, the birth of new neurons is inhibited. If you learned your introductory neurobiology any time in the last 1,000 years, one fact that would be hammered in repeatedly is that the adult brain doesn't make new neurons. In the last decade, it has become clear that this is utterly wrong. As a result, the study of adult neurogenesis is now arguably the hottest topic in neuroscience. Two features about such neurogenesis are highly relevant to this chapter. First, the hippocampus is one of only 2 sites in the brain where these new neurons originate. Second, the rate of neurogenesis can be regulated. Learning, an enriched environment, exercise, or exposure to estrogen all increase the rate of neurogenesis, while the strongest inhibitors identified to date are, you guessed it, stress and glucocorticoids, as little as a few hours of either in a rat. 2 key questions arise. First, when the stress stops, does neurogenesis recover? And if so, how fast? No one knows yet. Second, what does it matter that stress inhibits adult neurogenesis? Intrinsic in this question is the larger question of what adult neurogenesis is good for. This is incredibly controversial, an issue that has adversaries practically wrestling each other on the podium during scientific conferences. At one extreme are studies that suggest that under the right conditions, there are tons of neurogenesis in the adult hippocampus, that these new neurons form connections with other neurons, and that these new connections, in fact, are needed for certain types of learning. At the other extreme, every one of these findings is questioned. So the jury's out on this one. Fourth, hippocampal neurons become endangered. As noted, within seconds of the onset of stress, glucose delivery throughout the brain increases. What if the stressor continues? By about 30 minutes into a continuous stressor, glucose delivery is no longer enhanced and has returned to normal levels. If the stressor goes on even longer, the delivery of glucose to the brain is even inhibited, particularly in the hippocampus. Delivery is inhibited about 25%, and the effect is due to glucocorticoids. Decreasing glucose uptake to this extent in a healthy, happy neuron is no big deal. It just makes the neuron a little queasy and lightheaded. But what if the neuron isn't healthy and happy, and is instead in the middle of a neurological crisis? It's now more likely to die than usual. Glucocorticoids will compromise the ability of hippocampal neurons to survive an array of insults. Take a rat, give it a major epileptic seizure, and the higher the glucocorticoid levels at the time of the seizure, the more hippocampal neurons will die. Same thing for cardiac arrest, where oxygen and glucose delivery to the brain is cut off, or for a stroke, in which a single blood vessel in the brain shuts down. Same for concussive head trauma, or drugs that generate oxygen radicals. Disturbingly, same thing for the closest there is to a rat neuron's equivalent of being damaged by Alzheimer's disease, exposing the neuron to fragments of an Alzheimer's-related toxin called beta-amyloid. Same for a rat hippocampus's equivalent of having AIDS-related dementia, induced by exposing the neuron to a damaging constituent of the AIDS virus called GP120. My lab and others have shown that the relatively mild energy problem caused by the inhibition of glucose storage by glucocorticoids or stress makes it harder for a neuron to contain the 11 things that go wrong during one of these neurological insults. All of these neurological diseases are ultimately energy crises for a neuron. Cut off the glucose to a neuron, hypoglycemia, or cut off both the glucose and oxygen, hypoxia ischemia, or make a neuron work like mad, a seizure, and energy stores drop precipitously. Damaging tidal waves of neurotransmitters and ions flood into the wrong places. Oxygen radicals are generated. If you throw in glucocorticoids on top of that, the neuron is even less able to afford to clean up the mess. Thanks to that stroke or seizure, today's the worst day of that neuron's life, and it goes into the crisis with 25% less energy in the bank than usual. Finally, there is now evidence that truly prolonged exposure to stress or glucocorticoids can actually kill hippocampal neurons. The first hints of this came in the late 1960s. Two researchers showed that if guinea pigs are exposed to pharmacological levels of glucocorticoids, that is, higher levels than the body ever normally generates on its own, the brain is damaged. Oddly, damage was mainly limited to the hippocampus. This was right around the time that Bruce McEwen was first reporting that the hippocampus is loaded with receptors for glucocorticoids, and no one really appreciated yet how much the hippocampus was the center in the brain for glucocorticoid actions. Beginning in the early 1980s, various researchers, including myself, showed that this glucocorticoid neurotoxicity was not just a pharmacological effect, but was relevant to normal brain aging in the rat. Collectively, the studies showed that lots of glucocorticoid exposure, in the range seen during stress, or lots of stress itself, would accelerate the degeneration of the aging hippocampus. Conversely, diminishing glucocorticoid levels by removing the adrenals of the rat would delay hippocampal aging. And as one might expect by now, the extent of glucocorticoid exposure over the rat's lifetime not only determined how much hippocampal degeneration there would be in old age, but how much memory loss as well. Where do glucocorticoids and stress get off killing your brain cells? Sure, stress hormones can make you sick in lots of ways, but isn't neurotoxicity going a bit beyond the bounds of good taste? A dozen years into studying the phenomenon, we're not yet sure. What about damage to the human hippocampus? We know from earlier in this chapter that an excess of stress and/or glucocorticoids can disrupt functioning of the hippocampus. Is there any evidence that this can include the sort of overt damage to the hippocampus that we've been discussing? That is, can it disconnect neural networks by the atrophying of processes, inhibit the birth of new neurons, worsen the neuron death caused by other neurological insults, or overtly kill neurons? To date, 6 sets of findings in humans should raise some worries. 1. Cushing's syndrome. As discussed, Cushing's involves any of a number of types of tumors that produce a vast damaging excess of glucocorticoids, where the consequences include impairment of hippocampal-dependent memory. Monica Starkman at the University of Michigan has used brain imaging techniques on Cushing's patients to look at the overall size of the brain and the sizes of various subsections. She reports that there is a selective decrease in the volume of the hippocampus in these individuals. Moreover, the more severe the glucocorticoid excess, the greater the loss of hippocampal volume, and the greater the memory problems. 2. Post-traumatic stress disorder, PTSD. As will be discussed in more detail in Chapter 15, this anxiety disorder can arise from a variety of types of traumatic stressors. Work pioneered by Douglas Bremner of Emory University, replicated by others, shows that people with PTSD from repeated trauma, as opposed to a single trauma, soldiers exposed to severe and repeated carnage in combat, individuals repeatedly abused as children, have smaller hippocampi. Again, the volume loss appears to be only in the hippocampus, and in at least one of those studies, the more severe the history of trauma, the more extreme the volume loss. 3. Major depression. As will be detailed in Chapter 14, major depression is utterly intertwined with prolonged stress, and this connection includes elevated glucocorticoid levels in about half the people with major depression. Yvette Chéline of Washington University and others have shown that prolonged major depression is once again associated with a smaller hippocampus. The more prolonged the history of depression, the more volume loss. Furthermore, it is in patients with the subtype of depression that is most associated with elevated glucocorticoid levels, where you see the smaller hippocampus. 4. Repeated jet lag. Chapter 11 will consider a single but intriguing study examining airline flight attendants with long careers of shifting time zones on intercontinental flights. The shorter the average time allowed to recover from each large bout of jet lag over a career, the smaller the hippocampus and the more memory problems. 5. Normative aging. Work by Sonia Lupin of McGill University, and replicated by others, has examined healthy elderly people. Check out what their resting glucocorticoid levels are, the size of their hippocampus, and the quality of their hippocampal-dependent memory. Then come back some years later and retest them. As will be discussed in Chapter 12 on aging, there is somewhat of a rise in resting glucocorticoid levels with age in humans, although there is a lot of variability in this. What is seen is that those whose glucocorticoid levels have been rising over the years since the study began are the ones who have had the most severe loss of hippocampal volume and the greatest decline in memory. 6. Interactions between glucocorticoids and neurological insults. A handful of studies report that for the same severity of a stroke, The higher the glucocorticoid levels in a person at the time they come into an emergency room, the more ultimate neurological impairment. So, these studies collectively demonstrate that glucocorticoids damage the human hippocampus. Well, let's hold on a second. There are some problems and complications. First, there have been some studies suggesting that PTSD involves lower than normal levels of glucocorticoids. Thus, it can't be the case that an excess of the hormones is damaging the hippocampus. However, it looks as if in those PTSD patients with the low levels, there is excessive sensitivity to the glucocorticoids. So the hormones are still plausible culprits. As a next issue, it isn't clear whether the loss of hippocampal volume in PTSD is caused by the trauma itself or by the post-traumatic period. Amid that uncertainty, there has been at least one excellent study upending both of those ideas. It suggested instead that having a small hippocampus comes before the PTSD, and in fact makes you more likely to develop PTSD when exposed to trauma. Finally, it should be remembered that the aging studies present a relationship that is merely correlative. In other words, yes, it could be that increasing glucocorticoid levels with age lead to hippocampal atrophy, but there are at least as good reasons to think that it is the other way around, that progressive hippocampal atrophy leads to the rising glucocorticoid levels, as will be explained more fully in Chapter 12. This is because the hippocampus also helps to inhibit glucocorticoid release, such that an atrophied hippocampus isn't very good at that task. In other words, no one is quite sure yet what is going on. One of the biggest problems is a lack of studies of brains like these after people have died. Phenomenally obsessive research could be carried out that would tell us whether the hippocampus is smaller because there are fewer of the millions of hippocampal neurons, or because neurons have fewer and shorter cables connecting them to other neurons. Or both. If it turned out that there were fewer neurons, you might even be able to tell whether it is because more of them have died than usual, or because fewer of them were born. Or again, both. Actually, even without the post-mortem studies, there are a few hints about the sources of the volume loss. Intriguingly, when the tumor that gave rise to the Cushing's syndrome is removed and the glucocorticoid levels revert to normal, the hippocampus slowly comes back to normal size. As noted before, when glucocorticoids cause the cables connecting neurons to shrivel up, it is not a permanent process. Stop the glucocorticoid excess and the processes can slowly regrow. Thus, the best guess is that the volume loss in Cushing's is based on the retraction of processes. In contrast, the volume losses in PTSD and major depression appear to be something approaching permanent, in that the loss persists in the former case decades after the trauma, and in the latter, years to decades after the depression has been gotten under control with medication. So in those cases, the volume loss in the hippocampus probably can't be due to shriveling processes of neurons, given that the shriveling can reverse. Beyond that, no one knows at this point why the hippocampus winds up being smaller in these disorders and situations. It is the knee-jerk reflex of all scientists to say, more research is needed. But more research really is needed in this case. For the moment, I think it is fair to say that there is decent but not definitive evidence that stress and/or prolonged exposure to glucocorticoids can cause structural as well as functional changes in the hippocampus, that these are changes that you probably wouldn't want to have happen to your hippocampus, and that these changes can be long-lasting. What are some of the disturbing implications of these findings? The first concerns the use by neurologists of synthetic versions of glucocorticoids, such as hydrocortisone, dexamethasone, or prednisone, after someone has had a stroke. As we know from our introduction to glands and hormones in Chapter 2, glucocorticoids are classic anti-inflammatory compounds and are used to reduce the edema, the damaging brain swelling that often occurs after a stroke. Glucocorticoids do wonders to block the edema that occurs after something like a brain tumor, but it turns out that they don't do much for post-stroke edema. Worse, There's increasing evidence that those famously anti-inflammatory compounds can actually be pro-inflammatory, worsening inflammation in the injured brain. Yet, tons of neurologists still prescribe the stuff, despite decades-old warnings by the best people in the field, and findings that the glucocorticoids tend to worsen the neurological outcome. So these recent findings add a voice to that caution. Clinical use of glucocorticoids tends to be bad news for neurological diseases that involve a precarious hippocampus. As a caveat, however, it turns out that huge doses of glucocorticoids can occasionally help reduce damage after a spinal cord injury, for reasons having nothing to do with stress or with much of this book. Related to this is the concern that physicians may use synthetic glucocorticoids to treat problems outside the nervous system, and in the process might endanger the hippocampus. A scenario that particularly disturbs me concerns the ability of these hormones to worsen GPL-20 damage to neurons and its relevance to AIDS-related dementia. Remember, the GPL-20 protein is found in the AIDS virus and appears to play a central role in damaging neurons and causing the dementia. If many experiments down the line, it turns out that glucocorticoids can worsen the cognitive consequences of HIV infection, this will be worrisome. That isn't just because people with AIDS are under stress. It's also because people with AIDS are often treated with extremely high doses of synthetic glucocorticoids to combat other aspects of the disease. This same logic extends to the use of glucocorticoids in other realms of clinical medicine. About 16 million prescriptions are written annually in the United States for glucocorticoids. Much of the use is benign. A little hydrocortisone cream for some poison ivy, a hydrocortisone injection for a swollen knee, maybe even use of steroid inhalants for asthma, which is probably not a worrisome route for glucocorticoids to get into the brain. But there are still hundreds of thousands of people taking high-dose glucocorticoids to suppress the inappropriate immune responses in autoimmune diseases, such as lupus, multiple sclerosis, or rheumatoid arthritis. As discussed earlier, prolonged glucocorticoid exposure in these individuals is associated with problems with hippocampal-dependent memory. So should you avoid taking glucocorticoids for your autoimmune disease in order to avoid the possibility of accelerated hippocampal aging somewhere down the line? Almost certainly not. These are often devastating diseases, and glucocorticoids are often highly effective treatments. Potentially, the memory problems are a particularly grim and unavoidable side effect. An even more disturbing implication of these findings is that if glucocorticoids turn out to endanger the human hippocampus, making it harder for neurons to survive an insult, you're still in trouble, even if your neurologist doesn't administer synthetic glucocorticoids to you. This is because your body secretes boatloads of the stuff during many neurological crises. Humans coming into ERs after neurological insults have immensely high levels of glucocorticoids in their bloodstreams. And what we know from rats is that the massive outpouring of glucocorticoids at that time adds to the damage. Remove the adrenals of a rat right after a stroke or seizure, or use a drug that will transiently shut down adrenal secretion of glucocorticoids, and less hippocampal damage will result. In other words, what we think of as typical amounts of brain damage after a stroke or seizure is damage being worsened by the craziness of our bodies having stress responses at the time. Consider how bizarre and maladaptive this is. Lion chases you. You secrete glucocorticoids in order to divert energy to your thigh muscles. Great move. Go on a blind date. Secrete glucocorticoids in order to divert energy to your thigh muscles. Probably irrelevant. Have a grand mal seizure. Secrete glucocorticoids in order to divert energy to your thigh muscles and make the brain damage worse. This is as stark a demonstration as you can ask for, that a stress response is not always what you want your body to be having. How did such maladaptive responses evolve? The most likely explanation is that the body simply has not evolved the tendency not to secrete glucocorticoids during a neurological crisis. Stress-induced glucocorticoid secretion works roughly the same in all the mammals, birds, and fish. and it has only been in the last half-century or so that westernized versions of just one of those species had much of a chance of surviving something like a stroke. There simply has not been much evolutionary pressure yet to make the body's response to massive neurological injury more logical. We are now 50, 60 years into thinking about ulcers, blood pressure, and aspects of our sex lives as being sensitive to stress. Most of us recognize the ways in which stress can also disrupt how we learn and remember. This chapter raises the possibility that the effects of stress in the nervous system might extend even to damaging our neurons, and the next chapter continues this theme in considering how stress might well accelerate the aging process of our brains. The noted neuroscientist Woody Allen once said, "My brain is my second favorite organ." My guess is that most of us would rank our brains even higher up on a list.
This is the end of the CD. The audiobook continues on the next CD.
Chapter 11. Stress and a Good Night's Sleep. Then there was the day when my son was about 2 weeks old. He was our firstborn, and we had been plenty nervous about how demanding parenting was going to be. It had been a great day. He'd slept well through the night, waking up a few times to nurse, and took some long naps during the day that allowed us to do the same. We'd settled into a schedule. My wife did the nursing, and I fetched the tureens of cranberry juice that she had become obsessed with since giving birth. Our son filled his diapers on cue, and his every gesture was confirming how wondrous he was. Things were calm. In the evening, as he slept and we settled into our old routines, like doing dishes, the first time in days, I indulged myself in some editorializing about the human condition. You know, this newborn business is really quite manageable if you just stay on top of things. You need to work as a team, be organized, roll with the punches. I went on fatuously like this for a while. That night, our son woke up to nurse right after we fell asleep. He was fussy, wouldn't go back to sleep unless I patted him repeatedly, protested each time I tried to stop by waking up. This went on for an insane hour, and then he needed to nurse again. Then, after patting him some more, he responded by blowing out his diaper, making a mess of his onesie and me. Then he screamed bloody murder when I washed him off. Finally, he then slept contentedly without patting for about 20 minutes, before needing to nurse again, another blowout soiling of his fresh onesie, followed by our discovery that we had no clean ones, having neglected to do the laundry. Rather than doing something useful, I orated in a half-psychotic state. "We can't do this. We're going to die. I'm serious. People die from lack of sleep. It's not possible to do this. It's physiologically proven. We're all going to die." I swung my arms with emphasis, knocking over and loudly breaking a glass of cranberry juice. This woke up our, by then, happily sleeping son, causing all three of us to burst into tears. He eventually settled down and slept like a baby for the rest of the night, while I tossed anxiously, waiting for him to wake up again. Contained in this are the two central features of this chapter. Not getting enough sleep is a stressor. Being stressed makes it harder to sleep. Yep, we've got a dread vicious cycle on our hands. The basics of sleep. All things considered, sleeping is pretty creepy. For a third of your life, you're just not there, floating in this suspended state, everything slowed down. Except, at points, your brain is more active than when you're awake, making your eyelids all twitchy, and it's consolidating memories from the day and solving problems for you. Except when it's dreaming, when it's making no sense. And then you sometimes walk or talk in your sleep, or drool. And then there's those mysterious penile or clitoral erections that occur intermittently during the night. Weird. What's going on here? To start, sleep is not a monolithic process, a uniform phenomenon. Instead, there are different types of sleep. Shallow, also known as stages 1 and 2 sleep, where you are easily awakened. Deep sleep, also known as stages 3 and 4, or slow wave sleep, rapid eye movement, REM sleep, where the puppy's paws flutter and our eyes dart around and dreams happen. There are not only these different stages, but a structure, an architecture to them. You start off shallow, gradually sleep your way down to slow wave sleep, followed by REM, then back up again, and then repeat the whole cycle about every 90 minutes. And as we'll see in Chapter 14, something goes wrong with the architecture of sleep during a major depression. Not surprisingly, the brain works differently in different stages of sleep. This can be studied by having people sleep in a brain scanner while you measure the levels of activity of different brain regions. Take some volunteers, sleep-deprive them for some god-awful length of time, stick them in one of these imaging machines, poke them awake a little more while you get a measure of their brain's activity when they're awake, and then, snug as a bug in a scanner, let them go to sleep with the scanner running. The picture during slow-wave sleep makes lots of sense. Parts of the brain associated with arousal activity slow down. Ditto for brain regions involved in controlling muscle movement. Interestingly, regions involved in the consolidation and retrieval of memories don't have much of a decrease in metabolism. However, the pathways that bring information to and from those regions shut down dramatically, isolating them. The parts of the brain that first respond to sensory information have somewhat of a metabolic shutdown. But the more dramatic changes are in downstream brain areas that integrate, associate those bites of sensory information, and give them meaning. What you've got is a metabolically quiescent sleeping brain. This makes sense, as deep, slow wave sleep is when energy restoration occurs. This is shown by the fact that the extent of sleep deprivation is not a great predictor of the total amount you will ultimately sleep, but it is a good predictor of how much slow-wave sleep there'll be. A very active brain, or a sleep-deprived brain, tends to consume a lot of a particular form of energy. The breakdown product of that depleted form of energy is the signal that biases towards slow-wave sleep. A very different picture emerges during REM sleep. Overall, there's an increase in activity. Some brain regions become even more metabolically active than when you're awake. Parts of the brain that regulate muscle movement, brainstem regions that control breathing and heart rate, all increase their metabolic rate. In a part of the brain called the limbic system, which is involved in emotion, there is an increase as well. The same for areas involved in memory and sensory processing, especially those involved in vision and hearing. Something particularly subtle goes on in the visual processing regions. The part of the cortex that processes the first bits of visual information does not show much of an increase in metabolism, whereas there is a big jump in the downstream regions that integrate simple visual information. How can this be when, on top of it, your eyes are closed? This is dreaming. That tells us something about how dream imagery arises. But something else that happens in the brain tells us something about the content of dreams. There's a part of the brain, briefly mentioned in the last chapter, called the frontal cortex. It's the most recently evolved part of the human brain, is disproportionately huge in primates, and is the last part of our brain to fully mature. The frontal cortex is the nearest thing we have to a superego. Starting from toilet training, it helps you to do the harder rather than easier thing. For example, thinking in a logical, sequential manner rather than bouncing all over the place cognitively. It keeps you from murdering someone just because you feel like it, stops you from telling someone exactly what you think of their hideous outfit, and instead finds something complimentary. The frontal cortex does all this disciplining of you by inhibiting that frothy emotional limbic system. If you damage the frontal cortex, someone gets frontally disinhibited, doing and saying the things we may think about but would never act upon. During REM sleep, metabolism in the frontal cortex goes way down, disinhibiting the limbic system to come up with the most outlandish ideas. That's why dreams are dreamlike, illogical, non-sequential, hyper-emotional. You breathe underwater, fly in the air, communicate telepathically. You announce your love to strangers, invent languages, rule kingdoms, star in Busby Berkeley musicals. So those are the nuts and bolts of sleep. But what is sleep for? You die without it. Even fruit flies do. The most obvious answer is to have a stretch where your brain is going at half speed in order to build up supplies of energy. Your brain consumes phenomenal amounts of energy to pull off all that calculus and symphony writing that you do. The brain constitutes something like 3% of your body weight, but needs nearly a quarter of the energy. So stores tend to decline during the day, and some solid, slow wave sleep is needed to restock those stores, mostly of a molecule called glycogen, which is also an energy store in liver and muscle. Others speculate that sleep is for decreasing brain temperature, letting it cool off from all that daytime brainstorming, or for detoxifying the brain. Weirdly, another major reason to sleep is to dream. If you skip a night's sleep, when you finally get to sleep the next night, you have more REM sleep than normal, suggesting that you've built up a real deficit of dreaming. Some extremely difficult studies that make me queasy just to contemplate deprive people or animals of REM sleep preferentially, and the study subjects go to pieces much faster than they do for the equivalent amount of deprivation of other types of sleep. Thus, this begs the question of what dreaming is for. To work out unresolved issues about your mother? To provide a living for surrealists and Dadaists? So you can have a sex dream about some unlikely person in your waking life, and then act all weird around that person the next morning by the water cooler? Well, maybe. The marked increase in metabolic activity during REM sleep, and in some of the most inhibited areas of the brain during waking, have suggested to some a sort of use it or lose it scenario, in which dreaming gives some aerobic exercise to otherwise underutilized brain pathways. That is, the oft-neglected Busby Berkeley musical brain circuit. What has become clear is that sleep plays a role in cognition. For example, sleep can facilitate problem solving. This is the realm of sleeping on a problem and then suddenly discovering a solution the next morning while you're cleaning crud out of the corners of your eyes. The neurobiologist Robert Sapolsky of Harvard has emphasized that this type of problem solving is the kind where a morass of unhelpful facts are broken through to get to feelings. As he says, you don't forget a phone number and then sleep on it to remember it. You do it for some complex, ambiguous problem. Both slow-wave and REM sleep also seem to play roles in the formation of new memories, the consolidation of information from the previous day, even information that became less accessible to you while awake over the course of the day. One type of evidence supporting this is the fact that if you teach an animal some task and disrupt its sleep that night, the new information isn't consolidated. While this has been shown in many different ways, the interpretation remains controversial. As we saw in the last chapter, stress can disrupt memory consolidation. As we're about to see in great detail, sleep deprivation is stressful. Maybe sleep deprivation disrupts memory consolidation merely because of the stress, which wouldn't prove that sleep normally helps memory consolidation. But the pattern of memory disruption caused by sleep deprivation is different from that caused by stress. Another type of evidence is correlative. Being exposed to lots of new information during the day is associated with more REM sleep that night. Moreover, the amount of certain subtypes of sleep at night predicts how well new information is recalled the next day. For example, lots of REM sleep during the night predicts better consolidation of emotional information from the day before, while lots of stage 2 sleep predicts better consolidation of a motor task, and a combination of lots of REM and slow-wave sleep predicts better retention of perceptual information. Others have taken this further, reporting that it's not just the amount of some subtype of sleep that predicts some subtype of learning, but whether it occurs early or late in the night. Another style of evidence for the sleep helps you consolidate memories story was first obtained by Bruce McNaughton of the University of Arizona. As we saw in Chapter 10, The hippocampus has a central role in explicit learning. McNaughton recorded the activity of single hippocampal neurons in rats, identifying ones that became particularly busy while the rat was learning some new explicit information. That night, during slow-wave sleep, it would be those same neurons that would be particularly busy. Taking that one step further, he showed that patterns of activation of hippocampal neurons that occur during learning are then repeated when the animal is sleeping. Brain imaging studies with humans have shown something similar. There's even evidence that when consolidation is going on during REM, genes are activated that help form new connections between neurons. During slow-wave sleep, metabolism remains surprisingly high in areas like the hippocampus. It's as if sleep is the time when the brain practices those new memory patterns over and over, cementing them into place. Weirdly, amid this general picture of sleep deprivation disrupting cognition, at least one type of learning is facilitated by sleep deprivation, as shown in some recent work by a graduate student of mine, Lana Hairston. Suppose you have some unlikely task where you have to learn to recite the months of the year backward as rapidly as possible. Why is this going to be hard? Because there will repeatedly be the pull to recite the months in the way that you've done your whole life, which is forward. The previous, overlearned version of the task interferes with this new reversal task. Who would excel at this task? Someone who has never learned to do January, February, March, etc. automatically in that direction. If you sleep-deprive some rats and give them a rat's equivalent of a reversal task, they do better than do control animals. Why? Because they can't remember the prior overlearned version of the task well enough for it to intrude now. So now we have the basics of sleep and what it might be good for. Entrée stress. Sleep deprivation as a stressor. As we glide down into slow-wave sleep, some obvious things occur to facets of the stress response system. For starters, the sympathetic nervous system shuts down in favor of that calm, vegetative parasympathetic nervous system. In addition, glucocorticoid levels go down. As introduced back in Chapter 2, CRH is the hypothalamic hormone that gets the pituitary to release ACTH in order to trigger adrenal release of glucocorticoids. Some of the hypothalamic control of pituitary hormone release consists of an accelerator and a brake, a releasing factor and an inhibiting factor. For years, there's been evidence floating around for a hypothalamic corticotropin inhibiting factor, CIF, that would inhibit the release of ACTH, counteracting the effects of CRH. No one's sure what CIF is, or if it really exists, but there's some decent evidence that CIF is a brain chemical that helps bring on slow-wave sleep, called delta sleep-inducing factor. Thus, sleep deeply, and you turn off glucocorticoid secretion. In contrast, during REM, as you're mobilizing all that energy to generate that outlandish dream imagery and to move your eyes rapidly, glucocorticoid secretion and the sympathetic nervous system rev up again. But given that most of what counts as a good night's sleep consists of slow-wave sleep, sleep is predominantly a time when the stress response is turned off. This is seen in species whether they're nocturnal or diurnal, that is, sleeping during the dark hours like us. About an hour before you wake up, levels of CRH, ACTH, and glucocorticoids begin to rise. This is not just because merely rousing from slumber is a mini-stressor, requiring mobilization of some energy, but because those rising stress hormone levels play a role in terminating sleep. So deprive yourself of sleep, and the sleep-induced decline in the levels of those stress hormones doesn't occur. And no surprise, they rise instead. Glucocorticoid levels increase and the sympathetic nervous system is activated. Commensurate with everything that's been reviewed in previous chapters, down go levels of growth hormone and of various sex hormones. Sleep deprivation definitely stimulates glucocorticoid secretion, although not to a massive extent in most studies, unless the sleep deprivation is really prolonged. However, It is postulated that these increases in response to severe sleep deprivation are due to the stress of dying rather than to sleep loss, dryly noted one journal article. The elevated glucocorticoid levels during sleep deprivation play a role in breaking down some of the stored forms of energy in the brain. This, along with many of the glucocorticoid effects on memory, could have something to do with why learning and memory are so lousy when you're sleep deprived. That's something we all learned when doing an all-nighter and discovering the next morning during the final exam that we can barely recall what month it was, let alone any of the factoids crammed in our heads the previous night. A recent study beautifully demonstrated one way in which our brains become impaired when we try to think hard on no sleep. Take a normally rested subject, stick her in a brain imager, and ask her to solve some working memory problems, holding on to some facts and manipulating them, like adding sequences of 3-digit numbers. As a result, her frontal cortex lights up metabolically. Now take someone who is sleep-deprived, and he's awful at the working memory task. And what's going on in his brain? What you might have guessed is that frontal metabolism would be inhibited, too groggy to get activated in response to the task. Instead, the opposite occurs. The frontal cortex is activated, but so are large parts of the rest of the cortex. It's as if sleep deprivation has reduced this gleaming computer of a frontal cortex to a bunch of unshaven, gibbering neurons counting on their toes, having to ask the rest of their cortical buddies to help out with this tough math problem. So why care if sleep deprivation is a stressor? It's obvious. We're accustomed to all sorts of amenities in our modern lives. Overnight deliveries of packages, advice nurses who can be called at 2 in the morning, round-the-clock technical support staff. Therefore, people are required to work under conditions of sleep deprivation. We're not a nocturnal species, and if a person works at night or works swing shifts, regardless of how many total hours of sleep she's getting, it's going against her biological nature. People who work these sorts of hours tend to overactivate the stress response, and there's little habituation that goes on. Given that an overactive stress response makes every section of this book relevant, it is not surprising that night work or shift work increases the risk of cardiovascular disease, gastrointestinal disorders, immune suppression, and fertility problems. A widely reported study a few years back really brought this into focus. Recall how prolonged stress and glucocorticoids can damage the hippocampus and impair hippocampal-dependent explicit memory. Kay Cho of the University of Bristol studied flight attendants working for 2 different airlines. On one airline, after you worked a transcontinental flight with major jet lag, you'd have a 15-day break until being scheduled for the next transcontinental flight. In contrast, on airline number 2, presumably with a weaker union, you got a 5-day break before the next transcontinental flight. Cho controlled for total amount of flying time and total number of time zones shifted in the course of flying. Thus, airline number 2's crews didn't experience more total jet lag, just less time to recover. Finally, Cho considered only employees who had been doing this for more than 5 years. He found that airline number 2's attendants had, on average, impaired explicit memory, higher glucocorticoid levels, and a smaller temporal lobe, the part of the brain that contains the hippocampus. This study was briefly alluded to in Chapter 10. This is obviously not a good thing for the employees working under these conditions. And this may make it less likely that the flight attendant will remember that 17C requested a mixture of ginger ale and skim milk with ice. But it kind of makes one wonder whether the back-to-the-grind-after-5 days pilot is having trouble remembering whether or not this little old switch turns the engine on or off. These worries about sleep deprivation are relevant to even those whose 9-to-5 job is 9 to 5 during daylight hours. We have an unprecedented number of ways to make us sleep deprived, beginning with something as simple as indoor lighting. In 1910, the average American slept 9 hours a night, disturbed only by the occasional Model T backfiring. We now average 7.5 and declining. When there's the lure of 24-hour-a-day fun, activities, and entertainment, or for the workaholic, The knowledge that somewhere in some time zone, someone else is working while you indulge yourself in sleep, that pull of just a few more minutes of pushing yourself, becomes irresistible and damaging. And stress as a disruptor of sleep. What should happen to sleep during stress? This one's simple, given a zebra-ocentric view of the world. Lion coming, don't nap. Or as the old joke goes, the lion and the lamb shall lie down together, but the lamb won't get much sleep. The hormone CRH seems to be most responsible for this effect. As you'll recall, the hormone not only starts the glucocorticoid cascade by stimulating ACTH release from the pituitary, but it is also the neurotransmitter that activates all sorts of fear, anxiety, and arousal pathways in the brain. Infuse CRH into a sleeping rat's brain and you suppress sleep. It's like throwing ice water onto those happily dozing neurons. Part of this is due to the direct effects of CRH in the brain, but part is probably due to CRH activating the sympathetic nervous system. If you go up to high altitude without acclimating, your heart is going to be racing, even when you're not exerting yourself. This is not because you are stressed or anxious, but simply because your heart has to beat more often to deliver sufficient oxygen. Suddenly you discover that it's awfully hard to fall asleep with your eyeballs throbbing rhythmically, 110 times a minute. So the bodily consequences of sympathetic activation make sleeping hard. Not surprisingly, about 75% of cases of insomnia are triggered by some major stressor. Moreover, many, but not all, studies show that poor sleepers tend to have higher levels of sympathetic arousal or of glucocorticoids in their bloodstream. So, lots of stress and potentially little sleep. But stress not only can decrease the total amount of sleep, but can compromise the quality of whatever sleep you do manage. For example, when CRH infusion decreases the total amount of sleep, it's predominantly due to a decrease in slow-wave sleep, exactly the type of sleep you need for energy restoration. Instead, your sleep is dominated by more shallow sleep stages, meaning you wake up more easily. Fragmented sleep. Moreover, when you do manage to get some slow-wave sleep, you don't even get the normal benefits from it. When slow-wave sleep is ideal, really restoring those energy stores, there's a characteristic pattern in what is called the delta power range that can be detected on an EEG, electroencephalogram, recording. When people are stressed pre-sleep or are infused with glucocorticoids during sleep, you get less of that helpful sleep pattern during slow-wave sleep. Glucocorticoids compromise something else that occurs during good quality sleep. Jan Born of the University of Lübeck in Germany has shown that if you infuse glucocorticoids into someone while they're sleeping, you impair the memory consolidation that would normally be occurring during slow-wave sleep. A causes B, causes A, causes B, causes... We have the potential for some real problems here, insofar as lack of sleep or poor quality sleep activates the stress response, and an activated stress response makes for less sleep or lower quality sleep. Each feeds on the other. Does that mean that experiencing even a smidgen of stress, or staying up late once to see Ted Koppel interview Britney Spears about the evidence for and against global warming, and that's it, you're finished? Downward spiral of stress and sleep deprivation? Obviously not. For one thing, as mentioned, sleep deprivation doesn't cause all that massive of a stress response. Moreover, the need to sleep will eventually overcome the most stressful of stressors. Nonetheless, a fascinating study suggests how the two halves might interact, along the lines that the expectation that you're going to sleep poorly makes you stressed enough to get poor quality sleep. In the study, one group of volunteers was allowed to sleep for as long as they wanted, which turned out to be until around 9 in the morning. As would be expected, their stress hormone levels began to rise around 8. How might you interpret that? These folks had enough sleep, happily restored and re-energized, and by about 8 in the morning their brains knew it. Start secreting those stress hormones to prepare to end the sleep. But the second group of volunteers went to sleep at the same time, but were told that they would be woken up at 6 in the morning. And what happened with them? At 5 in the morning, their stress hormone levels began to rise. This is important. Did their stress hormone levels rise 3 hours earlier than the other group because they needed 3 hours less sleep? Obviously not. The rise wasn't about them feeling rejuvenated. It was about the stressfulness of anticipating being woken up earlier than desirable. Their brains were feeling that anticipatory stress while sleeping, demonstrating that a sleeping brain is still a working brain. What might be happening, then, if you go to sleep thinking that not only will you be woken up earlier than you would like, but at an unpredictable time, where any minute could be your last minute of sleep for the night? It's quite possible that stress hormone levels will be elevated throughout the night, in nervous anticipation of that wake-up call. As we've seen, with an elevated stress response during sleep, the quality of the sleep is going to be compromised. Thus, there is a hierarchy as to what counts as miserable sleep. Continuous, uninterrupted sleep, but too little of it. Deadline looming, go to sleep late, get up early, not good. Even worse is too little sleep that is fragmented. As an example, I once did an experiment where every 3 hours for days I had to take blood samples from some animals. Even though I did next to nothing on these nights and days other than sleep, in fact, I got more total sleep per day than was usual for me. I was a wreck. But worst of all is too little sleep that is unpredictably fragmented. You finally get back to sleep, but with the corrosive knowledge that 5 hours or 5 minutes from now, another patient will come into the emergency room, or the alarms will go off and it's back to the fire truck, or someone's diaper will slowly but surely fill up. This teaches us a lot about what counts as good sleep and how stress can prevent it. But as we'll see in a couple of chapters, this generalizes beyond sleep. When it comes to what makes for psychological stress, a lack of predictability and control are at the top of the list of things you want to avoid. Chapter 12. Aging and Death. Predictably, it comes at the most unpredictable times. I'll be lecturing, bored, telling the same story about neurons I did last year. Daydreaming, looking at the ocean of irritatingly young undergraduates. And then it hits, producing almost a sense of wonderment. How can you just sit there? Am I the only one who realizes that we're all going to die someday? Or I'll be at a scientific conference, this time barely understanding someone else's lecture, and amid the roomful of savants, a wave of bitterness will sweep over me. All you damned medical experts, and not one of you can make me live forever. It first really dawns on us emotionally sometime around puberty. Woody Allen, once our untarnished high priest of death and love, captures its roundabout assault perfectly in Annie Hall. The protagonist is shown in flashback as a young adolescent. He is sufficiently depressed for the worried mother to drag him to the family doctor. Listen to what he keeps saying. What's wrong with him? Does he have the flu? The Allen-esque adolescent, glazed with despair and panic, announces in a monotone, "The universe is expanding." It's all there. The universe is expanding. Look how big infinity is and how finite we are. And he has been initiated into the great secret of our species. We will die, and we know it. With that rite of passage, he has found the motherlode of psychic energy that fuels our most irrational and violent moments, our most selfish and our most altruistic ones, our neurotic dialectic of simultaneously mourning and denying, our diets and exercising, our myths of paradise and resurrection. It's as if we were trapped in a mine shouting out for rescuers. Save us! We're alive, but we're getting old and we're going to die. And of course, before dying, most of us will become old, a process aptly described as not for sissies. Racking pain, dementia so severe we can't recognize our children, cat food for dinner, forced retirement, colostomy bags, muscles that no longer listen to our commands, organs that betray us, children who ignore us. Mostly that aching sense that just when we finally grow up and learn to like ourselves and to love and play, the shadows lengthen. There is so little time. Oh, it doesn't have to be that bad. For many years I have spent part of each year doing stress research on wild baboons in East Africa. The people living there, like many people in the non-westernized world, clearly think differently about these issues than we do. No one seems to find getting old depressing. How could they? They wait their whole lives to become powerful elders. My nearest neighbors are of the Maasai tribe, nomadic pastoralists. I often patch up their various minor injuries and ills. One day, one of the extremely old men of the village, perhaps 60 years old, tottered into our camp. Ancient, wrinkled beyond measure, tips missing from a few fingers, frayed earlobes, long-forgotten battle scars. He spoke only Maasai and not Swahili, the lingua franca of East Africa, so he was accompanied by his more worldly, middle-aged neighbor who translated for him. He had an infected sore on his leg, which I washed and treated with antibiotic ointment. He also had trouble seeing. Cataracts was my barely educated guess, and I explained that they were beyond my meager curative powers. He seemed resigned, but not particularly disappointed, and as he sat there cross-legged, naked except for the blanket wrapped around him, basking in the sun, the woman stood behind him and stroked his head. In a voice as if describing last year's weather, she said, "Oh, when he was younger, he was beautiful and strong. Soon he will die." That night in my tent, sleepless and jealous of the Maasai, I thought, I'll take your malaria and parasites. I'll take your appalling infant mortality rates. I'll take the chances of being attacked by buffalo and lions. Just let me be as unafraid of dying as you are. Maybe we will luck out and wind up as respected village elders. Perhaps we will grow old with grace and wisdom. Perhaps we will be honored, surrounded by strong, happy children whose health and fecundity will feel like immortality to us. Gerontologists studying the aging process find increasing evidence that most of us will age with a fair degree of success. There's far less institutionalization and disability than one might have guessed. While the size of social networks shrink with age, the quality of the relationships improves. There are types of cognitive skills that improve in old age. These are related to social intelligence and to making good strategic use of facts, rather than merely remembering them easily. The average elderly individual thinks his or her health is above average and takes pleasure from that. And most important, the average level of happiness increases in old age. Fewer negative emotions occur, and when they do, they don't persist as long. Connected to this, brain imaging studies show that negative images have less of an impact, and positive images have more of an impact on brain metabolism in older people, as compared to young. So maybe old age is not so bad. The final chapter of this book reviews some of the patterns seen in aged people who are particularly successful in their aging. The purpose of this chapter is to review what stress has to do with the aging process, and whether we wind up with the honored village elder model of aging or the cat food variant. Aged organisms and stress. How do aged organisms deal with stress? Not very well, it turns out. In many ways, aging can be defined as the progressive loss of the ability to deal with stress, and that certainly fits our perception of aged individuals as fragile and vulnerable. This can be stated more rigorously by saying that many aspects of the bodies and minds of old organisms work fine, just as they do in young ones, so long as they aren't pushed. Throw in an exercise challenge, an injury or illness, time pressure, novelty, any of a variety of physical, cognitive, or psychological stressors, and aged organisms don't do so well. Not doing so well in the stress response department can take at least two forms that should be familiar by now. The first is failing to activate a sufficient stress response when it is needed. This occurs at many levels during aging. For example, individual cells have a variety of defenses they can mobilize in response to a challenge, that can be viewed as a cellular stress response. Heat a cell to an unhealthy extent, and heat shock proteins are synthesized to help stabilize cellular function during a crisis. Damage DNA and DNA repair enzymes are activated. Generate oxygen radicals and antioxidant enzymes are made in response. And all of these cellular stress responses become less responsive to challenge during aging. A similar theme comes through at the level of how whole organ systems respond to stress. For example, after you eliminate from your study elderly people who have heart disease and look only at healthy subjects of different ages, so as to study aging instead of inadvertently studying disease, many aspects of cardiac function are unchanged by age. But challenge the system with exercise, for example, and old hearts do not respond as adequately as do young ones, in that the maximal work capacity and the maximal heart rate that can be achieved are nowhere near as great as in a young person. Similarly, in the absence of stress, old and young rat brains contain roughly the same amount of energy. But when you stress the system by cutting off the flow of oxygen and nutrients, energy levels decline faster in the old brains. Or as a classic example, normal body temperature, 98.6 degrees, does not change with age. Nevertheless, aged bodies are impaired in mounting a thermoregulatory stress response, and thus it takes the bodies of the elderly longer to restore a normal temperature after being warmed or chilled. The idea also applies to measures of cognition. What happens to IQ test scores as people get older? You'll notice that I didn't say intelligence. What that has to do with IQ test scores is a controversy I don't want to touch. The dogma in the field was once that IQ declined with age. Then it was that it did not decline. It depends on how you test it. If you test young and old people and give them lots of time to complete the test, there is little difference. As you stress the system, in this case by making the subjects race against a time limit, scores fall for all ages, but much further among older people. So, sometimes the problem in aging is not enough of a stress response. Predictably, in some realms, the problem is too much of a stress response, either one turned on all the time, or one that takes too long to turn off at the end of a stressor. As an example, older individuals are impaired at turning off epinephrine, norepinephrine, or glucocorticoid secretion after a stressor has finished. It takes longer for levels of these substances to return to baseline. Moreover, even in the absence of the stressor, epinephrine, norepinephrine, and glucocorticoid levels are typically elevated in aged rats, non-human primates, and humans as well. Do aged organisms pay a price for having these components of the stress response turned on too often? This seems to be the case. As one example, which was discussed in the chapter on memory, stress and glucocorticoids inhibit the birth of new neurons in the adult hippocampus and inhibit the growth of new processes in pre-existing neurons. Is the birth of new neurons and the elaboration of neuronal processes preferentially inhibited in old rats? Yes. And if their glucocorticoid levels are lowered, neurogenesis and process growth increase to levels seen in young animals. We know by now that ideally the hormones of the stress response should be nice and quiet when nothing bad is happening, secreted in tiny amounts. When a stressful emergency hits, your body needs a huge and fast stress response. At the end of the stressor, everything should shut off immediately. And these traits are precisely what old organisms typically lack. Why you seldom see really old salmon. We shift over to the other half of the aging-stress relationship. Not whether aged organisms can deal well with stress, but whether stress can accelerate aspects of aging. There is some decent evidence that an excess of stress can increase the risk of some of the diseases of aging. Remarkably, it turns out that in more than a dozen species, glucocorticoid excess is the cause of death during aging. Pictures of heroic wild animals, a la Marlin Perkins. Penguins who stand all winter amid the Antarctic cold, keeping their eggs warm at their feet. Leopards dragging massive kills up trees with their teeth in order to eat them free of harassment by lions. Desiccated camels marching scores of miles. And then there's salmon, leaping over dams and waterfalls to return to the freshwater stream of their birth, where they spawn a zillion eggs, after which most of them die over the next few weeks. Why do salmon die so soon after spawning? No one is quite sure, but evolutionary biologists are rife with theories about why this and the rare other cases of programmed die-offs in the animal kingdom may make some evolutionary sense. What is known, however, is the proximal mechanism underlying the sudden die-off. Not how come they die in terms of evolutionary patterns over the millennia, but how come they die in the sense of which parts of the body's functioning suddenly go crazy? It is glucocorticoid secretion. If you catch salmon right after they spawn, just when they are looking a little green around the gills, you find they have huge adrenal glands, peptic ulcers, and kidney lesions. Their immune systems have collapsed, and they are teeming with parasites and infections. Aha! Kind of sounds like Cellier's rats way back when. Moreover, the salmon have stupendously high glucocorticoid concentrations in their bloodstreams. When salmon spawn, regulation of their glucocorticoid secretion breaks down. Basically, the brain loses its ability to measure accurately the quantities of circulating hormones and keeps sending a signal to the adrenals to secrete more of them. Lots of glucocorticoids can certainly bring about all those diseases with which the salmon are festering. But is the glucocorticoid excess really responsible for their death? Yep. Take a salmon right after spawning, remove its adrenals, and it will live for a year afterward. The bizarre thing is that this sequence of events not only occurs in 5 species of salmon, but also among a dozen species of Australian marsupial mice. All the male mice of these species die shortly after seasonal mating. Cut out their adrenal glands, however, and they too keep living. Pacific salmon and marsupial mice are not close relatives. At least twice in evolutionary history, completely independently, 2 very different sets of species have come up with the identical trick. If you want to degenerate very fast, secrete a ton of glucocorticoids. Chronic stress and the aging process in the mainstream. That is all fine for the salmon looking for the fountain of youth, but we and most other mammals age gradually over time, not in catastrophic die-offs over the course of days. Does stress influence the rate of gradual mammalian aging? Intuitively, the idea that stress accelerates the aging process makes sense. We recognize that there is a connection between how we live and how we die. Around 1900, a madly inspired German physiologist, Max Rubner, tried to define this connection scientifically. He looked at all sorts of different domestic species and calculated things like lifetime number of heartbeats and lifetime metabolic rate. Not the sort of study that many scientists have tried to replicate. He concluded that there is only so long a body can go on, only so many breaths, so many heartbeats, so much metabolism that each pound of flesh can carry out, before the mechanisms of life wear out. A rat with approximately 400 heartbeats a minute uses up its heartbeat allotment faster, after approximately 2 years, than an elephant with approximately 35 beats per minute and a 60-year lifespan. Such calculations lay behind ideas about why some species lived far longer than others. Soon, the same sort of thinking was applied to how long different individuals within a species live. If you squander a lot of your heartbeats being nervous about blind dates when you're 16, there would be that much less metabolic reserve available to you at 80. In general, Rubner's ideas about lifespans among different species have not held up well in their strictest versions, while the rate of living hypotheses about individuals within a species that his ideas have inspired have been even less tenable. Nevertheless, they led many people in the field to suggest that a lot of environmental perturbations can wear out the system prematurely. Such wear and tear thinking fit in naturally with the stress concept. As we have seen, excessive stress increases the risks of adult-onset diabetes, hypertension, cardiovascular disease, osteoporosis, reproductive decline, and immune suppression. All of these conditions become more common as we age. Moreover, in Chapter 4, it was shown that if you have a lot of the indices of allostatic load, it increases your risk of metabolic syndrome. That same study showed that it increased your mortality risk as well. We return to the tendency of very old rats, humans, and primates to have elevated resting levels of glucocorticoids in the bloodstream. Some aspect of the regulation of normal glucocorticoid secretion is disrupted during aging. To get a sense of why this happens, we must return to Chapter 1's interest about why the water tank on your toilet does not overflow when it's refilling. Once again, the process of refilling can trigger a sensor, the flotation device, to decrease the amount of water flowing into the tank. Engineers who study this sort of thing term that process negative feedback inhibition, or end product inhibition. Increasing amounts of water accumulating in the tank decrease the likelihood of further release of water. Most hormonal systems, including the CRH-ACTH glucocorticoid axis, work by this feedback inhibition process. The brain triggers glucocorticoid release indirectly via CRH and pituitary release of ACTH. The brain needs to know whether to keep secreting more CRH. It does this by sensing the levels of glucocorticoids in the circulation, sampling the hormone from the bloodstream coursing through the brain, to see if levels are at, below, or above a set point. If levels are low, the brain keeps secreting CRH, just as when water levels in the toilet tank are still low. Once glucocorticoid levels reach or exceed that set point, there is a negative feedback signal, and the brain stops secreting CRH. As a fascinating complication, the set point can shift. In the absence of stress, the brain wants different levels of glucocorticoids in the bloodstream from those required when something stressful is happening. This implies that the quantity of glucocorticoids in the bloodstream necessary to turn off CRH secretion by the brain should vary with different situations, which turns out to be the case. This is how the system works normally, as can be shown experimentally by injecting a person with a massive dose of a synthetic glucocorticoid, dexamethasone. The brain senses the sudden increase and says, in effect, "My God, I don't know what is going on with those idiots in the adrenal, but they just secreted way too many glucocorticoids." The dexamethasone exerts a negative feedback signal, and soon the person has stopped secreting CRH, ACTH, and her own glucocorticoids. This person would be characterized as dexamethasone responsive. If negative feedback regulation is not working very well, however, the person is dexamethasone resistant. She keeps secreting the various hormones, despite the whopping glucocorticoid signal in the bloodstream. And that is precisely what happens in old people, old non-human primates, and old rats. Glucocorticoid feedback regulation no longer works very well. This may explain why very old organisms secrete excessive glucocorticoids, in the absence of stress and during the recovery period after the end of a stressor. Why the failure of feedback regulation? There is a fair amount of evidence that it is due to the degeneration during aging of one part of the brain. The entire brain does not serve as a glucocorticoid sensor. Instead, that role is served by only a few areas with very high numbers of receptors for glucocorticoids, and the means to tell the hypothalamus whether or not to secrete CRH. In Chapter 10, I described how the hippocampus is famed for its role in learning and memory. As it turns out, it is also one of the important negative feedback sites in the brain for controlling glucocorticoid secretion. It also turns out that during aging, hippocampal neurons may become dysfunctional. When this occurs, some of the deleterious consequences include a tendency to secrete an excessive amount of glucocorticoids. This could be the reason aged people may have elevated resting levels of the hormone, may have trouble turning off secretion after the end of stress, or may be dexamethasone resistant. It is as if one of the brakes on the system has been damaged, and hormone secretion rushes forward, a little out of control. The elevated glucocorticoid levels of old age, therefore, arise because of a problem with feedback regulation in the damaged hippocampus. Why are neurons damaged in the aging hippocampus? It's glucocorticoid exposure, as was discussed in Chapter 10. If you've listened carefully, you will begin to note something truly insidious embedded in these findings. When the hippocampus is damaged, the rat secretes more glucocorticoids, which should damage the hippocampus further, which should cause even more glucocorticoid secretion. Each makes the other worse, causing a degenerative cascade that appears to occur in many aging rats, and whose potential pathological consequences have been detailed throughout virtually every sentence of this book. Does this degenerative cascade occur in humans? As noted, glucocorticoid levels rise with extreme old age in the human, and Chapter 10 outlines the first evidence that these hormones might have some bad effects on the human hippocampus. The primate and human hippocampus appear to be negative feedback regulators of glucocorticoid release, such that hippocampal damage is associated with glucocorticoid excess, just as in the rodent. So the pieces of the cascade appear to be there in the human, raising the possibilities that histories of severe stress or of heavy use of synthetic glucocorticoids to treat some disease might accelerate aspects of this cascade. Does that mean that all is lost? That this sort of dysfunction is an obligatory part of aging? Certainly not. It was not by chance that 2 paragraphs prior I described this cascade as occurring in many aging rats, rather than in all. Some rats age successfully in a way that spares them this cascade, as do many humans. These pleasing stories are part of the final chapter of this book. It is thus not yet clear whether the glucocorticoid neurotoxicity story applies to how our brains age. Unfortunately, the answer is not likely to be available for years. The subject is difficult to study in humans. Nevertheless, from what we know about this process in the rat and monkey, glucocorticoid toxicity stands as a striking example of ways in which stress can accelerate aging. Should it turn out to apply to us as well, it will be an aspect of our aging that will harbor a special threat. If we are crippled by an accident, if we lose our sight or hearing, if we are so weakened by heart disease as to be bedbound, we cease having so many of the things that make our lives worth living. But when it is our brains that are damaged, when it is our ability to recall old memories or to form new ones that is destroyed, we fear we'll cease to exist as sentient, unique individuals, the version of aging that haunts us most. Even the most stoic of listeners should be pretty frazzled by now, given the detailing in the 12 chapters so far about the sheer number of things that can go wrong with stress. It is time to shift to the second half of the book, which examines stress management, coping, and individual differences in the stress response. It is time to begin to get some good news. Chapter 13. Why is psychological stress stressful? Some people are born to biology. You can spot them instantly as kids. They're the ones comfortably lugging around the toy microscopes, dissecting some dead animal on the dining room table, being ostracized at school for their obsession with geckos. But all sorts of folks migrate to biology from other fields: chemists, psychologists, physicists, mathematicians. Several decades after stress physiology began, the discipline was inundated by people who had spent their formative years as engineers. Like physiologists, they thought there was a ferocious logic to how the body worked. But for bioengineers, that tended to mean viewing the body a bit like the circuitry diagram that you get with a radio. Input-output ratios, impedance, feedback loops, servo mechanisms. I shudder even to write such words, as I barely understand them. But the bioengineers did wonders for the field, adding a tremendous vigor. Suppose you wonder how the brain knows when to stop glucocorticoid secretion, when enough is enough. In a vague sort of way, everyone knew that somehow the brain must be able to measure the amount of glucocorticoids in the circulation, compare that to some desired set point, and then decide whether to continue secreting CRH or turn off the faucet, returning to the toilet tank model. The bioengineers came in and showed that the process was vastly more interesting and complicated than anyone had imagined. There are multiple feedback domains. Some of the time, the brain measures the quantity of glucocorticoids in the bloodstream, and sometimes the rate at which the level is changing. The bioengineers solved another critical issue. Is the stress response linear or all or nothing? Epinephrine, glucocorticoids, prolactin, and other substances are all secreted during stress, but are they secreted to the same extent regardless of the intensity of the stressor? All or nothing responsiveness. The system turns out to be incredibly sensitive to the size of the stressor, demonstrating a linear relationship between, for example, the extent of the drop in blood pressure and the extent of epinephrine secretion, between the degree of hypoglycemia, drop in blood sugar, and glucagon release. The body not only can sense something stressful, but it also is amazingly accurate at measuring just how far and how fast that stressor is throwing the body out of allostatic balance. Beautiful stuff, and important. Hans Selye loved the bioengineers, which makes perfect sense, since in his time the whole stress field must have still seemed a bit soft-headed to some mainstream physiologists. Those physiologists knew that the body does one set of things when it is too cold, and a diametrically opposite set when it is too hot. But here was Selye and his crew insisting that there were physiological mechanisms that respond equally to cold and hot, and to injury, and hypoglycemia, and hypotension. The beleaguered stress experts welcomed the bioengineers with open arms. You see, it's for real. You can do math about stress, construct flow charts, feedback loops, formulas. Golden days for the business. If the system was turning out to be far more complicated than ever anticipated, it was complicated in a way that was precise, logical, and mechanistic. Soon it would be possible to model the body as one big input-output relationship. You tell me exactly to what degree a stressor impinges on an organism, how much it disrupts the allostasis of blood sugar, fluid volume, optimal temperature, and so on, and I'll tell you exactly how much of a stress response will occur. This approach, fine for most of the ground that we've covered up until now, will probably allow us to estimate quite accurately what the pancreas of that zebra is doing when the organism is sprinting from a lion. But the approach is not going to tell us which of us will get an ulcer when the factory closes down. Starting in the late 1950s, a new style of experiments in stress physiology began to be conducted that burst that lucid mechanistic bioengineering bubble. A single example will suffice. An organism is subjected to a painful stimulus, and you are interested in how great a stress response will be triggered. The bioengineers had been all over that one, mapping the relationship between the intensity and duration of the stimulus and the response. But this time, when the painful stimulus occurs, the organism under study can reach out for its mommy and cry in her arms. Under these circumstances, this organism shows less of a stress response. Nothing in that clean mechanistic world of the bioengineers could explain this phenomenon. The input was still the same. The same number of pain receptors should have been firing while the child underwent some painful procedure. Yet the output was completely different. A critical realization roared through the research community. The physiological stress response can be modulated by psychological factors. Two identical stressors with the same extent of allostatic disruption can be perceived, can be appraised differently, and the whole show changes from there. Suddenly, the stress response could be made bigger or smaller, depending on psychological factors. In other words, psychological variables could modulate the stress response. Inevitably, the next step was demonstrated. In the absence of any change in physiological reality, any actual disruption of allostasis, psychological variables alone could trigger the stress response. Flushed with excitement, Yale physiologist John Mason, one of the leaders in this approach, even went so far as to proclaim that all stress responses were psychological stress responses. The old guard was not amused. Just when the conception of stress was becoming systematized, rigorous, credible, along came this rabble of psychologists muddying up the picture. In a series of published exchanges in which they first praised each other's achievements and ancestors, Selye and Mason attempted to shred each other's work. Mason smugly pointed to the growing literature on psychological initiation and modulation of the stress response. Selye, facing defeat, insisted that all stress responses couldn't be psychological and perceptual. If an organism is anesthetized, it still gets a stress response when a surgical incision is made. The psychologists succeeded in getting a place at the table, and as they have acquired some table manners and a few gray hairs, they have been treated less like barbarians. We now have to consider which psychological variables are critical. Why is psychological stress stressful? The building blocks of psychological stressors. Outlets for frustration. You would expect key psychological variables to be mushy concepts to uncover, but in a series of elegant experiments, the physiologist J. Weiss, then at Rockefeller University, demonstrated exactly what is involved. The subject of one experiment is a rat that receives mild electric shocks, roughly equivalent to the static shock you might get from scuffing your foot on a carpet. Over a series of these, the rat develops a prolonged stress response. Its heart rate and glucocorticoid secretion rate go up, for example. For convenience, we can express the long-term consequences by how likely the rat is to get an ulcer, and in this situation the probability soars. In the next room, a different rat gets the same series of shocks, identical pattern and intensity. Its allostatic balance is challenged to exactly the same extent. But this time, whenever the rat gets a shock, it can run over to a bar of wood and gnaw on it. The rat in this situation is far less likely to get an ulcer. You have given it an outlet for frustration. Other types of outlets work as well. Let the stressed rat eat something, drink water, or sprint on a running wheel, and it is less likely to develop an ulcer. We humans also deal better with stressors when we have outlets for frustration. Punch a wall, take a run, find solace in a hobby. We are even cerebral enough to imagine those outlets and derive some relief. Consider the prisoner of war who spends hours imagining a golf game in tremendous detail. I have a friend who passed a prolonged and very stressful illness, lying in bed with a mechanical pencil and a notepad, drawing topographic maps of imaginary mountain ranges, and taking hikes through them. A central feature of an outlet being effective is that it distracts from the stressor. But obviously, more important is that it also be something positive for you. A reminder that there is more to life than whatever is making you crazed and stressed at the time. The frustration-reducing effects of exercise provide an additional layer of benefit, one harking back to my dichotomy repeated ad nauseum, between the zebra running for its life and the psychologically stressed human. The stress response is about preparing your body for an explosive burst of energy consumption right now. Psychological stress is about doing all the same things to your body for no physical reason whatsoever. Exercise finally provides your body for the outlet that it was preparing for. A variant of Weiss's experiment uncovers a special treatment of the outlet for frustration reaction. This time, when the rat gets the identical series of electric shocks and is upset, it can run across the cage, sit next to another rat, and bite the hell out of it. Stress-induced displacement of aggression. The practice works wonders at minimizing the stressfulness of a stressor. It's a real primate specialty as well. A male baboon loses a fight. Frustrated, he spins around and attacks a subordinate male who is minding his own business. An extremely high percentage of primate aggression represents frustration displaced onto innocent bystanders. Humans are pretty good at it too. And we have a technical way of describing the phenomenon in the context of stress-related disease. He's one of those guys who doesn't get ulcers. He gives them. Taking it out on someone else. How well it works at minimizing the impact of a stressor. Social support. An additional way we can interact with another organism to minimize the impact of a stressor on us is considerably more encouraging for the future of our planet than is displacement aggression. Rats only occasionally use it, but primates are great at it. Put a primate through something unpleasant, it gets a stress response. Put it through the same stressor while in a room full of other primates, and it depends. If those primates are strangers, the stress response gets worse. But if they are friends, the stress response is decreased. Social support networks. It helps to have a shoulder to cry on, a hand to hold, an ear to listen to you, someone to cradle you and to tell you it will be okay. The same is seen with primates in the wild. While I mostly do laboratory research on how stress and glucocorticoids affect the brain, I spend my summers in Kenya studying patterns of stress-related psychology and disease among wild baboons living in a national park. The social life of a male baboon can be pretty stressful. You get beaten up as a victim of displaced aggression. You carefully search for some tuber to eat and clean it off, only to have it stolen by someone of higher rank, and so on. Glucocorticoid levels are elevated among low-ranking baboons and among the entire group if the dominance hierarchy is unstable, or if a new aggressive male has just joined the troop. But if you are a male baboon with a lot of friends, you are likely to have lower glucocorticoid concentrations than males of the same general rank who lack these outlets. And what counts as friends? You play with kids, have frequent non-sexual grooming bouts with females, and social grooming in non-human primates lowers blood pressure. Social support is certainly protective for humans as well. This can be demonstrated even in transient instances of support. In a number of subtle studies, subjects were exposed to a stressor, such as having to give a public speech, or perform a mental arithmetic task, or having two strangers argue with them, with or without a supportive friend present. In each case, social support translated into less of a cardiovascular stress response. Profound and persistent differences in degrees of social support can influence human physiology as well. Within the same family, there are significantly higher glucocorticoid levels among stepchildren than among biological children. Or as another example, among women with metastatic breast cancer, the more social support, the lower the resting cortisol levels. As noted in Chapter 8, people with spouses or close friends have longer life expectancies. When the spouse dies, the risk of dying rises. Recall also from that chapter the study of parents of Israeli soldiers killed in the Lebanon War. In the aftermath of this stressor, there was no notable increase in risk of diseases or mortality, except among those who were already divorced or widowed. Some additional examples concern the cardiovascular system. People who are socially isolated have overly active sympathetic nervous systems. Given the likelihood that this will lead to higher blood pressure and more platelet aggregation in their blood vessels, remember that from Chapter 3? They are more likely to have heart disease, 2 to 5 times as likely, it turns out. And once they have the heart disease, they are more likely to die at a younger age. In a study of patients with severe coronary heart disease, Redford Williams of Duke University and colleagues found that half of those lacking social support were dead within 5 years, a rate 3 times higher than was seen in patients who had a spouse or close friend, after controlling for the severity of the heart disease. Finally, support can exist at the broad community level. Stay tuned for Chapter 17. If you are a member of an ethnic minority, the fewer members there are of your group in your neighborhood, the higher your risks of mental illness, psychiatric hospitalization, and suicide. Predictability. Weiss's rat studies uncovered another variable modulating the stress response. The rat gets the same pattern of electric shocks, but this time, just before each shock, it hears a warning bell. fewer ulcers. Predictability makes stressors less stressful. The rat with the warning gets two pieces of information. It learns when something dreadful is about to happen. The rest of the time, it learns that something dreadful is not about to happen. It can relax. The rat without a warning can always be a half-second away from the next shock. In effect, information that increases predictability tells you that there is bad news, but comforts you that it's not going to be worse. You are going to get shocked soon, but it's never going to be sprung on you without warning. We all know a human equivalent of this principle. You're in the dentist's chair. No Novocaine. The dentist drilling away. 10 seconds of nerve-curling pain. Some rinsing. 5 seconds of drilling. A pause while the dentist fumbles a bit. 15 seconds of drilling, and so on. In one of the pauses, frazzled and trying not to whimper, you gasp, "Almost done?" "Hard to say," the dentist mumbles, returning to the intermittent drilling. Think how grateful we are for the dentist who instead says, "2 more and we're done." The instant the second burst of drilling ends, down goes blood pressure. By being given news about the stressor to come, you are also implicitly being comforted by now knowing what stressors are not coming. As another variant on the helpfulness of predictability, organisms will eventually habitate to a stressor if it is applied over and over. It may knock physiological allostasis equally out of balance the umpteenth time that it happens, but it is a familiar, predictable stressor by then, and a smaller stress response is triggered. One classic demonstration involved men in the Norwegian military going through parachute training. As the process went from being hair-raisingly novel to something they could do in their sleep, their anticipatory stress response went from being gargantuan to non-existent. The power of loss of predictability as a psychological stressor is shown in an elegant, subtle study. A rat is going about its business in its cage, and at measured intervals the experimenter delivers a piece of food down a chute into the cage. Rat eats happily. This is called an intermittent reinforcement schedule. Now, change the pattern of food delivery so that the rat gets exactly the same total amount of food over the course of an hour, but at a random rate. The rat receives just as much reward, but less predictably, and up go glucocorticoid levels. There is not a single physically stressful thing going on in the rat's world. It's not hungry, pained, running for its life. Nothing is out of allostatic balance. In the absence of any stressor, loss of predictability triggers a stress response. There are even circumstances in which a stress response can be more likely to occur in someone despite the reality that the outside world is less stressful. Work by the zoologist John Wingfield of the University of Washington has shown an example of this with wild birds. Consider some species that migrates between the Arctic and the tropics. Bird number 1 is in the Arctic, where the temperature averages 5 degrees and where it is, indeed, 5 degrees outside that day. In contrast, bird number 2 is in the tropics, where the average temperature is 80 degrees, but today it has dropped down to 60. Who has the bigger stress response? Amazingly, bird number 2. The point isn't that the temperature in the tropics is 55 degrees warmer than in the Arctic. What kind of stressor would that be? It's that the temperature in the tropics is 20 degrees colder than anticipated. A human version of the same idea has been documented. During the onset of the Nazi blitzkrieg bombings of England, London was hit every night like clockwork. Lots of stress. In the suburbs, the bombings were far more sporadic, occurring perhaps once a week. Fewer stressors, but much less predictability. There was a significant increase in the incidence of ulcers during that time. Who developed more ulcers? The suburban population. As another measure of the importance of unpredictability, by the 3rd month of the bombing, ulcer rates in all the hospitals had dropped back to normal. Despite the similarity between the responses of humans and of other animals to a lack of predictability, I suspect that they are not identical and in an important way. The warning of impending shocks to a rat has little effect on the size of the stress response during the shocks. Instead, allowing the rat to feel more confident about when it doesn't have to worry reduces the rat's anticipatory stress response the rest of the time. Analogously, when the dentist says, "Only 2 more times and then we're done," it allows us to relax at the end of the second burst of drilling. But I suggest, although I cannot prove it, that unlike the case for the rat, proper information will also lower our stress response during the pain. If you were told only 2 times more versus only 10 times more, wouldn't you use different mental strategies to try to cope? With either scenario, you would pull out the comforting thought of, "Only 1 more and then it's the last one," at different times. You would save your most distracting fantasy for a different point. You would try counting to 0 from different numbers. Predictive information lets us know what internal coping strategy is likely to work best during a stressor. We often wish for information about the course of some medical problem because it aids our strategizing about how we will cope. A simple example. You have some minor surgery, and you're given predictive information. The first post-surgical day there is going to be a lot of pain, pretty constant, whereas by the second day you'll just feel a bit achy. Armed with that information, you are more likely to plan on watching the 8 distracting videos on day 1 and to devote day 2 to writing delicate haikus than the other way around. Among other reasons, we wish to optimize our coping strategies when we request the most devastating piece of medical information any of us will ever face. How much time do I have left? Control. Rat studies also demonstrate a related facet of psychological stress. Give the rat the same series of shocks. This time, however, you study a rat that has been trained to press a lever to avoid electric shocks. Take away the lever, shock it, and the rat develops a massive stress response. It's as if the rat were thinking, "I can't believe this. I know what to do about electric shocks. Give me a damned lever and I could handle this. This isn't fair." Ulceration City, as well as higher glucocorticoid levels, poorer immune function, and faster tumor growth. Give the trained rat a lever to press, even if it is disconnected from the shock mechanism. It still helps. Down goes the stress response. So long as the rat has been exposed to a higher rate of shocks previously, it will think that the lower rate now is due to its having control over the situation. This is an extraordinarily powerful variable in modulating the stress response. The identical style of experiment with humans yields similar results. Place 2 people in adjoining rooms and expose both to intermittent, noxious, loud noises. The person who has a button and believes that pressing it decreases the likelihood of more noise is less hypertensive. In one variant on this experiment, subjects with the button who did not bother to press it did just as well as those who actually pressed the button. Thus, the exercise of control is not critical. Rather, it is the belief that you have it. An everyday example: airplanes are safer than cars, yet more of us are phobic about flying. Why? Because your average driver believes that he is a better than average driver, thus more in control. In an airplane, we have no control at all. My wife and I tease each other on plane flights, exchanging control. "Okay, you rest for a while. I'll take over concentrating on keeping the pilot from having a stroke." The issue of control runs through the literature on the psychology of stress. As will be discussed in the final chapter on coping, exercise can be a great stress reducer, but only so long as it is something that seems even remotely desirable. Amazingly, the same is seen in a rat. Let a rat run voluntarily in a running wheel, and it makes it feel great. Force a rat to do the same amount of exercise, and it gets a massive stress response. The issue of control runs through the extensive literature on occupational stress. Sure, there are some jobs where stress comes in the form of someone having too much control and responsibility. That rare occupation where, over the course of an average workday, you might find yourself having to direct the landing pattern of an array of circling jumbo jets at the local airport, personally excise someone's cerebral aneurysm, and make the final decision as to whether taffeta is going to be in at the fall runway show in Milan. For most, though, Occupational stress is built more around lack of control, work life spent as a piece of the machine. Endless studies have shown that the link between occupational stress and increased risk of cardiovascular and metabolic diseases is anchored in the killer combination of high demand and low control. You have to work hard, a lot is expected of you, and you have minimal control over the process. This is the epitome of the assembly line, the combination of stressors that makes for Marx's alienation of the workers. The control element is more powerful than the demand one. Low demand and low control is more damaging to one's health than high demand and high control. The stressfulness of lack of control on the job applies in only certain domains, however. For example, there is the issue of what product is made, and lack of control in this realm tends not to be all that stressful. Few people are ulcerating because of their deep conviction that all of their capable and motivated fellow workers should be cranking vast numbers of stuffed Snoopies out of this factory instead of ball bearings. Instead, it is stress about lack of control over the process, what work rate is expected and how much flexibility there is about it, what amenities there are and how much control you have over them, how authoritarian the authorities are. These issues can apply just as readily to some less expected workplaces, ones that can be highly prestigious and desirable. For example, professional musicians in orchestras generally have lower job satisfaction and more stress than those in small chamber groups, such as a string quartet. Why? One pair of researchers suggest that this is because of the lack of autonomy in an orchestra, where centuries of tradition hold that orchestras are subservient to the dictatorial whims of the maestro conducting them. For example, it was only in recent years that orchestra unions won the right for regularly scheduled bathroom breaks during rehearsals, instead of having to wait until the conductor cared to note how squirmy the reed players had become. So the variable of control is extremely important. Controlling the rewards that you get can be more desirable than getting them for nothing. As an extraordinary example, both pigeons and rats prefer to press a lever in order to obtain food, so long as the task is not too difficult, over having the food delivered freely, a theme found in the activities and statements of many scions of great fortunes, who regret the contingency-free nature of their lives, without purpose or striving. Loss of control and lack of predictive information are closely related. Some researchers have emphasized this, pointing out that the common theme is that the organism is subjected to novelty. You thought you knew how to manage things. You thought you knew what would happen next. And it turns out you are wrong in this novel situation. The potency of this is demonstrated in primate studies, in which merely placing the animal into a novel cage suppresses its immune system. Others have emphasized that these types of stressors cause arousal and vigilance, as you search for the new rules of control and prediction. Both views are different aspects of the same issue. A perception of things worsening. Yet another critical psychological variable in the stress response has been uncovered. A hypothetical example. 2 rats get a series of electric shocks. On the first day, one gets 10 shocks an hour, the other 50. Next day, both get 25 shocks an hour. Who becomes hypertensive? Obviously the one going from 10 to 25. The other rat is thinking, 25? Piece of cheese. No problem, I can handle that. Given the same degree of disruption of allostasis, a perception that events are improving helps tremendously. The principle pops up in the realm of human illness. Recall in Chapter 9 the scenario where pain is less stressful, can even be welcome when it means, for example, that the drugs are working. The tumor is shrinking. One classic study demonstrated that in examining parents of children who had a 25% chance of dying of cancer. Astonishingly, these parents showed only a moderate rise in glucocorticoid levels in the bloodstream. How could that be? Because the children were all in remission after a period in which the odds of death had been far higher. 25% must have seemed like a miracle. 25 shocks an hour. a certain degree of social instability, a 1 in 4 chance of your child dying. Each can imply either good news or bad, and only the latter seems to stimulate a stress response. It's not just the external reality, it's the meaning you attach to it. A version of this can be observed among the baboons I study in Kenya. In general, when dominance hierarchies are unstable, resting glucocorticoid levels rise. This makes sense because such instabilities make for stressful times. Looking at individual baboons, however, shows a more subtle pattern. Given the same degree of instability, males whose ranks are dropping have elevated glucocorticoid levels, while males whose ranks are rising amid the tumult don't show this endocrine trait. Not so fast. Thus, some powerful psychological factors can trigger a stress response on their own, or make another stressor seem more stressful. Loss of control or predictability, loss of outlets for frustration or sources of support, a perception that things are getting worse. There are obviously some overlaps in the meaning of these different factors. As we saw, control and predictability are closely aligned. Combine them with a perception of things worsening, and you have the situation of bad things happening, out of your control, and utterly unpredictable. The primatologist Joan Silk of UCLA has emphasized how, among primates, a great way to maintain dominance is for the alpha individual to mete out aggression in a randomly brutal way. This is our primate essence of terrorism. Sometimes these different variables conflict, and it becomes a question as to which is more powerful. This often involves a dichotomy between control predictability issues and the perception of whether things are improving or worsening. For example, someone unexpectedly wins the lottery big time. Is this a stressor? It depends on what is more powerful, the beneficial perception of things getting better part, or the stressful lack of predictability part. Not surprisingly, if the lottery win is big enough, most people's psyches can handle some unpredictability. Nonetheless, some non-human primate studies in which rank was manipulated by the experimenters show that it can go in the other way, that if the change is sufficiently unexpected, it can be stressful, even if it is good change. And psychotherapy often must delve into the reasons why people sometimes find change for the good to be less desirable than persisting with a known misery. Conversely, if a situation is sufficiently awful, the fact that it may have been predictable offers little comfort. These factors play a major role in explaining how we all go through lives full of stressors, yet differ so dramatically in our vulnerability to them. The final chapter of this book examines the bases of these individual differences in greater detail. This will serve as a blueprint for analyzing how to learn to exploit these psychological variables, how, in effect, to manage stress better. The ways in which these different psychological variables can interact brings up a key point, one that will dominate the final chapter. This is that stress management cannot consist merely of the simple-minded solution of maximize control, maximize predictability, maximize outlets for frustration. As we will now see, it is considerably more complicated than that. As the most obvious first pass at this, some lack of control and predictability can be a great thing. A good roller coaster ride, a superbly terrifying movie, a mystery novel with a great surprise ending, winning a lottery, being subject to a random act of kindness. And sometimes an overabundance of predictability is a disaster. Boredom on the job. The right amounts of loss of control and predictability are what we call stimulation. In Chapter 16, we will look at the biology of why stimulation makes us happy rather than stressed. The goal is never to generate lives in which there is never a challenge to allostasis, and the remainder of this chapter considers when increasing a sense of control and predictability reduces stress. Some subtleties of predictability. We have already seen how predictability can ameliorate the consequences of stress. One rat gets a series of shocks and develops a higher risk for an ulcer than the rat who gets warnings beforehand. Predictability doesn't always help, however. The experimental literature on this is pretty dense. Some human examples of this point make it more accessible. Remember, in these scenarios, the stressor is inevitable. The warning cannot change the stressor, just the perception of it. How predictable is the stressor in the absence of a warning? What if one morning an omnipotent voice says, "There is no way out of it. A meteor is going to crush your car while you're at work today. But it's the only time it will happen this year." Not soothing. There's the good news that it's not going to happen again tomorrow, but that's hardly comforting. This is not an event that you anxiously fret over often. At the other extreme, what if one morning an omnipotent voice whispers, "Today it's going to be stressful on the freeway. Lots of traffic, stops and goes. Tomorrow, too. In fact, every day this year except November 9th, when there'll hardly be any traffic. People will wave to each other, and a highway patrol cop will stop you in order to share his coffee cake with you." Who needs predictive information about the obvious fact that driving to work is going to be stressful? Thus, warnings are less effective for very rare stressors. You don't usually worry much about meteors, and very frequent ones. They approach being predictable even without the warning. How far in advance of the stressor does the warning come? Each day, you go for a mysterious appointment. You are led into a room with your eyes closed and are seated in a deep, comfortable chair. Then, with roughly even probabilities but no warning, either a rich, avuncular voice reads you to sleep with your favorite childhood stories, or a bucket of ice water is sloshed over your head. Not a pleasing prospect, I would bet. Would the whole thing be any less unsettling if you were told which treatment you were going to get 5 seconds before the event? Probably not. There is not enough time to derive any psychological benefits from the information. At the other extreme, how about predictive information long in the future? Would you wish for an omnipotent voice to tell you, 11 years and 27 days from now, your ice water bath will last 10 full minutes? Information either just before or long before the stressor does little good to alleviate the psychological anticipation. Some types of predictive information can even increase the cumulative anticipatory stressor. For example, if the stressor is truly terrible. Would you be comforted by the omnipotent message, "Tomorrow, an unavoidable accident will mangle your left leg, although your right leg will remain in great shape"? Likewise, predictive information can make things worse if the information is vague. As I write this section, we continue to be stressed by the maddening vagueness of predictive information in our post-9/11 world, when we are given warnings that read like horoscopes from hell. Orange alert. We don't know what the threat is, but be extra alert about everything for the next few days. Collectively, these scenarios tell us that predictability does not always work to protect us from stress. The much more systematic studies with animals suggest that it works only in a mid-range of frequencies and intensities of stressors, and with certain lag times and levels of accurate information. Subtleties of control. To understand some important subtleties of the effects of control on stress, we need to return to the paradigm of the rat being shocked. It had previously trained to press a lever to avoid shocks, and now it's pounding away like crazy on a lever. The lever does nothing. The rat is still getting shocked, but with less chance of an ulcer because the rat thinks it has control. To introduce a sense of control into the experimental design decreases the stress response, because in effect the rat is thinking, 10 shocks an hour, not bad. Just imagine how bad it would be if I wasn't on top of it with my lever here. But what if things backfire, and adding a sense of control makes the rat think, 10 shocks an hour, what's wrong with me? I have a lever here. I should have avoided the shocks. It's my fault. If you believe you have control over stressors that are in fact beyond your control, you may consider it somehow to be your fault that the inevitable occurred. An inappropriate sense of control in the face of awful events can make us feel terrible. Some of our most compassionate words to people experiencing tragedy involve minimizing their perceived sense of control. It's not your fault. No one could have stopped in time. She just darted out from between the cars. It's not something you could have done anything about. You tried your best. The economy's just lousy now. Honey, getting him the best doctor in the world couldn't have cured him. And some of the most brutally callous of society's attempts to shift blame attribute more personal control during a stressor than exists. She was asking for it if she was going to dress that way. Rape victims have the control to prevent the rape. Your child's schizophrenia was caused by your mothering style. This was a destructive belief that dominated psychiatry for decades, before the disease was recognized to be neurochemical. If they'd only made the effort to assimilate, they wouldn't have these problems. Minorities have the power to prevent their persecution. The effects of the sense of control on stress are highly dependent on context. In general, if the stressor is of a sort where it is easy to imagine how much worse it could have been, inserting an artificial sense of control helps. That was awful, but think of how bad it would have been if I hadn't done X. But when the stressor is truly awful, an artificial sense of control is damaging. It is difficult to conceive a yet worse scenario that you managed to avoid, but easy to be appalled by the disaster you didn't prevent. You don't want to feel as if you could have controlled the uncontrollable when the outcome is awful. People with a strong internal locus of control, in other words, people who think they are the masters of their own ship, that what goes on around them reflects their actions, have far greater stress responses than do those with external loci when confronted with something uncontrollable. This is a particular risk for the elderly, especially elderly men, as life generates more and more things beyond their control. As we will see in the final chapter, there is even a personality type whose tendency to internalize control in the face of bad, uncontrollable things greatly increases the risk of a particular disease. These subtleties about control and predictability help to explain a confusing feature about the studies of stress. In general, the less control or predictability, the more at risk you are for a stress-induced disease. Yet, an experiment conducted by Joseph Brady in 1958 with monkeys gave rise to the view that more control and more predictability cause ulcers. Half the animals could press a bar to delay shocks, executive monkeys. The other half were passively yoked to one of the executives, such that they received a shock whenever the first one did. In this widely reported study, the executive monkeys were more likely to develop ulcers. Out of these studies came the popular concept of the executive stress syndrome and associated images of executive humans weighed down with the stressful burdens of control, leadership, and responsibility. Ben Natelson of the VA Medical Center in East Orange, New Jersey, along with Jay Weiss, noted some problems with that study. First, it was conducted with parameters where control and predictability are bad news. Second, the executive and non-executive monkeys were not chosen randomly. Instead, the monkeys that tended to press the bar first in pilot studies were selected to be executives. Monkeys that press sooner have since been shown to be more emotionally reactive animals. So Brady was inadvertently stacking the executive side with the more reactive, ulcer-prone monkeys. In general, executives of all species are more likely to be giving ulcers than to be getting them, as we will see in Chapter 17. To summarize, stress responses can be modulated or even caused by psychological factors, including loss of outlets for frustration and of social support, a perception of things worsening, and, under some circumstances, a loss of control and of predictability. These ideas have vastly expanded our ability to answer the question, why do only some of us get stress-related diseases? Obviously, we differ as to the number of stressors that befall us. After all the chapters on physiology, you can guess that we differ in how fast our adrenals make glucocorticoids, how many insulin receptors we have in our fat cells, the thickness of our stomach walls, and so on. But in addition to those physiological differences, we can now add another dimension. We differ in the psychological filters through which we perceive the stressors in our world. Two people participating in the same event, a long wait at the supermarket checkout, public speaking, parachuting out of an airplane, may differ dramatically in their psychological perception of the event. Oh, I'll just read a magazine while I wait. Outlet for frustration. I'm nervous as hell, but by giving this after-dinner talk, I'm a shoo-in for that promotion. Things are getting better. This is great. I've always wanted to try skydiving. This is something I'm in control of. In the next 2 chapters, we will consider psychiatric disorders such as depression and anxiety, and personality disorders, in which there's a bad match between how stressful the real world is and how stressful the person perceives it to be. As we'll see, the mismatch between the two can take a variety of forms, but the thing in common is the fact that a potentially considerable price is paid by the sufferer. Following that, in Chapter 16, we consider what psychological stress has to do with the process of addiction. Following that is a chapter examining how your place in society, and the type of society it is, can have profound effects on stress physiology and patterns of disease. In the final chapter, we will examine how stress management techniques can aid us by teaching how to exploit these psychological defenses. Chapter 14. Stress and Depression. We are morbidly fascinated with the exotica of disease. They fill our made-for-television movies, our tabloids, and the book reports of adolescents hoping to become doctors someday. Victorians with the elephant man's disease, murderers with multiple personality disorders, 10-year-olds with progeria, idiot savants with autism, cannibals with kuru. Who could resist? But when it comes to the bread and butter of human misery, try a major depression. It can be life-threatening, it can destroy lives, demolish the families of sufferers. And it is dizzyingly common. The psychologist Martin Seligman has called it the common cold of psychopathology. Best estimates are that from 5 to 20% of us will suffer a major, incapacitating depression at some point in our lives, causing us to be hospitalized or medicated or non-functional for a significant length of time. Its incidence has been steadily decreasing for decades. By the year 2020, depression is projected to be the second leading cause of medical disability on Earth. This chapter differs a bit from those that preceded it, in which the concept of stress was at the forefront. Initially, that may not seem to be the case in our focus on depression. The two appear to be inextricably linked, however, and the concept of stress will run through every section of this chapter. It is impossible to understand either the biology or psychology of major depressions without recognizing the critical role played in the disease by stress. To begin to understand this connection, it is necessary to get some sense of the disorder's characteristics. We have first to wrestle with a semantic problem. Depression is a term that we all use in an everyday sense. Something mildly or fairly upsetting happens to us and we get the blues for a while, followed by recovery. This is not what occurs in a major depression. One issue is chronicity. For a major depression to be occurring, the symptoms have to have persisted for at least 2 weeks. The other is severity. This is a vastly crippling disorder that leads people to attempt suicide. Its victims may lose their jobs, family, and all social contact because they cannot force themselves to get out of bed or refuse to go to a psychiatrist because they feel they don't deserve to get better. It is a horrific disease, and throughout this chapter I will be referring to this major, devastating form of depression, rather than the transient blues that we may casually signify with the term feeling depressed. The symptoms. The defining feature of a major depression is a loss of pleasure. If I had to define a major depression in a single sentence, I would define it as a genetic neurochemical disorder requiring a strong environmental trigger whose characteristic manifestation is an inability to appreciate sunsets. Depression can be as tragic as cancer or a spinal cord injury. Think about what our lives are about. None of us will live forever, and on occasion we actually believe it. Our days are filled with disappointments, failures, unrequited loves, Despite this, almost inconceivably, we not only cope, but even feel vast pleasures. I, for example, am resoundingly mediocre at soccer, but nothing keeps me from my twice-weekly game. Invariably, there comes a moment when I manage to gum up someone more adept than I. I'm panting and heaving and pleased, and there's still plenty more time to play, and a breeze blows, and I suddenly feel dizzy with gratitude for my animal existence. What could be more tragic than a disease that, as its defining symptom, robs us of that capacity? The trait is called anhedonia. Hedonism is the pursuit of pleasure. Anhedonia is the inability to feel pleasure, also often called dysphoria. I'll be using the terms interchangeably. Anhedonia is consistent among depressives. A woman has just received the long-sought promotion. A man has just become engaged to the woman of his dreams. And amid their depression, they will tell you how they feel nothing, how it really doesn't count, how they don't deserve it. Friendship, achievement, sex, food, humor, none can bring any pleasure. This is the classic picture of depression, and some recent research, much of it built around work of the psychologist Alex Zautra of the University of Arizona, shows that the story is more complex. Specifically, positive and negative emotions are not mere opposites. If you take subjects and, at random times throughout the day, have them record how they are feeling at that moment, the frequencies of feeling good and feeling bad are not inversely correlated. There's normally not much of a connection between how much your life is filled with strongly positive emotions and how much with strongly negative ones. Depression represents a state where those two independent axes tend toward collapsing into one inverse relationship. Too few positive emotions and too many negative ones. Naturally, the inverse correlation isn't perfect, and a lot of current research focuses on questions like, are different subtypes of depression characterized more by the absence of positive emotions or the overabundance of negatives? Accompanying major depression are great grief and great guilt. We often feel grief and guilt in the everyday sadnesses that we refer to as depression, but in a major depression, they can be incapacitating, as the person is overwhelmed with the despair. There can be complex layers of these feelings, not just obsessive guilt, for example, about something that has contributed to the depression, but obsessive guilt about the depression itself, what it has done to the sufferer's family, the guilt of not being able to overcome depression, a life lived but once and wasted amid this disease. Small wonder that worldwide depression accounts for 800,000 suicides per year. In a subset of such patients, the sense of grief and guilt can take on the quality of a delusion. By this, I do not mean the thought-disordered delusions of schizophrenics. Instead, delusional thinking in depressives is the sort where facts are distorted, over or underinterpreted to the point where one must conclude that things are terrible and getting worse, hopeless. An example: a middle-aged man, out of the blue, has a major heart attack. Overwhelmed by his implied mortality, the transformation of his life, he slips into a major depression. Despite this, he is recovering from the attack reasonably well, and there is every chance that he will resume a normal life. But each day, he's sure he's getting worse. The hospital in which he is staying is circular in construction, with a corridor that forms a loop. One day, the nurses walk him once around the hospital before he collapses back in bed. The next day, he does 2 laps. He is getting stronger. That evening, when his family visits, he explains to them that he is sinking. What are you talking about? The nurses said that you did 2 loops today. Yesterday you only did 1. No. He shakes his head sadly. You don't understand. He explains that the hospital is being renovated and, well, last night they closed off the old corridor and opened a newer, smaller one. And, you see, the distance around the new loop is less than half the distance of the old one. So 2 laps today is still less than I could do yesterday. This particular incident occurred with the father of a friend, an engineer who lucidly described radii and circumferences, expecting his family to believe that the hospital had opened up a new corridor through the core of the building in one day. This is delusional thinking. The emotional energies behind the analysis and evaluation are disordered, so that the everyday world is interpreted in a way that leads to depressive conclusions. It's awful, getting worse, and this is what I deserve. Cognitive therapists like Aaron Beck of the University of Pennsylvania even consider depression to be primarily a disorder of thought rather than emotion, in that sufferers tend to see the world in a distorted negative way. Beck and colleagues have conducted striking studies that provide evidence for this. For example, they might show a subject two pictures. In the first, a group of people are gathered happily around a dinner table feasting. In the second, the same people are gathered around a coffin. Show the two pictures rapidly or simultaneously. Which one is remembered? Depressives see the funeral scene at rates higher than chance. They are not only depressed about something, but see the goings-on around them in a distorted way that always reinforces that feeling. Their glasses are always half empty. Another frequent feature of a major depression is called psychomotor retardation. The person moves and speaks slowly. Everything requires tremendous effort and concentration. She finds the act of merely arranging a doctor's appointment exhausting. Soon it is too much even to get out of bed and get dressed. It should be noted that not all depressives show psychomotor retardation. Some may show the opposite pattern, termed psychomotor agitation. The psychomotor retardation accounts for one of the important clinical features of depression, which is that severely, profoundly depressed people rarely attempt suicide. It's not until they begin to feel a bit better. If the psychomotor aspects make it too much for this person to get out of bed, they sure aren't going to find the often considerable energy needed to kill themselves. A key point. Many of us tend to think of depressives as people who get the same everyday blahs as you and I, but that for them it just spirals out of control. We may also have the sense, whispered out of earshot, that these are people who just can't handle normal ups and downs, who are indulging themselves. Why can't they just get themselves together? A major depression, however, is as real a disease as diabetes. Another set of depressive symptoms supports that view. Basically, many things in the bodies of depressives work peculiarly. These are called vegetative symptoms. You and I get an everyday depression. What do? Typically, we sleep more than usual, probably eat more than usual, convinced in some way that such comforts will make us feel better. These traits are just the opposite of the vegetative symptoms seen in most people with major depressions. Eating declines, sleeping does as well, and in a distinctive manner. While depressives don't necessarily have trouble falling asleep, they have the problem of early morning wakening, spending months on end sleepless and exhausted from 3:30 or so each morning. Not only is sleep shortened, but as mentioned in Chapter 11, the architecture of sleep is different as well. The normal pattern of shifting between deep and shallow sleep, the rhythm of the onset of dream states are disturbed. An additional vegetative symptom is extremely relevant to this chapter, namely that major depressives often experience elevated levels of glucocorticoids. This is critical for a number of reasons that will be returned to, and helps to clarify what the disease is actually about. When looking at a depressive sitting on the edge of the bed, barely able to move, it is easy to think of the person as energyless, enervated. A more accurate picture is of the depressive as a tightly coiled spool of wire, tense, straining, active, but all inside. As we will see, a psychodynamic view of depression shows the person fighting an enormous aggressive mental battle. No wonder they have elevated levels of stress hormones. Chapter 10 reviewed how glucocorticoids can impair aspects of memory that depend on the hippocampus, and the frequently elevated glucocorticoid levels in depression may help explain another feature of the disease, which is problems with hippocampal-dependent memory. The memory problems may reflect in part a lack of motivation on the part of the depressed person. Why work hard on some shrink's memory test when everything is hopeless and pointless? Or an anhedonic inability to respond to the rewards of remembering something in a task. Nonetheless, amid those additional factors, The pure process of storing and retrieving memories via the hippocampus is often impaired. As we'll see shortly, this fits extraordinarily well with recent findings, showing that the hippocampus is smaller than average in many depressives. Another feature of depression also confirms that it is a real disease, rather than merely the situation of someone who simply cannot handle everyday ups and downs. There are multiple types of depressions, and they can look quite different. In one variant, unipolar depression, the sufferer fluctuates from feeling extremely depressed to feeling reasonably normal. In another form, the person fluctuates between deep depression and wild, disorganized hyperactivity. This is called bipolar depression, or more familiarly, manic depression. Here we run into another complication, because just as we use depression in an everyday sense that is different from the medical sense, mania has an everyday connotation as well. We may use the term to refer to madness, as in made-for-television homicidal maniacs. Or we could describe someone as being in a manic state when he is buoyed by some unexpected good news, talking quickly, laughing, gesticulating. But the mania found in manic depression is of a completely different magnitude. Let me give an example of the disorder. A woman comes into the emergency room. She's bipolar, completely manic, hasn't been taking her medication. She's on welfare, doesn't have a cent to her name, and in the last week she's bought 3 Cadillacs with money from loan sharks. And get this, she doesn't even know how to drive. People in manic states will go for days on 3 hours of sleep a night and feel rested, will talk non-stop for hours at a time, will be vastly distractible, unable to concentrate amid their racing thoughts. In outbursts of irrational grandiosity, they will behave in ways that are foolhardy or dangerous to themselves and others. At the extreme, poisoning themselves in attempting to prove their immortality, burning down their homes, giving away their life savings to strangers. It is a profoundly destructive disease. The strikingly different subtypes of depression and their variability suggest not just a single disease, but a heterogeneity of diseases that have different underlying biologies. Another feature of the disorder also indicates a biological abnormality. Suppose a patient comes to a doctor in the tropics. The patient is running a high fever that abates, only to come back a day or two later, abate again, return again, and so on every 48 to 72 hours. The doctors will recognize this instantly as malaria, because of the rhythmicity of the disorder. It has to do with the life cycle of the malarial parasite as it moves from red blood cells to the liver and spleen. The rhythmicity screams biology. In the same way, certain subtypes of depression have a rhythm. A manic depressive may be manic for 5 days, severely depressed for the following week, then mildly depressed for half a week or so, and finally symptom-free for a few weeks. Then the pattern starts up again, and may have been doing so for a decade. Good things and bad things happen, but the same cyclic rhythm continues, which suggests just as much deterministic biology as in the life cycle of the malarial parasite. In another subset of depression, the rhythm is annual, where sufferers get depressed during the winter. These are called seasonal affective disorders, or SADS. Affective is the psychiatric term for emotional responses, and are thought to be related to patterns of exposure to light. Recent work has uncovered a class of retinal cells that respond to light intensity, and surprisingly, send their information directly into the limbic system, the emotional part of the brain. Again, the rhythmicity appears independent of external life events. A biological clock is ticking away in there that has something to do with mood, and something is seriously wrong with its ticking. The biology of depression. Neurochemistry and depression. Considerable evidence exists that something is awry with the chemistry of the brain of depressives. In order to appreciate that, it is necessary to learn a bit about how brain cells communicate with one another. Figure 15 on your PDF companion shows a schematic version of 2 neurons, the principal type of brain cell. If a neuron has become excited with some thought or memory, Metaphorically speaking, its excitement is electrical. A wave of electricity sweeps from the dendrites over the cell body, down the axon to the axon terminals. When the wave of electrical excitation reaches the axon terminal, it releases chemical messengers that float across the synapse. These messengers, neurotransmitters, bind to specialized receptors on the adjacent dendrite, causing the second neuron to become electrically excited. A minor piece of housekeeping, however. What happens to the neurotransmitter molecule after it has done its job and floats off the receptor? In some cases, it is recycled, taken back up by the axon terminal of the first neuron and repackaged for future use. Or it can be degraded in the synapse and the debris flushed out to sea, the cerebrospinal fluid, then to the blood, and then the urine. If these processes of clearing neurotransmitters out of the way fail, reuptake ceases or degradation stops, or both, suddenly a lot more neurotransmitter remains in the synapse, giving a stronger signal to the second neuron than usual. Thus, the proper disposal of these powerful messengers is integral to normal neuronal communication. There are trillions of synapses in the brain. Do we need trillions of chemically unique neurotransmitters? Certainly not. You can generate a seemingly infinite number of messages with a finite number of messengers. Consider how many words we can form with the mere 26 letters in our alphabet. All you need are rules that allow for the same messenger to convey different meanings, metaphorically speaking, in different contexts. At one synapse, neurotransmitter A sends a message relevant to pancreatic regulation, while at another synapse, the same neurotransmitter substance may pertain to adolescent crushes. There are many neurotransmitters, probably on the order of a few hundred, but certainly not trillions. So that's a primer on how neurons talk to each other with neurotransmitters. The best evidence suggests that depression involves abnormal levels of the neurotransmitters norepinephrine, serotonin, and dopamine. Before reviewing the evidence, it's important to clear up a point. You are no doubt thinking, wasn't there something about norepinephrine and the sympathetic nervous system many chapters ago? Absolutely. And that proves the point about the varied roles played by any given neurotransmitter. In one part of the body, the heart for example, norepinephrine is a messenger concerning arousal and the 4 F's, while in a different part of the nervous system, norepinephrine seems to have something to do with the symptoms of depression. Why is it likely that there is something wrong with norepinephrine, serotonin, or dopamine in depression? The best evidence is that most of the drugs that lessen depression increase the amount of signaling by these neurotransmitters. One class of antidepressants, called tricyclics, a reference to their biochemical structure, stops the recycling or reuptake of these neurotransmitters into the axon terminals. The result is that the neurotransmitter remains in the synapse longer and is likely to hit its respective receptor a second or third time. Another class of drugs, called MAO inhibitors, blocks the degradation of these neurotransmitters in the synapse by inhibiting the action of a crucial enzyme in that degradation, monoamine oxidase, or MAO. The result, again, is that more of the messenger remains in the synapse to stimulate the dendrite of the receiving neuron. These findings generate a pretty straightforward conclusion. If you use a drug that increases the amount of norepinephrine, serotonin, and dopamine in synapses throughout the brain, and as a result someone's depression gets better, there must have been too little of those neurotransmitters in the first place. Case closed. Naturally, not so fast. As a first issue of confusion is the problem with serotonin, dopamine, or norepinephrine. The tricyclics and MAO inhibitors work on all 3 neurotransmitter systems, making it impossible to tell which one is critical to the disease. People used to think norepinephrine was the culprit, when it was thought that those classical antidepressant drugs worked only on the norepinephrine synapse. These days, most of the excitement centers on serotonin, mainly because of the efficacy of reuptake inhibitors that work only on serotonin synapses, selective serotonin reuptake inhibitors, or SSRIs, of which Prozac is the most famous. However, There still remains some reason to think that the other two neurotransmitters remain part of the story, since some of the newest antidepressants appear to work on them more than on serotonin. A second piece of confusion is actually quite major. Is the defect in depression with these neurotransmitters really one of too little neurotransmitter in the synapse? You would think this was settled. The effective antidepressant drugs increase the amounts of these neurotransmitters in the synapse and alleviate depression. Thus, the problem had to be too little of the stuff to begin with. However, some clinical data suggest that this might not be so simple. The stumbling block has to do with timing. Expose the brain to some tricyclic antidepressant, and the amount of signaling with these neurotransmitters in the synapses change within hours. However, give that same drug to a depressed person, and it takes weeks for the person to feel better. Something doesn't quite fit. Two theories have arisen in recent years that might reconcile this problem with timing, and they are both extremely complicated. Revisionist Theory 1. The "it's not too little neurotransmitter, it's actually too much" hypothesis. First, some orientation. If somebody constantly yells at you, you stop listening. Analogously, if you inundate a cell with lots of a neurotransmitter, the cell will not listen as carefully. It will down-regulate, decrease the number of receptors for that neurotransmitter in order to decrease its sensitivity to that messenger. If, for example, you double the amount of serotonin reaching the dendrites of a cell, and that cell down-regulates its serotonin receptors by 50%, the changes roughly cancel out. If the cell down-regulates less than 50%, the net result is more serotonin signaling in the synapse. If more than 50%, the result is actually less signaling in the synapse. In other words, how strong the signal is in a synapse is a function both of how loudly the first neuron yells, the amount of neurotransmitter released, and of how sensitively the second neuron listens, how many receptors it has for the neurotransmitter. Okay, ready. This revisionist theory states that the original problem is that there is actually too much norepinephrine, serotonin, and/or dopamine in parts of the brains of depressives. What happens when you prescribe antidepressants that increase signaling of these neurotransmitters even further? At first, that should make the depressive symptoms worse. Some psychiatrists argue that this actually does occur. Over the course of a few weeks, however, the dendrites say, "This is intolerable, all this neurotransmitter. Let's downregulate our receptors a whole lot." If this occurs, and critical to the theory, more than compensates for the increased neurotransmitter signal, the depressive problem of excessive neurotransmitter signaling goes away. The person feels better. Revisionist Theory 2. It really is too little norepinephrine, serotonin, and/or dopamine after all. This theory is even more complicated than the first, and also requires orientation. Not only do dendrites contain receptors for neurotransmitters, but it turns out that on the axon terminals of the sending neuron as well, there are receptors for the very neurotransmitters being released by that neuron. What possible purpose could these so-called autoreceptors serve? Neurotransmitters are released, float into the synapse, bind to the standard receptors on the second neuron. Some neurotransmitter molecules, however, will float back and wind up binding to the autoreceptors. They serve as some sort of feedback signal. If, say, 5% of the released neurotransmitter reaches the autoreceptors, the first neuron can count its toes, multiply by 20, and figure out how much neurotransmitter it has released. Then it can make some decisions. Should I release more neurotransmitter or stop now? Should I start synthesizing more? And so on. If this process lets the first neuron do its bookkeeping on neurotransmitter expenditures, what happens if the neuron downregulates a lot of these autoreceptors? Underestimating the amount of neurotransmitter it has released, the neuron will inadvertently start increasing the amount it synthesizes and discharges. With this as background, here's the reasoning behind the second theory. that there really is too little norepinephrine, serotonin, or dopamine in a part of the brain of depressives. Give the antidepressant drugs that increase signaling of these neurotransmitters. Because of the increased signaling, over the course of weeks there will be downregulation of norepinephrine, serotonin, and dopamine receptors. Critical to this theory is the idea that the autoreceptors on the first neuron will downregulate to a greater extent than the receptors on the second neuron. If that happens, the second neuron may not be listening as well, but the first one will be releasing sufficient extra neurotransmitter to more than overcome that. The net result is enhanced neurotransmitter signaling, and depressive symptoms abate. This mechanism may explain the efficacy of electroconvulsive therapy, ECT or shock therapy. For decades, psychiatrists have used this technique to alleviate major depressions, and no one has quite known why it works. It turns out that among its many effects, ECT decreases the number of norepinephrine autoreceptors, at least in experimental animal models. If you are confused by now, you are in some good company, as the entire field is extremely unsettled. Norepinephrine, serotonin, or dopamine. Too much or too little signaling. If it is, for example, too little serotonin signaling, is it because too little serotonin is being released into synapses, or because there is some defect blunting the sensitivity of serotonin receptors? To give you a sense of how big a can of worms that one is, there are currently recognized more than a dozen different types of serotonin receptors, with differing functions, efficacies, and distributions in the brain. Maybe there are a variety of different neurochemical routes for getting to a depression, and different pathways are associated with different subtypes of depression. Unipolar versus manic depression, or one that is triggered by outside events versus one that runs with its own internal clockwork, or one dominated by psychomotor retardation versus one dominated by suicidalism. This is a very reasonable idea, but the evidence for it is still scant. Amid all those questions, another good one. Why does having too much or too little of these neurotransmitters cause a depression? There are a lot of links between these neurotransmitters and function. For example, serotonin is thought to have something to do with incessant ideation in depression, the uncontrollable wallowing in those dark thoughts. Connected with this, SSRIs are often effective on people with obsessive-compulsive disorder. There is a commonality here. In the depressive case, it is the obsessive sense of failure, of doom, of despair, while in the latter case, it can be obsessive worries that you left the gas on at home when you left, that your hands are dirty and need to be washed, and so on, trapped in a mind that just circles and circles around the same thoughts or feelings. Norepinephrine is thought to play a different role in the symptoms of depression. The major pathway that utilizes norepinephrine is an array of projections from a brain region called the locus ceruleus. That projection extends diffusely throughout the brain and seems to play a role in alerting other brain regions, increasing their baseline level of activation, lowering their threshold for responding to outside signals. Thus, a shortage of norepinephrine in this pathway might begin to explain the psychomotor retardation. Dopamine, meanwhile, has something to do with pleasure, a connection that will be reviewed at length in Chapter 16. Several decades ago, some neuroscientists made a fundamental discovery. They had implanted electrodes into the brains of rats and stimulated areas here and there, seeing what would happen. By doing so, they found an extraordinary area of the brain. Whenever this area was stimulated, the rat became unbelievably happy. So how can one tell when a rat is unbelievably happy? You ask the rat to tell you, by charting how many times it is willing to press a lever in order to be rewarded with stimulation in that part of the brain. It turns out that rats will work themselves to death on that lever to get stimulation. They would rather be stimulated there than get food when they are starving, or have sex, or receive drugs even when they're addicted and going through withdrawal. The region of the brain targeted in these studies was promptly called the pleasure pathway, and has been famous since. That humans have a pleasure pathway was discovered shortly afterward by stimulating a similar part of the human brain during neurosurgery. The results are pretty amazing. Something along the lines of, "Ah, boy, that feels good." It's kind of like getting your back rubbed, but also sort of like sex. Or playing in the backyard in the leaves when you're a kid and Mom calling you in for hot chocolate and then you get into your pajamas with the feet. Where can we sign up? This pleasure pathway seems to make heavy use of dopamine as a neurotransmitter. And in Chapter 16, we'll see how dopamine signals the anticipation of reward more than it signals reward itself. The strongest evidence for this is the ability of drugs that mimic dopamine, such as cocaine, to act as euphoriants. Suddenly, it seems plausible to hypothesize that depression, which is characterized above all by dysphoria, might involve too little dopamine, and thus dysfunction of those pleasure pathways. Thus, these are the big three when it comes to the neurotransmitters implicated in depression, with attention these days probably being the most for serotonin and the least for dopamine. All of the leading antidepressant drugs, the SSRIs and older classes such as tricyclics or MAO inhibitors, work by altering the levels of one or more of these three neurotransmitters. At this point, there is nothing close to resembling a science as to which sort of person will respond best to which type of antidepressants. Naturally, there's a spate of other neurotransmitters that may be involved. One particularly interesting one is called substance P. Decades of work have shown that substance P plays a role in pain perception, with a major role in activating the spinal cord pathways discussed in Chapter 9. Remarkably, some recent studies indicate that drugs that block the action of substance P can work as antidepressants in some individuals. What's this about? Perhaps the sense of depression as a disease of psychic pain may be more than just a metaphor. Neuroanatomy and depression. Figure 16 on your PDF companion is an illustration of what the brain looks like, to consider a second way in which brain function might be abnormal in depressives, in addition to the neurochemistry discussed. One region regulates processes like your breathing and heart rate. It includes the hypothalamus, which is busy releasing hormones and instructing the autonomic nervous system. If your blood pressure drops drastically, causing a compensatory stress response, it is the hypothalamus, midbrain, and hindbrain that kick into gear. All sorts of vertebrates have roughly the same connections here. Layered on top of that is a region called the limbic system, the functioning of which is related to emotion. As mammals, we have large limbic systems. Lizards have relatively tiny limbic systems. They are not noted for the complexity of their emotional lives. If you get a stress response from smelling the odor of a threatening rival, it's your limbic system that is involved. Above that is the cortex. Everyone in the animal kingdom has some, but it is a real primate specialty. The cortex does abstract cognition, invents philosophy, remembers where your car keys are. The stuff of the previous chapter. Now think for a second. Suppose you are gored by an elephant. You may feel a certain absence of pleasure afterward, maybe a sense of grief. Throw in a little psychomotor retardation. You're not as eager for your calisthenics as usual. Sleeping and feeding may be disrupted. Glucocorticoid levels may be a bit on the high side. Sex may lose its appeal for a while. Hobbies are not as enticing. You don't jump up to go out with friends. You pass up that all-you-can-eat buffet. Sound like some of the symptoms of a depression? Now, what happens during a depression? You think a thought about your mortality or that of a loved one. You imagine children in refugee camps, the rainforests disappearing, and endless species of life evaporating. Late Beethoven string quartets. And suddenly you experience some of the same symptoms as after being gored by the elephant. On an incredibly simplistic level, you can think of depression as occurring when your cortex thinks an abstract negative thought and manages to convince the rest of the brain that this is as real as a physical stressor. In this view, People with chronic depressions are those whose cortex habitually whispers sad thoughts to the rest of the brain. Thus, an astonishingly crude prediction. Cut the connections between the cortex and the rest of a depressive's brain, and the cortex will no longer be able to get the rest of the brain depressed. Remarkably, it actually works sometimes. Neurosurgeons may perform this procedure on people with vastly crippling depressions that are resistant to drugs, ECT, or other forms of therapy. Afterward, depressive symptoms seem to abate. Obviously, this is a simplified picture. No one actually disconnects the entire cortex from the rest of the brain. After all, the cortex does more than mope around feeling bad about the final chapter of Mice and Men. The surgical procedure, called a cingulotomy, or a cingulum bundle cut, actually disconnects just one area toward the front of the cortex, called the anterior cingulate cortex, ACC. The ACC is turning out to have all the characteristics of a brain region you'd want to take offline in a major depression. It's a part of the brain that is very concerned with emotions. Show people arrays of pictures. In one case, ask them to pay attention to the emotions being expressed by people in the pictures. In another case, ask them to pay attention to details like whether these are indoor or outdoor photographs. In only the former case do you get activation of the ACC. And the emotions that the ACC is involved in seem to be negative ones. Induce a positive state in someone by showing something amusing, and ACC metabolism decreases. In contrast, if you electrically stimulate the ACC in people, they feel a shapeless sense of fear and foreboding. Moreover, neurons in the ACC, including in humans, respond to pain of all sorts. But the ACC response isn't really about the pain. It more concerns feelings about the pain. As was discussed in Chapter 9, give someone a hypnotic suggestion that they will not feel the pain of dipping their hand into ice water. The primary parts of the brain that get pain projections from the spinal cord get just as active as if there were no hypnotic suggestion. But this time, the ACC doesn't activate. In addition, the ACC and adjacent brain regions activate when you show widows pictures of their lost loved ones versus pictures of strangers. As another example of this, put a volunteer in a brain imaging machine and, from inside, ask them to play some game with two other people via a computer console. Rig up the flow of the game so that over time, the other two, actually a computer program, gradually begin just playing with each other, excluding the test subject. Neuronal activity in the ACC lights up, and the more left out the person feels, the more intensely the ACC activates. How do you know this has something to do with that dread junior high school feeling of being picked last for the team? Because of a clever control in the study. Set the person up to play with the supposed other two players. Once again, it winds up that the other two only play against each other. The difference this time, though, is that early on, the subject is told there's been a technical glitch and that their computer console isn't working. Excluded because of a snafu in the technology, there's no ACC activation. Given these functions of the ACC, it is not surprising that its resting level of activity tends to be elevated in people with a depression. This is the fear and pain and foreboding churning away at those neurons. Interestingly, another part of the brain, called the amygdala, seems to be hyperactive in depressives as well. We will hear lots about the role of the amygdala in fear and anxiety in the next chapter. However, in depressives, the amygdala seems to have been recruited into a different role. Show a depressed person a fearful human face, and his amygdala doesn't activate all that much, in contrast to the response you'd see in the amygdala of a control subject. But show him a sad face, and the amygdala gets a highly exaggerated activation. Sitting just in front of the ACC is the frontal cortex, which, as we saw in Chapter 11, is one of the most distinctly human parts of the brain. Work by Richard Davidson of the University of Wisconsin has shown that one subregion called the prefrontal cortex, PFC, seems highly responsive to mood and in a lateralized way. Specifically, Activation of the left PFC is associated with positive moods, and activation of the right PFC with negative. For example, induce a positive state in someone by asking him to describe the happiest day of his life, and the left PFC lights up in proportion to the person's subjective assessment of his pleasure. Ask him to remember a sad event, and the right PFC dominates. Similarly, separate an infant monkey from its mother, and right PFC metabolism rises while left PFC decreases. Thus, not surprisingly, in depressives, there is decreased left PFC activity and elevated activity in the right PFC. There are a few other anatomical changes in the brain in depression, but to make sense of those, we have to consider what hormones have to do with the disease. Genetics and depression. It is hard to look at the biology of anything these days without genes coming into the picture, and depression is no exception. Depression has a genetic component. As a first observation, depression runs in families. For a long time, that would have been sufficient evidence for some folks that there is a genetic link. But this conclusion is undone by the obvious fact that not only do genes run in families, environment does as well. Growing up in a poor family, an abusive family, a persecuted family, can all increase the risk of depression running through that family without genes having anything to do with it. So we look for a tighter relationship. The more closely related two individuals are, the more genes they share in common, and as it turns out, the more likely they are to share a depressive trait. As one of the most telling examples of this, take any two siblings who are not identical twins. They share something like 50% of their genes. If one of them has a history of depression, the other has about a 25% likelihood, considerably higher than would be expected by chance. Now compare two identical twins who share all of their genes in common, and if one of them is depressive, the other has a 50% chance. This is quite impressive. The more genes in common, the more likelihood of sharing the disease. But there remains a confound. The more genes people share within a family, the more environment they share as well, starting with the fact that identical twins grow up treated more similarly than our non-identical twins. Tighten the relationship further. Look at children who were adopted at an early age. Consider those whose biological mother had a history of depression, but whose adoptive mother did not. They have an increased risk of depression, suggesting a genetic legacy shared with their biological mother. But the confound there, as we saw in Chapter 6, is that environment does not begin at birth, but begins much earlier, within the circulatory environment shared in utero with one's biological mother. For any card-carrying molecular biologist in the 21st century, if you want to prove that genes have something to do with depression, you're going to have to identify the specific genes, the specific stretches of DNA that code for specific proteins that increase the risk for depression. As we'll see shortly, precisely that has occurred in recent years. Immunology and depression. This subsection did not exist in previous editions of this book. Immunity is about fighting off pathogens. Depression is about feeling sad. Unrelated subjects. Well, they can be related, but in an idiotically obvious way. Like, duh, being sick can be depressing. But it's more complicated than that. Chronic illness that involves overactivation of the immune system, for example, chronic infections, or an autoimmune disease where the immune system has accidentally activated and is attacking some part of your body, is more likely to cause depression than other equally severe and prolonged illnesses that don't involve the immune system. Some more threads of interconnection involve the cytokines that act as messengers between immune cells. As you'll recall from Chapter 8, cytokines can also get into the brain, where they can stimulate CRH release. More recently, it's becoming clear that they also interact with norepinephrine, dopamine, and serotonin systems. Critically, cytokines can cause depression. This is shown in animal models of depression. Furthermore, certain types of cancers are sometimes treated with cytokines to enhance immune function, and this typically results in depression. So this represents a new branch of study for biological psychiatry, the interactions between immune function and mood. Endocrinology and depression. Abnormal levels of a number of different hormones often go hand in hand with depression. To begin, people who secrete too little thyroid hormone can develop major depressions, and when depressed, can be atypically resistant to antidepressant drugs working. This is particularly important because many people, seemingly with depressions of a purely psychiatric nature, turn out to have thyroid disease. There is another aspect of depression in which hormones may play a role. The incidence of major unipolar depression differs greatly, with women suffering far more than men. Even when you consider manic depression, where there is no sex difference in its incidence, bipolar women have more depressive episodes than do bipolar men. Why this female bias? It has nothing to do with the obvious first guess, which is that women are more likely to see a health professional for depression than are men. The difference holds up even when such reporting biases are controlled for. One theory, from the school of cognitive therapy, concentrates on the ways in which women and men tend to think differently. When something upsetting happens, women are more likely to ruminate over it, think about it, or want to talk about it with someone else. And men, terrible communicators that they so often are more likely to want to think about anything but the problem. Or even better, go and do something. Exercise, use power tools, get drunk, start a war. A ruminative tendency, the cognitive psychologists argue, makes you more likely to become depressed. Another theory about the sex difference is psychosocial in nature. As we will see, much theorizing about the psychology of depression suggests that it is a disorder of lack of power and control, and some scientists have speculated that because women in so many societies traditionally have less control over the circumstances of their lives than do men, they are at greater risk for depression. In support of this idea, some psychiatrists have produced data suggesting that the elevated rates of depression in women decline to the levels seen in men, in some traditional societies in which women don't have a subordinate role. Yet another theory suggests that men really do have as high a rate of depression as do women, but they are simply more likely to mask it with substance abuse. All of these ideas are reasonable, although they run into trouble when one considers that women and men, as noted, have the same rate of bipolar depression. It is only unipolar depression that is more common among women. These theories seem particularly weak in their failure to explain a major feature of female depressions, namely, that women are particularly at risk for depressions at certain reproductive points: menstruation, menopause, and most of all, the weeks immediately after giving birth. A number of researchers believe such increased risks are tied to the great fluctuations that occur during menstruation, menopause, and parturition in two main hormones, estrogen and progesterone. As evidence, they cite the fact that women can get depressed when they artificially change their estrogen or progesterone levels, for example when taking birth control pills. Critically, both of these hormones can regulate neurochemical events in the brain, including the metabolism of neurotransmitters such as norepinephrine and serotonin. With massive changes in hormone levels, 1,000-fold for progesterone at the time of giving birth, for example, current speculation centers on the possibility that the ratio of estrogen to progesterone can change radically enough to trigger a major depression. This is a new area of research, with some seemingly contradictory findings, but there is more and more confidence among scientists that there is a hormonal contribution to the preponderance of female depressions. Obviously, the next subject in a section on hormones and depression will have to look at glucocorticoids. But given how central this is to the whole venture of this book, the subject requires expansion. How does stress interact with the biology of depression? Stress, glucocorticoids, and the onset of depression. The first stress-depression link is an obvious one, in that stress and depression tend to go together. This can run in two directions. First, studies of what is called stress generation among depressives look at the fact that people who are prone to depression tend to experience stressors at a higher than expected rate. This is even seen when comparing them to individuals with other psychiatric disorders or health problems. Much of this appears to be stressors built around lack of social support. This raises the potential for a vicious cycle to emerge. This is because if you interpret the ambiguous social interactions around you as signs of rejection and respond as if you have been rejected, it can increase the chances of winding up socially isolated, thereby confirming your sense that you have been rejected. But the major way in which people think about a link between stress and depression, and the one that concerns us here, has causality running in the other direction. Specifically, people who are undergoing a lot of life stressors are more likely than average to succumb to a major depression, and people sunk in their first major depression are more likely than average to have undergone recent and significant stress. Obviously, not everyone who undergoes major stressors sinks into depression, and what those individual differences are about should be clearer as we proceed through this chapter. As noted, some people have the grave misfortune of suffering from repeated depressive episodes, one that can take on a rhythmic pattern stretching over years. When considering the case histories of those people, stressors emerge as triggers for only the first few depressions. In other words, have 2-3 major bouts of depression, and statistically you are no more at risk for subsequent major depression than anyone else. But somewhere around the fourth depression or so, a mad clockwork takes over, and the depressive waves crash, regardless of whether the outside world pummels you with stressors. What that transition is about will be considered shortly. Laboratory studies also link stress and the symptoms of depression. Stress a lab rat, and it becomes anhedonic. Specifically, it takes a stronger electrical current than normal in the rat's pleasure pathways to activate a sense of pleasure. The threshold for perceiving pleasure has been raised, just as in a depressive. Critically, glucocorticoids can do the same. A key point in Chapter 10 was how glucocorticoids and stress could disrupt memory. Part of the evidence for that came from people with Cushing's syndrome. As a reminder, that is a condition in which any of a number of different types of tumors wind up causing vast excesses of glucocorticoids in the bloodstream, as well as from people prescribed high doses of glucocorticoids to treat a number of ailments. It has also been known for decades that a significant subset of Cushingoid patients and patients prescribed synthetic glucocorticoids become clinically depressed, independent of memory problems. This has been tricky to demonstrate. First, when someone is initially treated with synthetic glucocorticoids, the tendency is to get, if anything, euphoric and even manic, perhaps for a week or so before the depression kicks in. You can immediately guess that we are dealing with one of our dichotomies between short and long-term stress physiology. Chapter 16 will explore in even more detail where that transient euphoria comes from. As a second complication, does someone with Cushing's syndrome or someone taking high pharmacological doses of synthetic glucocorticoids get depressed because glucocorticoids cause that state? Or is it because they recognize they have a depressing disease? You show it is the glucocorticoids that are the culprits by demonstrating higher depression rates in this population than among people with, for example, the same disease and the same severity, but not receiving glucocorticoids. At this stage, there's also not much of a predictive science to this phenomenon. For example, no clinician can reliably predict beforehand which patient is going to get depressed when put on high-dose glucocorticoids, let alone at what dose, and whether it is when the dose is raised or lowered to that level. Nonetheless, have lots of glucocorticoids in the bloodstream, and the risk of a depression increases. Stress and glucocorticoids tangle up with biology in predisposing a person toward depression in an additional critical way. Back to that business about there being a genetic component to depression. Does this mean that if you have the gene or genes for depression, that's it, you're up the creek, it's inevitable? Obviously not. And the best evidence for this is that factoid about identical twins. One has depression, and the other, sharing all the same genes, has about a 50% chance of having the disease as well, a much higher rate than in the general population. There, pretty solid evidence for genes being involved. But flip this the other way. Share every single gene with someone who is depressive, and you still have a 50% chance of not having the disease. Genes are rarely about inevitability, especially when it comes to humans, the brain, or behavior. They're about vulnerability, propensities, tendencies. In this case, genes increase the risk of depression only in certain environments. You guessed it, only in stressful environments. This is shown in a number of ways, but most dramatically in a recent study by Avshalom Caspi at King's College London. Scientists identified a certain gene in humans that increases the risk of depression. More specifically, it is a gene that comes in a few different allelic versions, a few different types or flavors that differ slightly in function. Have one of those versions and you're at increased risk. What that gene is, I'm not telling yet. I'm saving it for the end of this chapter, as it is a doozy. But the key thing is that having version X of this gene Z doesn't guarantee you get depression. It just increases your risk. And in fact, knowing nothing more about someone than which version of gene Z she has doesn't increase your odds of predicting whether she gets depressed. Version X increases depression risk only when coupled with a history of repeated major stressors. Amazingly, the same has been shown with studies of some non-human primate species who carry a close equivalent of that gene Z. It's not the gene that causes it. It's that the gene interacts with a certain environment. More specifically, a gene that makes you vulnerable in a stressful environment. Glucocorticoid profiles once a depression has been established. Not surprisingly, glucocorticoid levels are typically abnormal in people who are clinically depressed. A relatively infrequent subtype of depression, called atypical depression, is dominated by the psychomotor features of the disease, an incapacitating physical and psychological exhaustion. Just as is the case with chronic fatigue syndrome, atypical depression is characterized by lower than normal glucocorticoid levels. However, the far more common feature of depression is one of an overactive stress response, somewhat of an overly activated sympathetic nervous system, and even more dramatically, elevated levels of glucocorticoids. This adds to the picture that depressed people, sitting on the edge of their beds without the energy to get up, are actually vigilant and aroused with a hormonal profile to match, but the battle is inside them. Research stretching back some 40 years has explored why, on a nuts and bolts level, glucocorticoid levels are often elevated in depression. The elevated levels appear to be due to too much of a stress signal from the brain. Back to Chapter 2. Remember that the adrenals typically secrete glucocorticoids only when they are commanded to by the brain via the pituitary, rather than the adrenals just getting some depressive glucocorticoid hiccup all on their own now and then. Moreover, the excessive secretion of glucocorticoids is due to what is called feedback resistance. In other words, the brain is less effective than it should be at shutting down glucocorticoid secretion. Normally, the levels of this hormone are tightly regulated. The brain senses circulating glucocorticoid levels, and if they get higher than desired, the desired level shifts depending on whether events are calm or stressful, the brain stops secreting CRH. Just like the regulation of water in a toilet bowl tank. In depressives, this feedback regulation fails. Concentrations of circulating glucocorticoids that should shut down the system fail to do so, as the brain does not sense the feedback signal. What are the consequences of elevated glucocorticoid levels before and during a depression? The first most critical question to ask is, how does an excess of glucocorticoids increase the risk of depression? A preceding section detailed at great length the considerable confusion about whether depression is about serotonin or norepinephrine or dopamine. To the extent that this is the case, the glucocorticoid angle fits well, in that the hormones can alter features of all three neurotransmitter systems: the amount of neurotransmitter synthesized, how fast it is broken down, how many receptors there are for each neurotransmitter, how well the receptors work, and so on. Moreover, stress has been shown to cause many of the same changes as well. Sustained stress will deplete dopamine from those pleasure pathways, and norepinephrine from that alerting locus ceruleus part of the brain. Moreover, stress alters all sorts of aspects of the synthesis, release, efficacy, and breakdown of serotonin. It is not clear which of those stress effects are most important, simply because it is not clear which neurotransmitter or neurotransmitters are most important. However, it is probably safe to say that whatever neurochemical abnormalities wind up being shown definitively to underlie depression, there is precedent for stress and glucocorticoids causing those same abnormalities. Those elevated glucocorticoid levels appear to have some other consequences as well. They may play a role, for example, in the fact that depressive patients often are at least mildly immunosuppressed and are more prone to osteoporosis. Moreover, prolonged major depression increases the risk of heart disease about 3 to 4-fold, even after controlling for smoking and alcohol consumption, and the glucocorticoid excess is likely to contribute to that as well. And there may be more consequences. Think back to Chapter 10 and its discussion of the many ways in which glucocorticoids can damage the hippocampus. As that literature emerged in the 1980s, it immediately suggested that there may be problems with the hippocampus in people with major depression. This speculation was reinforced by the fact that the type of memory most often impaired in depression, declarative memory, is mediated by the hippocampus. As was discussed in Chapter 10, there is atrophy of the hippocampus in long-term depression. The atrophy emerges as a result of the depression, rather than precedes it, and the longer the depressive history, the more atrophy and the more memory problems. While no one has explicitly shown yet that the atrophy occurs only in those depressives with the elevated glucocorticoid levels, the atrophy is most common in the subtypes of depression in which the glucocorticoid excess is most common. Chronic depression has also been associated in some studies with decreased volume in the frontal cortex. This was initially puzzling for those of us who view the world through glucocorticoid-tinted glasses, but has recently been resolved. In the rat, the hippocampus is overwhelmingly the target in the brain for glucocorticoid action, as measured by the density of receptors for the hormone. However, in the primate brain, the hippocampus and frontal cortex seem to be equally and markedly sensitive to glucocorticoids. So, some pretty decent circumstantial evidence suggests that the glucocorticoid excess of depression may have something to do with the decreased volume of the hippocampus and frontal cortex. Chapter 10 noted an array of bad things that glucocorticoids could do to neurons. Some obsessively careful studies have shown loss of cells in the frontal cortex accompanying the volume loss in depression. As one point of confusion, it is those supportive glial cells rather than neurons that are lost. But in the hippocampus, no one has a clue yet. It could be the killing or atrophying of neurons, the inhibition of the birth of new neurons, or all of these. Whatever the explanation is at the cellular level, it appears to be permanent. Years to decades after these major depressions have been gotten under control, typically with medication, the volume loss is still there. Anti-glucocorticoids as antidepressants. The glucocorticoid depression link has some important implications. When I first introduced that link at the beginning of the chapter, it was meant to give some insight into the flavor of what a depression is like. A person looks like an enervated sea sponge, sitting there motionless on the edge of his bed, but he's actually boiling. in the middle of an internal battle. Tacit in that description was the idea that undergoing a depression is actually immensely stressful, and therefore, among other things, stimulates glucocorticoid secretion. The data just reviewed suggests the opposite scenario. Stress and glucocorticoid excess can be a cause of depression rather than merely a consequence. If that is really the case, then a novel clinical intervention should work. Take one of those depressives with high glucocorticoid levels, find some drug that works on the adrenals to lower glucocorticoid secretion, and the depression should lessen. And, very exciting, that has been shown. The approach, though, is filled with problems. You don't want to suppress glucocorticoid levels too much, because, by this point in the book, it should be apparent by now that those hormones are pretty important. Moreover, the adrenal steroidogenesis inhibitors, as those drugs are called, can have some nasty side effects. Nonetheless, some solid reports have shown them to have antidepressant effects in people with high glucocorticoid depressions. Another version of the same approach is to use a drug that blocks glucocorticoid receptors in the brain. These exist and are relatively safe, and there's now decent evidence that they work as well. A relatively obscure hormone called DHEA, which has some ability to block glucocorticoid access to its receptor, has been reported to have some antidepressant qualities as well. Thus, these recent studies not only teach us something about the bases of depression, but may open the way for a whole new generation of medications for the disease. Some investigators have built on these observations with a fairly radical suggestion. For those biological psychiatrists concerned with the hormonal aspect of depression, the traditional glucocorticoid scenario is outlined. In it, depressions are stressful and raise glucocorticoid levels. When someone is treated with antidepressants, the abnormal neurochemistry related to serotonin, norepinephrine, etc., is normalized, lessening the depression and, by the way, making life feel less stressful, with glucocorticoid levels returning to normal as a byproduct. The new scenario is the logical extension of the inverted causality also just discussed. In this version, for any of a number of reasons, glucocorticoid levels rise in someone, because the person is under a lot of stress, because something about the regulatory control of glucocorticoids is awry in that person, causing changes in the chemistry of serotonin, or norepinephrine, etc., and a depression. In this scenario, antidepressants work by normalizing glucocorticoid levels, thereby normalizing the brain chemistry and alleviating the depression. For this view to be supported, it has to be shown that the primary mechanism of action of the different classes of antidepressants is to work on the glucocorticoid system, and that changes in glucocorticoid levels precede the changes in brain chemistry or depressive symptoms. A few researchers have presented evidence that antidepressants work to rapidly alter numbers of glucocorticoid receptors in the brain, altering regulatory control of the system and lowering glucocorticoid levels, and these changes precede changes in the traditional symptoms of depression. Other researchers have not observed this. As usual, more research is needed. But even if it turns out that in some patients, depression is driven by elevated glucocorticoid levels, and recovery from depression thus mediated by reduction of those levels, that can't be the general mechanism of the disease in all cases. Only about half of depressives actually have elevated glucocorticoid levels. In the other half, the glucocorticoid system seems to work perfectly normally. Perhaps this particular stress-depression link is relevant only during the first few rounds of someone's depression, before the endogenous rhythmicity kicks in, or only in a subset of individuals. We have now seen ways in which stress and glucocorticoids are intertwined with the biology of depression. That intertwining is made even tighter when considering the psychological picture of the disease. Stress and the psychodynamics of major depressions. I have to begin with Freud. I know it is obligatory to dump on Freud, and some of it is deserved, but there is much that he still has to offer. I can think of few other scientists who, nearly a century after their major contributions, are still considered important and correct enough for anyone to want to bother pointing out their errors, instead of just consigning them to the library archives. Freud was fascinated with depression and focused on the issue that we began with. Why is it that most of us can have occasional terrible experiences, feel depressed, and then recover, while a few of us collapse into major depression, melancholia? In his classic essay, Mourning and Melancholia, 1917, Freud began with what the two have in common. In both cases, he felt, there is the loss of a love object. In Freudian terms, such an object is usually a person, but can also be a goal or an ideal. In Freud's formulation, in every loving relationship there is ambivalence, mixed feelings, elements of hatred as well as love. In the case of a small reactive depression, mourning, you are able to deal with those mixed feelings in a healthy manner. You lose, you grieve, and then you recover. In the case of a major melancholic depression, you have become obsessed with the ambivalence, the simultaneity, the irreconcilable nature of the intense love alongside the intense hatred. Melancholia, a major depression, Freud theorized, is the internal conflict generated by this ambivalence. This can begin to explain the intensity of grief experienced in a major depression. If you are obsessed with the intensely mixed feelings, you grieve doubly after a loss, for your loss of the loved individual and for the loss of any chance now to ever resolve the difficulties. If only I had said the things I needed to. If only we could have worked things out. For all of time, you have lost the chance to purge yourself of the ambivalence. For the rest of your life, you will be reaching for the door to let you into a place of pure, unsullied love, and you can never reach that door. It also explains the intensity of the guilt often experienced in major depression. If you truly harbored intense anger toward the person along with love, in the aftermath of your loss, there must be some facet of you that is celebrating alongside the grieving. He's gone. That's terrible, but thank God I can finally live. I can finally grow up. No more of this or that. Inevitably, a metaphorical instant later, there must come a paralyzing belief that you have become a horrible monster to feel any sense of relief or pleasure at a time like this. Incapacitating guilt. This theory also explains the tendency of major depressives in such circumstances to, oddly, begin to take on some of the traits of the lost, loved, hated one. And not just any traits, but invariably the ones that the survivor found most irritating. Psychodynamically, this is wonderfully logical. By taking on a trait, you are being loyal to your lost beloved opponent. By picking an irritating trait, you are still trying to convince the world that you are right to be irritated. You see how you hate it when I do it? Can you imagine what it was like to have to put up with that for years? And by picking a trait that, most of all, you find irritating, you are not only still trying to score points in your argument with the departed, but you are punishing yourself for arguing as well. Out of the Freudian school of thought has come one of the more apt descriptions of depression: aggression turned inward. Suddenly, the loss of pleasure, the psychomotor retardation, the impulse to suicide, all make sense, as do the elevated glucocorticoid levels. This does not describe someone too lethargic to function. It is more like the actual state of a patient in depression, exhausted from the most draining emotional conflict of his or her life, one going on entirely within. If that doesn't count as psychologically stressful, I don't know what does. Like other good parts of Freud, these ideas are empathic and fit many clinical traits. They just feel right. But they are hard to assimilate into modern science, especially biologically oriented psychiatry. There is no way to study the correlation between serotonin receptor density and internalization of aggression, for example, or the effects of estrogen-progesterone ratios on love-hate ratios. The branch of psychological theorizing about depression that seems most useful to me, and is most tightly linked to stress, comes from experimental psychology. Work in this field has generated an extraordinarily informative model of depression. Stress, learned helplessness, and depression. In order to appreciate the experimental studies underlying this model, recall that in the preceding chapter on psychological stress, we saw that certain features dominated as psychologically stressful: a loss of control and of predictability within certain contexts, a loss of outlets for frustration, a loss of sources of support, a perception of life worsening. In one style of experiment, pioneered by the psychologists Martin Seligman and Stephen Meyer, animals are exposed to pathological amounts of these psychological stressors. The result is a condition strikingly similar to a human depression. Although the actual stressors may differ, the general approach in these studies always emphasizes repeated stressors with a complete absence of control on the part of the animal. For example, a rat may be subjected to a long series of frequent, uncontrollable, and unpredictable shocks or noises, with no outlets. After a while, something extraordinary happens to that rat. This can be shown with a test. Take a fresh, unstressed rat and give it something easy to learn. You put it in a room, for example, with the floor divided into two halves. Occasionally, electricity that will cause a mild shock is delivered to one half, and just beforehand, there is a signal indicating which half of the floor is about to be electrified. Your run-of-the-mill rat can learn this active avoidance task easily, and within a short time it readily and calmly shifts the side of the room it sits in according to the signal. Simple. Except for a rat who has recently been exposed to repeated uncontrollable stressors. That rat cannot learn the task. It does not learn to cope. On the contrary, it has learned to be helpless. This phenomenon, called learned helplessness, is quite generalized. The animal has trouble coping with all sorts of varied tasks after its exposure to uncontrollable stressors. Such helplessness extends to tasks having to do with its ordinary life, like competing with another animal for food or avoiding social aggression. One might wonder whether the helplessness is induced by the physical stress of receiving the shocks, or instead, the psychological stressor of having no control over or capacity to predict the shocks. It is the latter. The clearest way to demonstrate this is to yoke pairs of rats. One gets shocked under conditions marked by predictability and a certain degree of control. The other rat gets the identical pattern of shocks, but without the control or predictability. Only the latter rat becomes helpless. Seligman argues persuasively that animals suffering from learned helplessness share many psychological features with depressed humans. Such animals have a motivational problem. One of the reasons that they are helpless is that they often do not even attempt a coping response when they are in a new situation. This is quite similar to the depressed person who doesn't even try the simplest task that would improve her life. I'm too tired. It seems overwhelming to take on something like that. It's not going to work anyway. Animals with learned helplessness also have a cognitive problem, something awry with how they perceive the world and think about it. When they do make the rare coping response, they can't tell whether it works or not. For example, if you tighten the association between a coping response and a reward, a normal rat's response rate increases. In other words, if the coping response works for the rat, it persists in that response. In contrast, linking rewards more closely to the rare coping responses of a helpless rat has little effect on its response state. Seligman believes that this is not a consequence of helpless animals somehow missing the rules of the task. Instead, he thinks, they have actually learned not to bother paying attention. By all logic, that rat should have learned, when I am getting shocked, there is absolutely nothing I can do, and that feels terrible. But it isn't the whole world. It isn't true for everything. Instead, it has learned, there is nothing I can do, ever. Even when control and mastery are potentially made available to it, the rat cannot perceive them. This is very similar to the depressed human who always sees glasses half empty. As Beck and other cognitive therapists have emphasized, much of what constitutes a depression is centered around responding to one awful thing and overgeneralizing from it, cognitively distorting how the world works. The learned helplessness paradigm produces animals with other features strikingly similar to those in humans with major depressions. There is a rat's equivalent of dysphoria. The rat stops grooming itself and loses interest in sex and food. The rat's failure even to attempt coping responses suggests that it experiences an animal equivalent of psychomotor retardation. In some models of learned helplessness, animals mutilate themselves, biting at themselves. Many of the vegetative symptoms appear as well: sleep loss and disorganization of sleep architecture, elevated glucocorticoid levels. Most critically, these animals tend to be depleted of norepinephrine in certain parts of the brain, while antidepressant drugs and ECT speed up their recovery from the learned helplessness state. Learned helplessness has been induced in rodents, cats, dogs, birds, insects, and primates, including humans. It takes surprisingly little in terms of uncontrollable unpleasantness to make humans give up and become helpless in a generalized way. In one study by Donald Hiroto, student volunteers were exposed to either escapable or inescapable loud noises. As in all such studies, the two groups were paired so that they were exposed to the same amount of noise. Afterward, they were given a learning task in which a correct response turned off a loud noise. The inescapable group was significantly less capable of learning the task. Helplessness can even be generalized to non-aversive learning situations. Hiroto and Seligman did a follow-up study in which again there was either controllable or uncontrollable noise. Afterward, the latter group was less capable of solving simple word puzzles. Giving up can also be induced by stressors far more subtle than uncontrollable loud noises. In another study, Hiroto and Seligman gave volunteers a learning task in which they had to pick a card of a certain color according to rules that they had to discern along the way. In one group, these rules were learnable. In the other group, the rules were not. The card color was randomized. Afterward, the latter group was less capable of coping with a simple and easily solved task. Seligman and colleagues have also demonstrated that unsolvable tasks induced helplessness afterward in social coping situations. Thus, humans can be provoked into at least transient cases of learned helplessness, and with surprising ease. Naturally, there is tremendous individual variation in how readily this happens. Some of us are more vulnerable than others, and you can bet that this is going to be important in considering stress management in the final chapter. In the experiment involving inescapable noise, Hiroto had given the students a personality inventory beforehand. Based on that, he was able to identify the students who came into the experiment with a strongly internalized locus of control, a belief that they were the masters of their own destiny and had a great deal of control in their lives, and, in contrast, the markedly externalized volunteers, who tended to attribute outcomes to chance and luck. In the aftermath of the uncontrollable stressor, the externalized students were far more vulnerable to learned helplessness. Transferring that to the real world with the same external stressors, the more that someone has an internal locus of control, the less the likelihood of a depression. Collectively, these studies strike me as extremely important in forming links among stress, personality, and depression. Our lives are replete with incidents in which we become irrationally helpless. Some are silly and inconsequential. Once, in the African camp that I shared with Lawrence Frank, the zoologist whose hyenas figured in Chapter 7, we managed to make a disaster of preparing macaroni and cheese over the campfire. Inspecting the mess, we ruefully admitted that it might have helped if we had bothered to read the instructions on the box. Yet we had both avoided doing that. In fact, we both felt a formless dread about trying to make sense of such instructions. Frank summed it up. Face it, we suffer from learned cooking helplessness. But life is full of more significant examples. If a teacher at a critical point in our education, or a loved one at a critical point of our emotional development, frequently exposes us to his or her own specialized uncontrollable stressors, we may grow up with distorted beliefs about what we cannot learn or ways in which we are unlikely to be loved. In one chilling demonstration of this, some psychologists studied inner-city school kids with severe reading problems. Were they intellectually incapable of reading? Apparently not. The psychologists circumvented the students' resistance to learning to read by instead teaching them Chinese characters. Within hours, they were capable of reading more complex symbolic sentences than they could in English. The children had apparently been previously taught all too well that reading English was beyond their ability. A major depression, these findings suggest, can be the outcome of particularly severe lessons in uncontrollability for those of us who are already vulnerable. This may explain an array of findings that show that if a child is stressed in certain ways, loss of a parent to death, divorce of parents, being a victim of abusive parenting, the child is more at risk for depression years later. What could be a more severe lesson that awful things can happen that are beyond our control than a lesson at an age when we are first forming our impressions about the nature of the world? As an underpinning of this, Paul Plotsky and Charles Nemiroff of Emory University have shown that rats or monkeys exposed to stressors early in life have a lifelong increase in CRH levels in their brain. According to our model, writes Seligman, depression is not generalized pessimism, but pessimism specific to the effects of one's own skilled actions. Subjected to enough uncontrollable stress, we learn to be helpless. We lack the motivation to try to live because we assume the worst. We lack the cognitive clarity to perceive when things are actually going fine, and we feel an aching lack of pleasure in everything. Attempting an integration. Psychological approaches to depression give us some insight into the nature of the disease. According to one school, it is a state brought about by pathological overexposure to loss of control and outlets for frustration. In another psychological view, the Freudian one, it is the internalized battle of ambivalences, aggression turned inward. These views contrast with the more biological ones, that depression is a disorder of abnormal neurotransmitter levels, abnormal communication between certain parts of the brain, abnormal hormone ratios, genetic vulnerability. There are extremely different ways of looking at the world, and researchers and clinicians from different orientations often don't have a word to say to one another about their mutual interest in depression. Sometimes they seem to be talking radically different languages. Psychodynamic ambivalence versus neurotransmitter autoreceptors. Cognitive overgeneralization versus allelic variants of genes. What I view as the main point of this chapter is that stress is the unifying theme that pulls together these disparate threads of biology and psychology. We have now seen some important links between stress and depression. Extremes of psychological stress can cause something in a laboratory animal that looks pretty close to a depression. Moreover, stress is a predisposing factor in human depression as well, and brings about some of the typical endocrine changes of depression. In addition, genes that predispose to depression only do so in a stressful environment. Tightening the link further, glucocorticoids as a central hormone of the stress response can bring about depression-like states in an animal and can cause depression in humans. And finally, both stress and glucocorticoids can bring about neurochemical changes that have been implicated in depression. With these findings in hand, the pieces begin to fit together. Stress, particularly in the form of extremes of lack of control and outlets, causes an array of deleterious changes in a person. Cognitively, this involves a distorted belief that there is no control or outlets in any circumstance learned helplessness. On the affective level, there is anhedonia. Behaviorally, there is psychomotor retardation. On the neurochemical level, there are likely disruptions of serotonin, norepinephrine, and dopamine signaling, as will be shown in Chapter 16. prolonged stress can deplete dopamine in the pleasure pathways. Physiologically, there are alterations in, among other things, appetite, sleep patterns, and sensitivity of the glucocorticoid system to feedback regulation. We call this array of changes collectively a major depression. This is terrific. I believe we have a stress-related disease on our hands. But some critical questions remain to be asked. One concerns why it is that after 3 or so bouts of major depression, the stress-depression link uncouples. This is the business about depressive episodes taking on an internal rhythm of their own, independent of whether the outside world is actually pummeling you with stressors. Why should such a transition occur? At present, there's a lot of theorizing, but very little in the way of actual data. But the most basic question remains, why do only some of us get depressed? An obvious answer is because some of us are exposed to a lot more stressors than others. And when factoring in development, that can be stated in a way that also includes history. Not only are some of us exposed to more stressors than others, but if we are exposed to some awful stressors early in life, forever after we will be more vulnerable to whatever subsequent stressors are thrown at us. This is the essence of allostatic load, of wear and tear, where exposure to severe stress produces rents of vulnerability. So, differential incidences of depression can be explained by differences in the amount of stress and or in stress histories. But even for the same stressors and the same history of stress, some of us are more vulnerable than others. Why should some of us succumb more readily? To begin to make sense of this, we have to invert that question to state it in a more world-weary way. How is it that any of us manage to avoid getting depressed? All things considered, this can be an awful world, and at times it must seem miraculous that any of us resist despair. The answer is that we have built into us a biology of recovering from the effects of stress that provoke depression. As we've seen, stress and glucocorticoids can bring about many of the same alterations in neurotransmitter systems that have been implicated in depression. One of the best documented links is that stress depletes norepinephrine. No one is sure exactly why the depletion occurs, though it probably has something to do with norepinephrine being consumed faster than usual, rather than its being made more slowly than usual. Critically, not only does stress deplete norepinephrine, but it simultaneously initiates the gradual synthesis of more epinephrine. At the same time that norepinephrine content is plummeting, shortly after the onset of stress, the brain is starting to make more of the key enzyme tyrosine hydroxylase, which synthesizes norepinephrine. Both glucocorticoids and, indirectly, the autonomic nervous system play a role in inducing the new tyrosine hydroxylase. The main point is that, in most of us, stress may cause depletion of norepinephrine, but only transiently. We're about to see there are similar mechanisms related to serotonin. Thus, while everyday stressors bring about some of the neurochemical changes linked to depression, along with some of the symptoms, we feel blue. At the same time, we are already building in the mechanisms of recovery. We get over it. We put things behind us. We get things in perspective. We move on with our lives. We heal and we recover. So, given the same stressors and stress histories, why do only some of us get depressed? There is increasing evidence for a reasonable answer, which is that the biology of vulnerability to depression is that you don't recover from stressors very well. Back to that finding of the different versions of gene Z, where one version increases your risk for depression, but only when coupled with a history of major stressors. The gene turns out to code for a protein called the serotonin transporter, also known as 5-HTT, derived from the fact that the chemical abbreviation for serotonin is 5-HT. In other words, the pump that causes the reuptake of serotonin from the synapse, whose actions are inhibited by drugs like Prozac, which are SSRIs, selective serotonin reuptake inhibitors. Aha! A whole bunch of pieces here are teetering on the edge of falling into place. The different allelic versions of the 5-HTT gene differ as to how good they are at removing serotonin from the synapse. And where does stress fit in? Glucocorticoids help regulate how much 5-HTT is made from the gene. And critically, glucocorticoids differ in how good they are at doing that, depending on which allelic version of the 5-HTT gene you have. This allows us to come up with a working model of depression risk. It is a simplistic one, and a more realistic version must incorporate the likelihood of scads more examples of interactions among genes and stressors than simply this stress glucocorticoids 5-HTT story. Nonetheless, maybe what occurs is something like this. A major stressor comes along and produces some of the neurochemical changes of depression. The more prior history of stress you have, especially early in life, the less of a stressor it takes to produce those neurochemical changes. But the same stress signal, namely glucocorticoids, alters norepinephrine synthesis, serotonin trafficking, and so on, starting you on the road toward recovery. Unless your genetic makeup means that those recovery steps don't work very well. This is the essence of the interaction between biology and experience. Take a sufficiently severe stressor, and, as studies suggest, virtually all of us will fall into despair. No degree of neurochemical recovery mechanisms can maintain your equilibrium in the face of some of the nightmares that life can produce. Conversely, have a life sufficiently free of stress, and even with a genetic predisposition, you may be safe. A car whose brakes are faulty presents no danger if it is never driven. But in between those two extremes, it is the interaction between the ambiguous experiences that life throws at us and the biology of our vulnerabilities and resiliencies that determines which of us fall prey to this awful disease. Chapter 15. Personality, Temperament, and their stress-related consequences. The main point of Chapter 13 was that psychological factors can modulate stress responses. Perceive yourself in a given situation to have expressive outlets, control, and predictive information, for example, and you are less likely to have a stress response. What this chapter explores is the fact that people habitually differ in how they modulate their stress responses with psychological variables. Your style, your temperament, your personality have much to do with whether you regularly perceive opportunities for control or safety signals when they are there, whether you consistently interpret ambiguous circumstances as implying good news or bad, whether you typically seek out and take advantage of social support. Some folks are good at modulating stress in these ways, and others are terrible. These fall within the larger category of what Richard Davidson has called affective style, and this turns out to be a very important factor in understanding why some people are more prone toward stress-related diseases than others. We start with a study in contrasts. Consider Gary. In the prime of his life, he is by most estimates a success. He's done okay for himself materially, and he's never come close to going hungry. He's also had more than his share of sexual partners, and he has done extremely well in the hierarchical world that dominates most of his waking hours. He's good at what he does, and what he does is compete. He's already number 2 and breathing down the neck of number 1, who's grown complacent and a bit slack. Things are good and likely to get better. But you wouldn't call Gary satisfied. In fact, he never really has been. Everything is a battle to him. The mere appearance of a rival rockets him into a tensely agitated state, and he views every interaction with a potential competitor as an in-your-face personal provocation. He views virtually every interaction with a distrustful vigilance. Not surprisingly, Gary has no friends to speak of. His subordinates give him a wide, fearful berth because of his tendency to take any frustration out on them. He behaves the same toward Kathleen, and barely knows their daughter Caitlin. This is the sort of guy who is completely indifferent to the cutest of infants. And when he looks at all he's accomplished, all he can think of is that he's still not number one. Gary's profile comes with some physiological correlates. Elevated basal glucocorticoid levels, a constant low-grade stress response because life is one big stressor for him, an immune system that you wouldn't wish on your worst enemy, elevated resting blood pressure, an unhealthy ratio of good to bad cholesterol, and already the early stages of serious atherosclerosis, and looking ahead a bit, a premature death in late middle age. Contrast that with Kenneth. He's also prime-aged and number 2 in his world, but he got there through a different route, one reflecting the different approach to life that he's had ever since he was a kid. Someone caustic or jaded might dismiss him as merely being a politician, but he's basically a good guy. Works well with others, comes to their aid, and they in turn to his. Consensus builder, team player, and if he's ever frustrated about anything, and it isn't all that certain he ever is, he certainly doesn't take it out on those around him. A few years ago, Kenneth was poised for a move to the number 1 spot, but he did something extraordinary. He walked away from it all. Times were good enough that he wasn't going to starve, and he had reached the realization that there were things in life more important than fighting your way up the hierarchy. So he's spending time with his kids, Sam and Alan, making sure they grow up safe and healthy. He has a best friend in their mother, Barbara, and never gives a thought to what he's turned his back on. Not surprisingly, Kenneth has a physiological profile quite different from Gary's, basically the opposite on every stress-related measure, and enjoys a robust good health. He is destined to live to a ripe old age, surrounded by kids, grandkids, and Barbara. Normally, with these sorts of profiles, you try to protect the privacy of the individuals involved, but I'm going to violate that by including pictures of Gary and Kenneth on your PDF companion, figures 17 and 18. Check them out. Isn't that something? Some baboons are driven sharks, avoid ulcers by giving them, see the world as full of waterholes that are half empty. And some baboons are the opposite in every way. Talk to any pet owner, and they will give ardent testimonials as to the indelible personality of their parakeet, turtle, or bunny. And they'd usually be at least somewhat right. People have published papers on animal personality. Some have concerned lab rats. Some rats have an aggressive, proactive style for dealing with stressors. Put a new object in their cage and they bury it in the bedding. These animals don't have much in the way of a glucocorticoid stress response. In contrast, there are reactive animals who respond to a menacing by avoiding it. They have a more marked glucocorticoid stress response. And then there are studies about stress-related personality differences in geese. There's even been a great study published about sunfish personalities, some of whom are shy, and some of whom are outgoing social butterflies. Animals are strongly individualistic, and when it comes to primates, there are astonishing differences in their personalities, temperaments, and coping styles. These differences carry some distinctive physiological consequences and disease risks related to stress. This is not the study of what external stressors have to do with health. This is instead the study of the impact on health of how an individual perceives, responds to, and copes with those external stressors. The lessons learned from some of these animals can be strikingly relevant to humans. Stress and the successful primate. If you are interested in understanding the stressors in our everyday lives and how some folks cope with them better than others, study a troop of baboons in the Serengeti. Big, smart, long-lived, highly social animals who live in groups of from 50 to 150. The Serengeti is a great place for them to live, offering minimal problems with predators, low infant mortality rates, easy access to food. Baboons there work perhaps 4 hours a day, foraging through the fields and trees for fruits, tubers, and edible grasses. This has been a critical implication for me, which has made them the perfect study subjects when I've snuck away from my laboratory to the Serengeti during the summers of the past 2 decades. If baboons are spending only 4 hours a day filling their stomachs, that leaves them with 8 hours a day of sunlight to be vile to one another. Social competition, coalitions forming to gang up on other animals, big males in bad moods beating up on someone smaller, snide gestures behind someone's back. Just like us. I am not being facetious. Think about some of the themes of the first chapter. How few of us are getting our ulcers because we have to walk 10 miles a day looking for grubs to eat. How few of us become hypertensive because we are about to punch it out with someone over the last gulp from the water hole. We are ecologically buffered and privileged enough to be stressed mainly over social and psychological matters. Because the ecosystem of the Serengeti is so ideal for savanna baboons, they have the same luxury to make each other sick with social and psychological stressors. Of course, like ours, theirs is a world filled with affiliation, friendships, relatives who support each other. But it is a viciously competitive society as well. If a baboon in the Serengeti is miserable, it is almost always because another baboon has worked hard and long to bring about that state. Individual styles of coping with the social stress appear to be critical. Thus, one of the things I set out to test was whether such styles predicted differences in stress-related physiology and disease. I watched the baboons, collected detailed behavioral data, and then would anesthetize the animals under controlled conditions, using a blowgun. Once they were unconscious, I could measure their glucocorticoid levels, their ability to make antibodies, their cholesterol profiles, and so on, under basal conditions and a range of stressed conditions. The cases of Gary and Kenneth already give us a sense of how different male baboons can be. Two students, Justina Ray and Charles Virgin, and I, analyzed years of behavioral data to try to formalize different elements of style and personality among these animals. Two students, Justina Ray and Charles Virgin, and I, analyzed years of behavioral data to try to formalize different elements of style and personality among these animals. We found some fascinating correlations between personality styles and physiology. Among males who were in the higher-ranking half of the hierarchy, we observed a cluster of behavioral traits associated with low-resting glucocorticoid levels, independent of their specific ranks. Some of these traits were related to how males competed with one another. The first trait was whether a male could tell the difference between a threatening and a neutral interaction with a rival. How does one spot this in a baboon? Look at a particular male and two different scenarios. First scenario. Along comes his worst rival, sits down next to him, and makes a threatening gesture. What does our male subject do? Alternative scenario. Our guy is sitting there. His worst rival comes along and wanders off to the next field to fall asleep. What does our guy do in this situation? Some males can tell the difference between these situations. Threatened from a foot away, they get agitated, vigilant, prepared. When they instead see their rival is taking a nap, they keep doing whatever they were doing. They can tell that one situation is bad news, the other is meaningless. But some males get agitated even when their rival is taking a nap across the field, the sort of situation that happens 5 times a day. If a male baboon can't tell the difference between the two situations, on the average, his resting glucocorticoid levels are twice as high as those of the guy who can tell the difference, after correcting for rank as a variable. If a rival napping across the field throws a male into turmoil, the latter's going to be in a constant state of stress. No wonder his glucocorticoid levels are elevated. These stressed baboons are similar to the hyperactive macaque monkeys that Jay Kaplan has studied. As you will recall from Chapter 3, these are individuals who respond to every social provocation with an overactivation of their stress response, the sympathetic nervous system, and carry the greater cardiovascular risk. Next variable. If the situation really is threatening, the rival's a foot away and making menacing moves, does our male sit there passively and wait for the fight? Or does he take control of the situation and strike first? Males who sit there passively, abdicating control, have much higher glucocorticoid levels than the take-charge types, after rank is eliminated as a factor in the analysis. We see the same pattern in low-ranking as well as high-ranking males. A third variable. After a fight, can the baboon tell whether he won or lost? Some guys are great at it. They win a fight and they groom their best friend. They lose a fight and they beat up someone smaller. Other baboons react the same way regardless of outcome. They can't tell if life is improving or worsening. The baboon who can't tell the difference between winning and losing has much higher glucocorticoid levels on average than the guys who can, independent of rank. Final variable. If a male has lost a fight, what does he do next? Does he sulk by himself, groom someone, or beat someone up? Discouragingly, it turns out that the males who are most likely to go beat on someone, thus displaying displaced aggression, have lower glucocorticoid levels, again after rank is eliminated as a variable. This is true for both subordinate baboons and the high-ranking ones. Thus, after factoring out rank, lower basal glucocorticoid levels are found in males who are best at telling the difference between threatening and neutral interactions, who take the initiative if the situation clearly is threatening, who are best at telling whether they won or lost, and in the latter case, who are most likely to make someone else pay for the defeat. This echoes some of the themes from the chapter on psychological stress. The males who were coping best, at least by this endocrine measure, had high degrees of social control, initiating the fights, predictability. They can accurately assess whether a situation is threatening, whether an outcome is good news, and outlets for frustration, a tendency to give rather than get ulcers. Remarkably, this style is stable over the years of these individuals' lives and carries a big payoff. Males with this cluster of low glucocorticoid traits remain high-ranking significantly longer than average. Our subsequent studies have shown another set of traits that also predict low basal glucocorticoid levels. These traits have nothing to do with how males compete with one another. Instead, they are related to patterns of social affiliation. Males who spent the most time grooming females not in heat, not of immediate sexual interest, just good old platonic friends, who are groomed by them the most frequently, who spend the most time playing with the young, these are the low glucocorticoid guys. Put most basically, and not at all anthropomorphically, these are male baboons who are most capable of developing friendships. This finding is remarkably similar to those discussed in previous chapters regarding the protective effects of social affiliation against stress-related disease in humans. And as will be discussed in the final chapter of this book, this cluster of personality traits is also stable over time and comes with a distinctive payoff as well, a male baboon's equivalent of a successful old age. Thus, among some male baboons, there are at least two routes for winding up with elevated basal glucocorticoid levels, independent of social rank: an inability to keep competition in perspective and social isolation. Stephen Swolmy at the National Institutes of Health has studied rhesus monkeys and identified another personality type that should seem familiar, which carries some physiological correlates. About 20% of rhesus are what he calls high reactors. Just like the baboons who find a rival napping to be an arousing threat, these individual monkeys see challenges everywhere. But in their case, the response to the perceived threat is a shrinking timidity. Put them into a novel environment that other rhesus monkeys would find to be a stimulating place to explore, and they react with fear, pouring out glucocorticoids. Place them with new peers and they freeze with anxiety, shy and withdrawn and again releasing vast amounts of glucocorticoids. Separate them from a loved one and they are atypically likely to collapse into a depression, complete with excessive glucocorticoids, overactivation of the sympathetic nervous system, and immunosuppression. These appear to be lifelong styles of dealing with the world, beginning early in infancy. From where do these various primate personalities arise? When it comes to the baboons, I'll never know. Male baboons change troops at puberty, often moving dozens of miles before finding an adult troop to join. it is virtually impossible to track the same individuals from birth to adulthood, so I have no idea what their childhoods were like, whether their mothers were permissive or stern, whether they were forced to take piano lessons, and so on. But Suomi has done elegant work that indicates both genetic and environmental components to these personality differences. For example, he has shown that an infant monkey has a significant chance of sharing a personality trait with its father, despite the formation of social groups in which the father is not present, a sure hint at a heritable genetic component. In contrast, the high reactivity personality in these monkeys can be completely prevented by fostering such animals early in life to atypically nurturing mothers, a powerful vote for environmental factors built around mothering style. Broadly, these various studies suggest two ways that a primate's personality style might lead down the path to stress-related disease. In the first way, there's a mismatch between the magnitude of the stressors they are confronted with and the magnitude of their stress response. The most neutral of circumstances is perceived as a threat, demanding either a hostile confrontational response, as with some of my baboons and Kaplan's macaques, or an anxious withdrawal, as with some of Suomi's monkeys. At the most extreme, they even react to a situation that most certainly does not constitute a stressor, for example, winning a fight, the same way as if it were a stressful misery, losing one. In their second style of dysfunction, the animal does not take advantage of the coping responses that might make a stressor more manageable. They don't grab the minimal control available in a tough situation. They don't make use of effective outlets when the going gets tough. And they lack social support. It would seem relatively straightforward to pull together some sound psychotherapeutic advice for these unhappy beasts. But in reality, it's hopeless. Baboons and macaques get distracted during therapy sessions, habitually pulling books off the shelves, for example. They don't know the days of the week and thus constantly miss appointments. They eat the plants in the waiting room, and so on. Thus, it might be more useful to apply those same insights to making sense of some humans who are prone toward an overactive stress response and increased risk of stress-related disease. The human realm. A cautionary note. There are by now some fairly impressive and convincing studies linking human personality types with stress-related diseases. Probably the best place to start, however, is with a bit of caution about some reported links that I suspect should be taken with a grain of salt. I've already noted some skepticism about early psychoanalytic theorizing that linked certain personality types with colitis. Recall Chapter 5. Another example concerns miscarriages and abortions. Chapter 7 reviewed the mechanisms by which stress can cause the loss of a pregnancy, and one hardly needs to have experienced that personally to have an inkling of the trauma involved. Thus, you can imagine the particular agony for women who miscarry repeatedly, and the special state of misery for those who never get a medical explanation for the problem. No expert has a clue what's wrong. Into that breach have charged people who have attempted to uncover personality traits common to women, labeled as psychogenic aborters. Some researchers have identified one subgroup of women with repeated psychogenic abortions, accounting for about half the cases, as being retarded in their psychological development. They are characterized as emotionally immature women, highly dependent on their husbands, who on some unconscious level view the impending arrival of the child as a threat to their own childlike relationship with their spouse. Another personality type identified at the opposite extreme are women who are characterized as being assertive and independent, who really don't want to have a child. Thus, a common theme in the two supposed profiles is an unconscious desire not to have the child, either because of competition for the spouse's attention or because of reluctance to cramp their independent lifestyles. Many experts are skeptical about the studies behind these characterizations, however. The first reason harks back to a caveat I aired early in the book. A diagnosis of psychogenic anything, impotency, amenorrhea, abortion, and so on, is usually a diagnosis by exclusion. In other words, the physician can't find any disease or organic cause, and until one is discovered, the disorder gets tossed into the psychogenic bucket. This may mean that, legitimately, it is heavily explained by psychological variables, or it may simply mean that the relevant hormone, neurotransmitter, or genetic abnormality has not yet been discovered. Once it is discovered, the psychogenic disease is magically transformed into an organic problem. Oh, it wasn't your personality after all. The area of repeated aborting seems to be one that is rife with recent biological insights. In other words, if so many of last decade's psychogenic aborters now have an organic explanation for their malady, that trend is likely to continue. So be skeptical of any current psychogenic label. Another difficulty is that these studies are all retrospective in design. The researchers examine the personalities of women after they have had repeated abortions. A study may thus cite the case of a woman who has had 3 miscarriages in a row, noting that she is emotionally withdrawn and dependent on her husband. But because of the nature of the research design, one can't tell whether these traits are a cause of the miscarriages or a response to them. 3 successive miscarriages could well exact a heavy emotional price, perhaps making the subject withdrawn and more dependent on her husband. In order to study the phenomenon properly, one would need to look at personality profiles of women before they become pregnant, to see if these traits predict who is going to have repeated miscarriages. To my knowledge, this kind of study has not yet been carried out. As a final problem, none of the studies provides any reasonable speculation as to how a particular personality type may lead to a tendency not to carry fetuses to term. What are the mediating physiological mechanisms? What hormones and organ functions are disrupted? The absence of any science in that area makes me pretty suspicious of the claims. Psychological stressors can increase the risk of a miscarriage, but although there is precedent in the medical literature for thinking that having a certain type of personality is associated with an increased risk for miscarriages, scientists are far from being able to agree on what personality is associated, let alone whether the personality is a cause or consequence of the miscarriages. Psychiatric disorders and abnormal stress responses. A number of psychiatric disorders involve personalities, roles, and temperaments that are associated with distinctive stress responses. We have seen an example of this in the previous chapter on depression. About half of depressives have resting glucocorticoid levels that are dramatically higher than in other people, often sufficiently elevated to cause problems with metabolism or immunity. Or in some cases, depressives are unable to turn off glucocorticoid secretion, their brains being less sensitive to a shutoff signal. A theme in the previous section on some troubled non-human primates is that there is a discrepancy between the sorts of stressors they are exposed to and the coping responses they come up with. Learned helplessness, which we saw to be an underpinning of depression, appears to be another example of such discrepancy. A challenge occurs, and what is the response of a depressive individual? I can't, it's too much, why bother doing anything? It isn't going to work anyway, nothing I do ever works. The discrepancy here is that in the face of stressful challenges, depressives don't even attempt to mount a coping response. A different type of discrepancy is seen with people who are anxiety-prone. Anxiety disorders. What is anxiety? A sense of disquiet, of disease, of the sands constantly shifting menacingly beneath your feet, where constant vigilance is the only hope of effectively protecting yourself. Anxiety disorders come in a number of flavors. To name just a few, generalized anxiety disorder is just that, generalized, whereas phobias focus on specific things. In people with panic attacks, the anxiety boils over with a paralyzing, hyperventilating sense of crisis that causes massive activation of the sympathetic nervous system. In obsessive-compulsive disorder, the anxiety buries and busies itself in endless patterns of calming, distracting ritual. In post-traumatic stress disorder, the anxiety can be traced to a specific trauma. In none of these cases is the anxiety about fear, Fear is the vigilance and the need to escape from something real. Anxiety is about dread and foreboding and your imagination running away with you. Much as with depression, anxiety is rooted in a cognitive distortion. In this case, people prone toward anxiety overestimate risks and the likelihood of a bad outcome. Unlike depressives, the anxiety-prone person is still attempting to mobilize coping responses. But the discrepancy is the distorted belief that stressors are everywhere and perpetual, and that the only hope for safety is constant mobilization of coping responses. Life consists of the concrete, agitated present of solving a problem that someone else might not even consider to exist. Awful and immensely stressful. Not surprisingly, anxiety disorders are associated with chronically overactive stress responses, and with increased risk of many of the diseases that fill the chapters of this book. Anxiety-prone rats, for example, have a shortened lifespan. However, glucocorticoid excess is not the usual response. Instead, it's too much sympathetic activation, an overabundance of circulating catecholamines, epinephrine and norepinephrine. We have now seen some interesting contrasts between glucocorticoids and the catecholamines, epinephrine and norepinephrine. Chapter 2 emphasized how the former defend you against stressors by handing out guns from the gun locker within seconds, in contrast to glucocorticoids, which defend you by constructing new weapons over the course of minutes to hours. Or there can be an elaboration of this time course, in which catecholamines mediate the response to a current stressor, while glucocorticoids mediate preparation for the next stressor. When it comes to psychiatric disorders, it seems that increases in the catecholamines have something to do with still trying to cope, and the effort that involves, whereas overabundance of glucocorticoids seems more of a signal of having given up or attempting to cope. You can show this with a lab rat. Rats, being nocturnal creatures, don't like bright lights, are made anxious by them. Put a rat in a cage whose edges are dark, just the place a rat likes to hunker down. But the rat is really hungry, and there's some wonderful food in the middle of the cage under a bright light. Massive anxiety. The rat starts toward the food, pulls back, again and again, frantically tries to figure ways to the food that might avoid the light. This is anxiety, a disorganized attempt to cope, and this phase is dominated by catecholamines. If it goes on for too long, the animal gives up, just lies there in the shaded perimeter. And that is depression, and it is dominated by glucocorticoids. The biology of anxiety. The main point of this chapter is to explore how different psychiatric disorders and personality styles involve dealing poorly with stress, and we've just seen how anxiety fits the bill. But it is worth looking at the biology of the disease a bit. There are some things that mammals get anxious about that are innate. Bright lights for a rat, being dangled up in the air if you are a terrestrial creature, having your breathing obstructed for most any animal. But most things that make us anxious are learned. Maybe because they are associated with some trauma, or maybe because we've generalized them based on their similarity to something associated with a trauma. Organisms are predisposed to learn some of those associations more readily than others. Humans and spiders, for example, or monkeys and snakes. But we can learn to be anxious about utterly novel things, as we speed up to get across a suspension bridge quickly, wondering if the guy in that panel truck is from Al-Qaeda. This is a different type of learning than what we focused on in Chapter 10, which concerned the hippocampus and declarative learning. This is implicit learning, where a certain autonomic response in your body has been conditioned. Thus, consider a woman who has suffered a traumatic assault, where her brain has become conditioned to speed up her heart every time she sees a similar-looking man. Pavlovian learning. Ring the bell associated with food, and the brain has learned to activate salivary glands. See a certain type of face, and the brain has learned to activate the sympathetic nervous system. The conditioned memory can be elicited without you even being conscious of it. That woman finds herself in a crowded party, having a fine time, when suddenly the anxiety is there. She's gasping, heart racing, and she hasn't a clue why. It is not until a few seconds later that she realizes that the man talking just behind her has an accent just like the man. The body responds before there is consciousness of the similarity. As we saw in Chapter 10, while mild transient stress enhances declarative learning, prolonged or severe stress disrupts it. But in the case of this pre-conscious, implicit, autonomic learning, any type of stress enhances it. For example, make a loud sound and a lab rat will have a startle response. In a few milliseconds, its muscles tense. Stress the rat beforehand with any type of stressor, and the startle response is exaggerated and more likely to become a habitual conditioned response. Same in us. As mentioned, this is outside the realm of the hippocampus, that wonderfully rational conduit of declarative memory, helping us recall someone's birthday. Instead, anxiety and fear conditioning are the province of a related structure, the amygdala. To begin to make sense of its function, you have to look at brain areas that project to the amygdala, and where the amygdala projects to in turn. One route to the amygdala is from pain pathways, which brings us back to Chapter 9, and how there's pain and then there's subjective pain interpretation. The amygdala is about the latter. The structure also gets sensory information. Remarkably, the amygdala gets sensory information before that information reaches the cortex and causes conscious awareness of the sensation. The woman's heart races before she is even aware of the accent of the man. The amygdala gets information from the autonomic nervous system. What's the significance of this? Suppose some ambiguous information is filtering in, and your amygdala is deciding whether this is a time to get anxious. If your heart is pounding and your stomach is in your throat, that input will bias the amygdala to vote for anxiety. And, to complete the picture, the amygdala is immensely sensitive to glucocorticoid signals. The outputs from the amygdala make perfect sense, mostly projections to the hypothalamus and related outposts, which initiate the cascade of glucocorticoid release and activate the sympathetic nervous system. And how does the amygdala communicate? By using CRH as a neurotransmitter. Some of the most convincing work implicating the amygdala and anxiety comes from brain imaging studies. Put people in a scanner, flash various pictures, see what parts of the brain are activated in response to each. Show a scary face and the amygdala lights up. Make the picture subliminal, flash them for thousandths of a second, too fast to be consciously seen, and too fast to activate the visual cortex, and the amygdala lights up. How does the functioning of the amygdala relate to anxiety? People with anxiety disorders have exaggerated startle responses, see menace that others don't. Give people some reading task where they are flashed a series of nonsense words and have to quickly detect the real ones. Everyone slows down slightly for a menacing word, but people with anxiety disorders slow down even more. Commensurate with these findings, the amygdala in such a person shows the same hyperreactivity, a picture that is sort of frightening, that doesn't quite activate the amygdala in a control subject, does so in an anxious person. A frightening picture that is flashed up too briefly to be even noted subliminally in a control subject does the trick to the amygdala in someone who is anxious. No wonder the sympathetic nervous system then races. Alarms are always going off in the amygdala. Why does the amygdala work differently in someone who is anxious? Some amazing research in recent years shows how this might work. As we saw in Chapter 10, major stressors and glucocorticoids disrupt hippocampal function. The synapses aren't able to do that long-term potentiation business, and the dendritic processes in neurons shrink. Remarkably, stress and glucocorticoids do just the opposite in the amygdala. Synapses become more excitable. Neurons grow more of the cables that connect the cells to each other. And if you artificially make the amygdala of a rat more excitable, the animal shows an anxiety-like disorder afterward. Joseph Ledoux of New York University, who pretty much put the amygdala on the map when it comes to anxiety, has constructed a remarkable model out of these findings. Suppose a major traumatic stressor occurs, of a sufficient magnitude to disrupt hippocampal function, while enhancing amygdaloid function. At some later point, in a similar setting, you have an anxious autonomic state, agitated and fearful, and you haven't a clue why. This is because you never consolidated memories of the event via your hippocampus, while your amygdala-mediated autonomic pathways sure as hell remember. This is a version of free-floating anxiety. Type A and the role of upholstery in cardiovascular physiology. A number of proposed links between personality and cardiovascular disease have been reported. Amid these, there is one proposed connection between personality and heart disease that has become so well known that it has suffered the ultimate accolade, namely, being distorted beyond recognition in many people's minds, usually winding up being ascribed to the most irritating behavioral trait that you want to complain about in someone else, or indirectly brag about in yourself. I'm talking being Type A. Two cardiologists, Meyer Friedman and Ray Rosenman, coined the term Type A in the early 1960s to describe a collection of traits that they found in some individuals. They didn't describe these traits in terms related to stress, for example, defining Type A people as those who responded to neutral or ambiguous situations as if they were stressful, although I will attempt to do that reframing shortly. Instead, they characterized Type A people as immensely competitive, overachieving, time-pressured, impatient, and hostile. People with that profile, they reported, had an increased risk of cardiovascular disease. This was met with enormous skepticism in the field. You're some 1950s Ozzie and Harriet cardiologist, and you think about heart valves and circulating lipids, not about how someone deals with a slow line at the supermarket. Thus, there was an initial tendency among many in the field to view the link between the behavior and the disease as the reverse of what Friedman and Rosenman proposed. Getting heart disease might make some people act in a more Type A manner. But Friedman and Rosenman did prospective studies that showed that the Type A-ness preceded the heart disease. This finding made a splash, and by the 1980s, some of the biggest guns in cardiology convened, checked the evidence, and concluded that being Type A carries at least as much cardiac risk as does smoking or having high cholesterol levels. Everyone was delighted, and Type A entered common parlance. The trouble was, soon thereafter, some careful studies failed to replicate the basic findings of Friedman and Rosenman. Suddenly, Type A wasn't looking good after all. Then, to add insult to injury, two studies showed that once you had coronary heart disease, being Type A was associated with better survival rates. In the notes of the attached PDF, I discuss subtle ways to explain this finding. By the late 1980s, the Type A concept underwent some major modifications. One was the recognition that personality factors are more predictive of heart disease when considering people who get their first heart attack at an early age. By later years, the occurrence of a first heart attack is more about fats and smoking. Moreover, work by Redford Williams of Duke University convinced most in the field that the key factor in the list of Type A-ish symptoms is the hostility. For example, when scientists reanalyzed some of the original Type A studies and broke the constellation of traits into individual ones, hostility popped out as the only significant predictor of heart disease. The same result was found in studies of middle-aged doctors who had taken personality inventory tests 25 years earlier as an exercise in medical school. And the same thing was found when looking at American lawyers, Finnish twins, Western Electric employees, a range of populations. As another example, there is a correlation between how hostile people are in 10 American cities and the mortality rates due to cardiovascular disease. These various studies have suggested that a high degree of hostility predicts coronary heart disease, atherosclerosis, hemorrhagic stroke, and higher rates of mortality with these diseases. Many of these studies, moreover, controlled for important variables like age, weight, blood pressure, cholesterol levels, and smoking. Thus, it is unlikely that the hostility-heart disease connection could be due to some other factor. For example, that hostile people are more likely to smoke, and the heart disease arises from the smoking, not the hostility. More recent studies have shown that hostility is associated with a significant overall increase in mortality across all diseases, not just those of the heart. Friedman and colleagues stuck with an alternative view. They suggested that at the core of the hostility is a sense of time-pressuredness. Can you believe that teller, how slowly he's working? I'm going to be here all day. I can't waste my life on some bank line. How did that kid know I was in a rush? I could kill him. And that the core of being time-pressured is rampant insecurity. There's no time to savor anything you've accomplished, let alone enjoy anything that anyone else has done, because you must rush off to prove yourself all over again and try to hide from the world for another day what a fraud you are. Their work suggested that a persistent sense of insecurity is in fact a better predictor of cardiovascular profiles than is hostility, although theirs appears to be a minority view in the field. Insofar as hostility has something to do with your heart, whether as a primary factor or as a surrogate variable, it remains unclear which aspects of hostility are bad news. For example, the study of lawyers suggested that overt aggressiveness and cynical mistrust were critical. In other words, frequent open expression of the anger you feel predicts heart disease. In support of that, experimental studies show that the full expression of anger is a powerful stimulant of the cardiovascular system. By contrast, in the reanalysis of the original type A data, a particularly powerful predictor of heart disease was not only high degrees of hostility, but also the tendency not to express it when angry. This latter view is supported by some fascinating work by James Gross of Stanford University. Show volunteers a film clip that evokes some strong emotion. Disgust, for example, thanks to a gory view of someone's leg being amputated. They writhe in discomfort and distaste, and no surprise, show the physiological markers of having turned on their sympathetic nervous systems. Now show some other volunteers the same film clip, but beforehand, instruct them to try not to express their emotions, so that if someone were watching, they'd have no idea what you were feeling. Run them through the blood and guts, and with them gripping the arms of their chairs and trying to remain stoic, and still the sympathetic activation becomes even greater. Repressing the expression of strong emotions appears to exaggerate the intensity of the physiology that goes along with them. Why would great hostility, or whatever variant, be bad for your heart? Some of it is likely to be that roundabout realm of risk factors, in that hostile individuals are more likely to smoke, eat poorly, drink to excess. Moreover, there are psychosocial variables, in that hostile people lack social support because they tend to drive people away. But there are direct biological consequences to hostility as well. Subjectively, we can describe hostile persons as those who get all worked up and angry over incidents that the rest of us would find only mildly provocative, if provocative at all. Similarly, their stress responses switch into high gear in circumstances that fail to perturb everyone else. Give both hostile and non-hostile people a non-social stressor, like some math problems, and nothing exciting happens. Everyone has roughly the same degree of mild cardiovascular activation. But if you generate a situation with a social provocation, the hostile people dump more epinephrine, norepinephrine, and glucocorticoids into their bloodstreams, and wind up with higher blood pressures and a host of other undesirable features of their cardiovascular systems. All sorts of social provocations have been used in studies. The subjects may be requested to take a test and during it be repeatedly interrupted. Or they may play a video game in which the opponent not only is rigged to win, but acts like a disparaging smart-aleck. In these and other cases, the cardiovascular stress responses of the non-hostile are relatively mild, but blood pressure goes through the roof in the hostile people. Isn't it remarkable how similar these folks are to Jay Kaplan's hyperreactive monkeys, with their exaggerated sympathetic responses to stressors and their increased risk of cardiovascular disease? Or to my baboons, the ones who can't differentiate between threatening and non-threatening events in their world. There are card-carrying type A individuals out there with tails. Here is that discrepancy again. For anxious people, life is full of menacing stressors that demand vigilant coping responses. For the type A, life is full of menacing stressors that demand vigilant coping responses of a particularly hostile nature. This is probably representative of the rest of their lives. If each day is filled with cardiovascular provocations that everyone else responds to as no big deal, life will slowly hammer away at the hearts of the hostile. An increased risk of cardiovascular disease is no surprise. A pleasing thing is that type A-ness is not forever. If you reduce the hostility component in type A people through therapy, using some of the approaches that will be outlined in the final chapter, you reduce the risk for further heart disease. This is great news. I've noticed that many health professionals who treat type A people are mostly trying to reform these folks. Basically, many type A people are abusive pains in the keister to lots of folks around them. When you talk to some of the type A experts, there is an odd tone between the lines that type A-ness, of which many of them are admittedly perfect examples, is a kind of ethical failing, and that the term is a fancied-up medical way of describing people who just aren't nice to others. Added to this is a tendency I've noticed for a lot of the type A experts to be lay preachers or descendants of clergy. That religious linkage will even sneak in the back door. I once talked with two leaders in the field, one an atheist and the other agnostic, and when they tried to give me a sense of how they try to get through to type A subjects about their bad ways, they made use of a religious sermon. I finally asked these two MDs an obvious question. Were they in the business of blood vessels or souls? Was the work that they do about heart disease or about ethics? And without a beat, they both chose ethics. Heart disease was just a wedge for getting at the bigger issues. I thought this was wonderful. If it takes turning our coronary vessels into our ledgers of sin and reducing circulating lipids as an act of redemption in order to get people to be more decent to each other, more power to them. Interior decorating as scientific method. A final question about this field. How was type A behavior discovered? We all know how scientists make their discoveries. There are the discoveries in the bathtub, Archimedes and his discernment of the displacement of water, discoveries in one's sleep, Kekuli and his dream of carbons dancing in a ring to form benzene, discoveries at the symphony. Our scientist, strained by overwork, is forced to the concert by a significant other. During a quiet woodwind section, there's the sudden realization, the scribbled equation on the program notes, the rushed, "Darling, I must leave this instant for the laboratory," accent on second syllable like in Masterpiece Theater, with the rest being history. But every now and then someone else makes the discovery and comes and tells the scientist about it. And who is that someone? Very often, someone whose role in the process could be summed up by an imaginary proverb that will probably never end up embroidered on someone's potholder. If you want to know if the elephant at the zoo has a stomach ache, don't ask the veterinarian, ask the cage cleaner. People who clean up messes become attuned to circumstances that change the amount of mess there is. Back in the 1950s, that fact caused a guy to just miss changing the course of medical history. I had the privilege of hearing this story from the horse's mouth, Dr. Meyer Friedman. It was the mid-1950s. Friedman and Rosenman had their successful cardiology practice, and they were having an unexpected problem. They were spending a fortune having to reupholster the chairs in their waiting rooms. This is not the sort of issue that would demand a cardiologist's attention. Nonetheless, there seemed to be no end of chairs that had to be fixed. One day, a new upholsterer came in to see the problem, took one look at the chairs, and discovered the type A cardiovascular disease link. "What the hell is wrong with your patients? People don't wear out chairs this way." It was only the frontmost few inches of the seat cushion and of the padded armrests that were torn to shreds, as if some very short beavers spent each night in the office craning their necks to savage the fronts of the chairs. The patients in the waiting rooms all habitually sat on the edges of their seats, fidgeting, clawing away at the armrests. The rest should have been history. Upswelling of music as the upholsterer is seized by the arms and held in a penetrating gaze. "Good heavens, man! Do you realize what you've just said?" Hurried conferences between the upholsterer and other cardiologists. Frenzied sleepless nights as teams of idealistic young upholsterers spread across the land, carrying the news of their discovery back to upholstery cardiology headquarters. Nope, you don't see that wear pattern in the waiting room chairs of the urologists, or the neurologists, or the oncologists, or the podiatrists. Just the cardiologists. There's something different about people who wind up with heart disease. And the field of type A therapy takes off. Instead, none of that happened. Dr. Friedman sighs. A confession. I didn't pay any attention to the man. I was too busy. It went in one ear and out the other. It wasn't until 4 or 5 years later that Dr. Friedman's formal research with his patients began to yield some hints, at which point there was the thunderclap of memory. Oh, my God! The upholsterer! Remember that guy going on about the wear pattern? And to this day, no one remembers his name. There have been a host of other studies concerning personality, temperament, and stress-related physiology. Scientists have reported differences in stress-related immune function between optimists and pessimists. Others have shown higher glucocorticoid levels in shyer individuals in social settings. Others have considered neuroses as a factor. But let's consider one more subject, one that is particularly interesting because it concerns the last people on Earth who you'd think were stressed. When life consists of nothing but squeezing tightly. This chapter has discussed personality types associated with overactive stress responses and argued that a common theme among them is a discrepancy between what sort of stressors life throws at these folks and what sort of coping responses they come up with. This final section is about a newly recognized version of an overactive stress response, and it's puzzling. These are not people who are dealing with their stressors too passively, too persistently, too vigilantly, or with too much hostility. They don't appear to have all that many stressors. They claim they're not depressed or anxious, and the psychological tests they are given show they're right. In fact, they describe themselves as pretty happy, successful, and accomplished. And according to personality tests, they really are. Yet these people, comprising approximately 5% of the population, have chronically activated stress responses. What's their problem? Their problem, I think, is one that offers insight into an unexpected vulnerability of our human psyche. The people in question are said to have repressive personalities, and we all have met someone like them. In fact, we usually regard these folks with a tinge of envy. I wish I had their discipline. Everything seems to come so easily to them. How do they do it? These are the archetypal people who cross all their T's and dot all their I's. They describe themselves as planners who don't like surprises, who live structured, rule-bound lives, walking to work the same way each day, always wearing the same style of clothes, the sort of people who can tell you what they're having for lunch 2 weeks from Wednesday. Not surprisingly, they don't like ambiguity and strive to set up their world in black and white, filled with good or bad people, behaviors that are permitted or strictly forbidden. They keep a tight lid on their emotions, stoic, regimented, hard-working, productive, solid folks who never stand out in a crowd, unless you begin to wonder at the unconventional nature of their extreme conventionality. Some personality tests, pioneered by Richard Davidson, identify repressive individuals. For starters, as noted, the personality tests show that these people aren't depressed or anxious. Instead, the tests reveal their need for social conformity, their dread of social disapproval, and their discomfort with ambiguity, as shown by the extremely high rates at which they agree with statements framed as absolutes, statements filled with never and always. No gray tones here. Intertwined with those characteristics is a peculiar lack of emotional expression. The tests reveal how repressive people inhibit negative affect. No expressing of those messy, complicated emotions for them, and little recognition of those complications in others. For example, ask repressors and non-repressors to recall an experience associated with a specific strong emotion. Both groups report that particular emotion with equal intensity. However, when asked what else they were feeling, non-repressors typically report an array of additional non-dominant feelings. Well, it mostly made me angry, but also a little sad, and a little disgusted, too. Repressors steadfastly report no secondary emotions, black and white feelings with little tolerance for subtle blends. Are these people for real? Maybe not. Maybe beneath their tranquil exteriors, they're actually anxious messes who won't admit to their frailties. Careful study indicates that some repressors are indeed mostly concerned about keeping up appearances. One clue is that they tend to give less repressed answers on personality questionnaires when they can be anonymous, and so their physiological symptoms of stress are easy to explain. We can cross those folks off the list. What about the rest of the repressors? Could they be deceiving themselves, roiling with anxiety but not even aware of it? Even careful questionnaires cannot detect that sort of self-deception. To ferret it out, psychologists traditionally rely on less structured, more open-ended tests, of the what do you see in this picture variety. Those tests show that yes, some repressors are far more anxious than they realize. Their physiological stress is also readily explained. Yet even after you cross the anxious self-deceivers off the list, there remains a group of people with tight, constrained personalities who are truly just fine, mentally healthy, happy, productive, socially interactive. But they have overactive stress responses. The levels of glucocorticoids in their bloodstream are as elevated as among highly depressed people, and they have elevated sympathetic tone as well. When exposed to a cognitive challenge, repressors show unusually large increases in heart rate, blood pressure, sweating, and muscle tension. And these over-aroused stress responses exact a price. For example, repressive individuals have relatively poor immune function. Furthermore, coronary disease patients who have repressive personalities are more vulnerable to cardiac complications than are non-repressors. Overactive, endangering stress responses, yet the people harboring them are not stressed, depressed, or anxious. Back to our envious thought. I wish I had their discipline. How do they do it? The way they do it, I suspect, is by working like maniacs to generate their structured, repressed world with no ambiguity or surprises. And this comes with a physiological bill. Davidson and Andrew Tomarkin of Vanderbilt University have used electroencephalographic EEG techniques to show unusually enhanced activity in a portion of the frontal cortex of repressors. As will be covered at length in the next chapter, this is a region of the brain involved in inhibiting impulsive emotion and cognition. For example, metabolic activity in this area has been reported to be decreased in violent sociopaths. It's the nearest anatomical equivalent we have to a superego. Makes you say you love the appalling dinner, compliment the new hairdo, keeps you toilet trained. It keeps those emotions tightly under control, and as Gross's work showed with emotional repression, it takes a lot of work to keep an especially tight squeeze on those emotional sphincters. It can be a frightening world out there, and the body may well reflect the effort of threading our way through those dark, menacing forests. How much better it would be to be able to sit, relaxed, on the sun-drenched porch of a villa, far, far from the wild things baying. Yet what looks like relaxation could well be exhaustion. Exhaustion from the labor of having built a wall around that villa, the effort of keeping out that unsettling, challenging, vibrant world. A lesson of repressive personality types and their invisible burdens is that sometimes it can be enormously stressful to construct a world without stressors. Chapter 16. Junkies, Adrenaline Junkies, and Pleasure. Okay. It's great that we're trying to understand how stress works and how to live healthier lives and make the world a better place and all that. But it's time we devoted a little space to a really important issue. Why can't we tickle ourselves? Before tackling this profound question, we first need to consider why not all people can make you feel ticklish. It probably requires that it be a person that you feel positive about. Thus, you're 5, and there's no one who can evoke ticklish feelings in you like your nutty uncle who chases you around the room first. Or you're 12, and it's the person in junior high school who's making your stomach feel like it's full of butterflies and making other parts of your body feel all mysterious and weird. It's why most of us probably wouldn't get the giggles if we were tickled by, say, Slobodan Milosevic. Most of us feel fairly positive about ourselves, so why can't we tickle ourselves? Philosophers have ruminated on this one through the ages and have come up with some speculations, but theories about self-tickling are a dime a dozen. Finally, a scientist has tackled this mystery by doing an experiment. Sarah Jane Blackmore of the University College of London first theorized that you can't tickle yourself because you know exactly when and where you're going to be tickled. There's no element of surprise. So she set out to test this by inventing a tickling machine. It consists of a lever attached to a foam pad where, thanks to various pulleys and fulcrums run by a computer, when you move the lever with one hand, the foam pad almost instantaneously strokes the palm of the other hand, moving in the same direction as the movement of the lever. Being a hard-nosed scientist, Blackmore quantified the whole thing, coming up with a tickle index. Then reinvent the wheel. If someone else operates the lever, it tickles you. If you do, nope. No element of surprise. You can't tickle yourself, even with a tickle machine. Then Blackmore tested her theory by removing the sense of predictability from the self-tickling process. First, remove the sense of predictability about when the tickling occurs. The person moves the lever, and unexpectedly there's a time lag until the foam pad moves. Anything more than 0.3 of a second delay, and it scores as high of a tickle index as if someone else had done it. Now remove the sense of predictability about where the tickling occurs. The person moves the lever, say, forward and back, and unexpectedly the foam pad moves in a different direction. Anything more than a 90-degree deviation from where you expected the pad to move, and it feels as ticklish as if someone else had done it. Now we've gotten somewhere. Being tickled doesn't feel ticklish until there is an element of surprise, of unpredictability, of lack of control. And suddenly, our beautiful world of tickle science is shattered around us. We spent a whole bunch of time some chapters back learning about how the cornerstones of psychological stress are built around a lack of control and predictability. Those were bad things, yet most of us like being tickled by the right person. Hey, wait a second. More pieces of our grand edifice begin to crumble. We stand in long lines to see movies that surprise and terrify us. We bungee jump and go on roller coasters that most definitely deprive us of a sense of control and predictability. We pay good money to be stressed sometimes. And as long as we're at it, as we've seen already, we turn on the sympathetic nervous system and secrete ample amounts of glucocorticoids during sex. What's up with that? Chapter 9 oriented us to the role of stress-induced analgesia in making us feel less awful during stress. But, as the starting point of this chapter, if you get the right amount of stress, if you get allostatically challenged just right, it doesn't just feel less awful. It can feel great. So how does that work? And why do some people find stress and risk-taking to feel so great that they get addicted? And how does stress interact with the pleasures and addictive qualities of various substances of abuse? The neurochemistry of pleasure. As we saw in Chapter 14, The brain contains a pleasure pathway that makes heavy use of the neurotransmitter dopamine. As we also saw in that chapter, if that pathway becomes depleted of dopamine, anhedonia or dysphoria can be an outcome. This dopaminergic projection begins in a region deep in the brain called the ventral tegmentum. It then projects to something called the nucleus accumbens, and then in turn goes on to all sorts of other places. These include the frontal cortex, which, as we saw in chapters 10 and 12, plays a key role in executive function, decision-making, and impulse control. There are also projections to the anterior cingulate cortex, which, as we saw in chapter 14, seems to play a role in having a sense of sadness, leading to the idea that the dopaminergic projection normally inhibits the cingulate. There's also a heavy projection into the amygdala, which, as we saw in the last chapter, plays a key role in anxiety and fear. The relationship between dopamine and pleasure is subtle and critical. On first pass, one might predict that the neurotransmitter is about pleasure, about reward. For example, take a monkey who has been trained in a task. A distinctive bell sounds, which means that the monkey now presses a lever 10 times. This leads 10 seconds later to a desirable food reward. You might initially guess that activation of the dopamine pathway causes neurons in the frontal cortex to become their most active in response to the reward. Some brilliant studies by Wolfram Schultz of the University in Freiburg in Switzerland showed something more interesting. Yes, frontal neurons become excited in response to reward, but the biggest response comes earlier, around the time of the bell sounding and the task commencing. This isn't a signal of, "this feels great." It's about mastery and expectation and confidence. It's, "I know what that light means. I know the rules. If I press the lever, then I'm going to get some food. I'm all over this. This is going to be great." The pleasure is in the anticipation of a reward. From the standpoint of dopamine, the reward is almost an afterthought. Psychologists refer to the period of anticipation, of expectation, of working for reward as the appetitive stage, one filled with appetite, and call the stage that commences with reward the consumatory stage. What Schultz's findings show is that if you know your appetite is going to be sated, pleasure is more about the appetite than about the sating. The next key thing to learn is that the dopamine and its associated sense of pleasurable anticipation fuels the work needed to get that reward. Paul Phillips from the University of North Carolina has used some immensely fancy techniques to measure millisecond bursts of dopamine in rats, and has showed with the best time resolution to date that the burst comes just before the behavior. Then, in the clincher, he artificially stimulated dopamine release, and suddenly the rat would start lever pressing. The dopamine does indeed fuel the behavior. The next critical point is that the strength of these pathways can change, just like in any other part of the brain. There's the burst of dopaminergic pleasure once that light comes on, and all that is required is to train for longer and longer intervals between light and reward, for those anticipatory bursts of dopamine to fuel ever-increasing amounts of lever pressing. This is how gratification postponement works. The core of goal-directed behavior is expectation. Soon, we're foregoing immediate pleasure in order to get good grades, in order to get into a good college, in order to get a good job, in order to get into the nursing home of our choice. Recent work by Schultz adds a twist to this. Suppose in one setup, the subject gets a signal, does a task, and then gets a reward. In the second situation, there's the signal, the task, and then, rather than a certainty of reward, there's simply a high probability of it. In other words, within a generally benevolent context, that is, the outcome is still likely to be good, there's an element of surprise. Under those conditions, there is even greater release of dopamine. Right after the task is completed, dopamine release starts to rise far higher than usual, peaking right around the time that the reward if it's going to happen, should be arriving. Introduce, "This is going to be great. Maybe. Probably." And your neurons spritz dopamine all over the place in anticipation. This is the essence of why, as we learned in Intro Psych, intermittent reinforcement is so reinforcing. What these findings show is that if you think there's a reasonably good chance that your appetite is going to be sated, but you're not positive, pleasure becomes even more about the appetite than about the sating. So, dopamine plays an important role in the anticipation of pleasure and in energizing you in order to respond to incentives. However, it can't be the whole story of pleasure, reward, and anticipation. For example, rats can still respond to reward to some extent even when artificially depleted of dopamine in those pathways. Opioids probably play a role in the other pathways involved. Moreover, the dopamine pathway might be most relevant to spiky, intense versions of anticipation. A recent and fascinating study shows this. Get some college students, either gender, who are in what they believe to be their one true love relationship. Put them in a scanner and flash up various familiar but neutral faces. Somewhere along the way, flash up a picture of the student's beloved. For people who are in the first few months of the relationship, the dopamine pathways lit up. For people whose relationship was more on the order of years, that's not what happened. Instead, there was activation of the anterior cingulate, that part of the brain discussed in the chapter on depression. The tegmentum accumbens dopamine system seems to be about edgy, make-you-crazy-with-anticipation passion. 2 years later, it's the cingulate weighing in, mediating something akin perhaps to comfort and warmth, or maybe even a non-hyperventilating version of love. Stress and reward. So, the really good thing about being tickled is the anticipation of being tickled, the element of surprise and lack of control. In other words, we're back to where we started. When does a lack of control and predictability fuel dopamine release and a sense of anticipatory pleasure? And when is it the core of what makes psychological stress stressful? The key seems to be whether the uncertainty occurs in a benign or malevolent context. If it's the right person tickling you in that adolescent stage of being on the cusp of sexuality, maybe, just maybe, that tickling is going to be followed by something really good, like hand-holding. In contrast, if it's Slobodan Milosevic who is tickling you, maybe, just maybe, it will be followed up by his trying to ethnically cleanse you. If the context is one of you being at risk for getting shocked, the lack of predictability adds to the stress. If the context is one in which that special someone is likely to eventually say yes, her running hot and cold is all that's needed to start you off on a 50-year courtship. Part of what makes the Las Vegas world of gambling so addictive is the brilliant ways in which people are manipulated into thinking that the environment is a benign rather than malevolent one. The belief that the outcome is likely to be a good one, especially for someone as lucky and special as you, so long as you keep putting in those coins and pressing that lever. What makes for the benign sort of environment in which uncertainty is pleasurable rather than stressful? One key element is how long the experience goes on. Pleasurable lack of control is all about transience. It's not for nothing that roller coaster rides are 3 minutes rather than 3 weeks long. Another thing that biases toward uncertainty being pleasurable is if it comes bound within a larger package of control and predictability. No matter how real and viscerally gripping the scary movie may be, you still know that Anthony Perkins is stalking Janet Leigh, not you. No matter how wild and scary and unpredictable and exhilarating the bungee jumping is, it's still in the context of having assured yourself that these folks have a license from the bungee jumping safety police. This is the essence of play. You surrender some degree of control. Think of how a dog initiates play with another dog by crouching down, making himself smaller, more vulnerable and less in control. But it has to be within a larger context of safety. You don't roll over and expose your throat in play to someone you haven't sniffed over carefully. Time now to introduce some really unexpected neurochemistry that ties this all together. Glucocorticoids, those hormones which have been discovered at the scene of the crime for virtually all the stress-related pathology we've been learning about. Those same villainous glucocorticoids will trigger the release of dopamine from pleasure pathways. It's not some generic effect upon all the dopamine pathways in the brain, just the pleasure pathway. Most remarkably, Pier Vincenzo Piazza and Michel Lemole of the University of Bordeaux in France have shown that lab rats will even work in order to get infused with glucocorticoids, will lever press the exact amount needed to maximize the amount of dopamine released by the hormone. And what is the pattern of glucocorticoid exposure that maximized dopamine release? You can probably guess already. A moderate rise that doesn't go on for too long. As we've seen, experience severe and prolonged stress, and learning, synaptic plasticity, and immune defenses are impaired. As we saw, experience moderate and transient stress, and memory, synaptic plasticity, and immunity are enhanced. Same thing here. Experience severe and prolonged glucocorticoid exposure, and we've returned to Chapter 14. Dopamine depletion, dysphoria, and depression. But with moderate and transient glucocorticoid elevation, you release dopamine. And transient activation of the amygdala releases dopamine as well. Couple the glucocorticoid rise with the accompanying activation of the sympathetic nervous system, and you're also enhancing glucose and oxygen delivery to the brain. You feel focused, alert, alive, motivated, anticipatory. You feel great. We have a name for such transient stress. We call it stimulation. Adrenaline junkies. What does this tell us about the subset of people who thrive on stress and risk-taking? Who are most alive under circumstances that would ulcerate anyone else? These are the folks who push every envelope. They spend every last dollar in Monopoly, have furtive sex in public places, try out a new complicated recipe on important dinner guests, answer the ad in Soldier of Fortune. What's up with them? We can make some pretty informed guesses. Maybe they release atypically low amounts of dopamine. Or, as another version of the same problem, maybe they have versions of dopamine receptors that are atypically unresponsive to a dopamine signal. In that scenario, it's hard to just say no to some thrilling possibility when there's not a whole lot of pleasurable yeses in one's life, a point that we'll return to when considering substance abuse. Supporting this idea are some reports of atypical versions of dopamine receptors in people with addictive personalities. As another possibility, maybe the baseline of dopamine signaling is fine, but those transients of stimulation cause whopping great rises of dopamine, bigger anticipatory pleasure signals than in most other people. That would certainly encourage one to try the stuff again. There's yet another possibility. Experience something thrilling with the right intensity and duration, and dopamine is released in the pleasure pathway. End of experience, dopamine levels go back down to baseline. What if someone's brain happens not to be great at keeping up with dopamine reserves in the pleasure pathway? As a result, at the end of a stimulating increase in dopamine release, dopamine levels not only drop back to baseline, but to a smidgen below baseline. In other words, a little lower than where you started. What's the only solution, then, to counteract this mild dysphoria, this mild inability to anticipate pleasure? Find something else that's thrilling, and of necessity a bit riskier, in order to achieve the same dopamine peak of the prior time. Afterward, your baseline drops a bit lower, necessitating another and another stimulant, each one having to be bigger, in the search for the giddy heights of dopamine that you reached that first time. This is the essence of the downward ratcheting of addiction. Once, a long time ago, the 16-year-old Evel Knievel behind the steering wheel with his brand-new driver's permit, sped up to beat a red light, and got a bit of a buzz from this. He then discovered the next time doing it that it didn't feel quite as exciting. Addiction. There's an astonishing number of substances that different cultures have come up with that can cause you to be ruinously addicted, to compulsively take the substance despite negative consequences. The field of addiction research has long had to grapple with the sheer variety of these compounds, from the standpoint of understanding their effects on brain chemistry. Alcohol is very different from tobacco or cocaine, let alone trying to make sense of how things like gambling or shopping wind up being addictive. Amid this variety, though, there's a critical commonality, which is that these compounds all cause the release of dopamine in the ventral tegmentum nucleus accumbens pathway. Not all to the same extent. Cocaine, which directly causes the release of dopamine from those neurons, is extremely good at doing it. Other drugs which do so through intervening steps are much less potent. Alcohol, for example. But they all do to at least some extent. And in brain imaging studies of humans taking addictive drugs, the more subjectively pleasurable a person finds a particular exposure to a drug to have been, the more activation of that pathway. This certainly makes sense and defines an addictive substance. You anticipate how pleasurable it will be, and thus come back for more. But addictive substances are not only addictive, but also typically have the property of causing tolerance or habituation. In other words, you need increasing amounts of the stuff to get the same anticipatory oomph as before. The explanation lies in part with the magnitude of dopamine released by these compounds. Consider some of the sources of pleasure we have. Promotion at work, beautiful sunset, great sex, getting a parking spot where there's still time on the meter. They all release dopamine for most people. Same thing for a rat. Food for a hungry rat, sex for a horny one, and dopamine levels rise 50 to 100% in this pathway. But give the rat some cocaine, and there is a 1,000-fold increase in dopamine release. What's the neurochemical consequence of this tidal wave of dopamine? We considered a related version in Chapter 14. If someone always yells at you, you stop listening. If you flood a synapse with a gazillion times more of a neurotransmitter than is usually the case, the recipient neuron has to compensate by becoming less sensitive. No one is sure what the mechanism is for what's termed an opponent process that counteracts the dopamine blast. Maybe fewer dopamine receptors, maybe fewer of whatever the dopamine receptors connect to. But regardless of the mechanism, the next time, it is going to take even more dopamine release to have the same impact on that neuron. This is the addictive cycle of escalating drug use. Around this point, there is a transition in the process of addiction. Early on, addiction is about wanting the drug, anticipating its effects, and about how high those dopamine levels are when they're pouring out in a drug-induced state. In addition, the release of endogenous opiates around this time fuels that sense of wanting. It's about the motivation to get the reward of a drug. With time, there's the transition to needing the drug, which is about how low the dopamine lows are without the drug. The stranglehold of addiction is when it is no longer the issue of how good the drug feels, but how bad its absence feels. It's about the motivation to avoid the punishment of not having the drug. George Koob of the Scripps Research Institute has shown that when rats are deprived of a drug they are addicted to, there is a 10-fold increase in levels of CRH in the brain, particularly in pathways mediating fear and anxiety, such as in the amygdala. No wonder you feel so awful. Brain imaging studies of drug users at that stage show that viewing a film of actors pretending to use drugs activates dopamine pathways in the brain more than does watching porn films. This process emerges in the context of the uncertainty and intermittent reinforcement that we discussed earlier. You're pretty sure you've scraped together enough money. You're pretty sure you can find a dealer. You're pretty sure you won't get caught. You're pretty sure it will be good stuff. But still, there's that element of uncertainty amid the anticipation, and that stokes the addictiveness like crazy. So, this tells us something about the acquisition of addiction, the downward spiral of tolerance to the drug, and the psychological contexts in which those processes can occur. There's a last basic feature of addiction that needs to be discussed. Consider the rare individual who has beaten his addiction, left his demons behind, rebooted, and started a new life. It's been months, years, even decades since he's gone near the drug. But uncontrollable circumstances put him back where he always used the drug back when. Back on the same street corner, in that same music studio, back in the same overstuffed armchair near the bar in the country club. And the craving comes roaring back like it was yesterday. The capacity to induce that craving doesn't necessarily decline with time. As many drug abusers in that situation will say, it is as if they had never stopped using. This is the phenomenon of context-dependent relapse. The itch is stronger in some places than others, specifically in places that you associate with prior drug use. You can show the identical phenomenon in a lab rat. Get them addicted to some substance where they are willing to lever press like mad to get infused with the stuff. Stick them in a novel cage with a lever and you may get some lever pressing out of them. But put them back in a cage that they associate with the drug exposure, and they lever press like mad. And, as with humans, the potential for relapse doesn't necessarily decrease over time. This process of associating drug use with a particular setting is a type of learning, and a lot of current addiction research explores the neurobiology of such learning. This work focuses not so much on those dopamine neurons, but on the neurons that project to them. Many of them come from cortical and hippocampal regions that carry information about setting. If you repeatedly use a drug in the same setting, those projections onto those dopamine neurons are repeatedly activated and eventually become potentiated, strengthened, in the same ways as the hippocampal synapses we learned about in Chapter 10. When those projections get strong enough, if you return to that setting, the dopamine anticipation of the drug gets triggered merely by the context. In a lab rat in this situation, you don't even need to place the animal back into the same setting. Just electrically stimulate those pathways that project onto the dopamine neurons, and you reinstate the drug craving. As goes one of the cliches of addiction, there's really no such thing as an ex-addict. It is simply an addict who is not in the context that triggers use. Stress and substance abuse. We are finally in a position to consider the interactions between stress and drug abuse. We begin by considering what taking any of various psychostimulant drugs does to the stress response. And everyone knows the answer to that one. I'm not feeling any pain. Drugs of abuse make you feel less stressed. In general, the evidence is pretty decent for this, given a few provisos. People do generally report themselves as feeling less stressed, less anxious, if a stressor occurs after some psychoactive drug's effects have kicked in. Alcohol is best known for this, and is formally termed an anxiolytic, a drug that lisses or disintegrates anxiety. You can show this with a lab rat. As discussed in the last chapter, rats hug the dark corners when put into a brightly lit cage. Put a hungry rat in a cage with some food in the brightly lit center, and how long does it take to overcome its anxious conflict and go for the food? Alcohol decreases the time to do this, as do many other addictive compounds. How does this work? Many drugs, including alcohol, raise glucocorticoid levels when they are first taken. But with more sustained use, various drugs can blunt the nuts and bolts of the stress response. Alcohol, for example, has been reported in some cases to decrease the extent of sympathetic nervous system arousal and to dampen CRH-mediated anxiety. In addition, drugs may change the cognitive appraisal of the stressor. What does that jargon mean? Basically, if you're in such a mess of an altered state that you can barely remember what species you are, you may not pick up on the subtle fact that something stressful has occurred. Intrinsic in that explanation is the downside of the anxiety-reducing consequences of getting wasted. As the blood levels of the drug drop, as the effects wear off, the cognition and reality sneak back in, and if anything, the drugs become just the opposite, become anxiety-generating. The dynamics of many of these drugs in the body is such that the amount of time that blood levels are rising, with their stress-reducing effects, is shorter than the amount of time that they are dropping. So, what's the solution? Drink, ingest, inhale, shoot up, snort all over again. So, various psychostimulants can decrease stress responses, secondary to blunting the machinery of the stress response, plus making you such a disoriented mess that you don't even notice that there's been a stressor. How about the flip side of this relationship? What does stress have to do with the likelihood of taking and abusing drugs? The clear punchline is that stress pushes you toward more drug use and a greater chance of relapse, although it's not completely clear how stress does this. The first issue is the effect of stress on initially becoming addicted. Set up a rat in a situation where if it presses a lever X number of times, it gets infused with some potentially addictive drug. Alcohol, amphetamines, cocaine. Remarkably, only some rats get into this self-administration paradigm enough to get addicted, and we'll see shortly which rats are more likely. If you stress a rat just before the start of this session of drug exposure, it is now more likely to self-administer to the point of addiction. And just as you'd expect from Chapter 13, unpredictable stress drives a rat toward addiction more effectively than does predictable stress. Similarly, put a rat or a monkey in a position of being socially subordinate, and the same increased risk occurs. And, no surprise, stress clearly increases alcohol consumption in humans as well. Importantly, stress increases the addictive potential of a drug only if the stressor comes right before the drug exposure. In other words, short-term stress, the type that boosts dopamine levels transiently. Why does stress have this effect? Imagine that you go into a bout of exposure to a novel, potentially addictive drug, and you just happen to be the type of rat or human for whom the drug doesn't do a whole lot. You're not releasing much dopamine or the other neurotransmitters involved. You're not getting this anticipatory sense afterward of wanting to do it again. But couple that same ho-hum dopamine rise with a rise due to stress and, whoa, you erroneously decide that something cosmic has just happened. Where can you get some more? Thus, acute stress increases the reinforcing potential of a drug. All that makes sense, but naturally, things get more complicated. Stress increases the likelihood of self-administering a drug to an addictive extent, but this time we're talking about stress during childhood, or even as a fetus. Stress a pregnant rat, and her offspring will have an increased propensity for drug self-administration as adults. Give a rat an experimentally induced birth complication by briefly depriving it of oxygen at birth, and you produce the same. Ditto if stressing a rat in its infancy. The same works in non-human primates. Separate a monkey from its mother during development, and that animal is more likely to self-administer drugs as an adult. The same has been shown in humans. In these instances, the stressor causing development can't be working merely by causing a transient rise in dopamine release. Something long-term has to be occurring. We're back in Chapter 6, and perinatal experiences causing lifelong programming of the brain and body. It's not clear how this works in terms of addictive substances, other than that there obviously has to be a permanent change in the sensitivity of the reward pathways. What about once the addiction has occurred? What does ongoing stress do to the extent of abuse? No surprise, it increases it. How does this work? Maybe because of transient suppressors briefly boosting dopamine levels and giving the drug more oomph. But by now, the main point for the addict may not be about wanting the high, as much as needing to avoid the low of drug withdrawal. As noted, during this time, levels of anxiety-mediating CRH are way up in the amygdala. Moreover, glucocorticoid secretion is constantly elevated during withdrawal, into the range where it depletes dopamine. And what happens if you add additional stress on top of that? All that the extra glucocorticoids can do in this scenario is make the dopamine depletion even worse, thus increasing the craving for that drug-induced boost of dopamine. What about that rare individual who manages to stop abusing whatever drug she's addicted to and successfully goes on the wagon? Stress increases the odds of her relapsing into drug use. As usual, the same is true in rats. Get a rat who is self-administering a drug by lever pressing to the point of addiction. Now, switch the rat to being infused with saline instead of with the drug. Soon the lever pressing extinguishes. The rat gives up on it, won't bother with the lever anymore. Sometime later, return the rat to that cage with the drug-associated lever, and there's an increased likelihood that the rat will try lever pressing for the drug again. Infuse the rat with a bit of the drug just before returning it to that familiar locale, and it's even more likely to start self-administering again. You've reawakened the taste for that drug. If you stress the rat right before you return it to the cage, it's even more likely to restart the drug use. As usual, unpredictable and uncontrollable stressors are the ones that really revive the drug use. And as usual, the human studies show basically the same thing. How does stress do this? It's not entirely clear. The effects of glucocorticoids on dopamine release may be relevant, but I have not seen a clear model built around their interaction. Maybe it's the stress-induced increase in sympathetic arousal, mediated by CRH in the amygdala. There's also some evidence suggesting that stress will increase the strength of those associative projections into the pleasure pathway. Perhaps it has something to do with stress impairing the functioning of the frontal cortex, which normally has that sensible restraining role of gratification postponement and decision-making. Shut down your frontal cortex, and suddenly you have what seems like an irresistibly clever idea. I know. Why don't I start taking that drug again which nearly destroyed my life? So, stress can increase the odds of abusing a drug to the point of addiction in the first place, make withdrawal harder, and make relapse more likely. Why do all the above happen more readily to some people than others? Immensely interesting work by Piazza and Lemol has started to answer this. Remember those apples and pears in Chapter 5? Who are the individuals who are more prone toward putting on fat around their gut, becoming apples, the less healthy version of fat deposition? We saw that they are likely to be people with more of a tendency to secrete glucocorticoids in response to stressors, and to have a slower recovery from such a stress response. Same thing here. Which rats are most likely to self-administer when given a chance? And once self-administering, do so to the point of escalating addiction? The ones who are high reactors, who are most behaviorally disrupted by being placed in a novel environment, who are more reactive to stress. They secrete glucocorticoids longer than the other rats in response to a stressor, causing them to pour out more dopamine when they are first exposed to the drug. So, if you're the kind of rat who is particularly thrown out of kilter by stress, you're atypically likely to try something that temporarily promises to make things right. The realm of synthetic pleasure. Chapter 13 raised the important point that positive and negative affect are not mere opposites of each other, and that they can independently influence one's risk of depression. Addiction maps onto this point well, in that an addiction can broadly serve two dissociable functions. One involves positive affect. Drugs can generate pleasure, albeit with an ultimate cost that offsets the transient rewards. The other function concerns negative affect. Drugs can be used to try to self-medicate away pain, depression, fear, anxiety, and stress. This dual purpose transitions us to the next chapter, with its theme that society does not evenly distribute healthy opportunities for pleasure, or sources of fear and anxiety. It is hard to just say no when life demands a constant vigilance, and when there are few other things to which to say yes. The premise of this book is that we humans, especially we westernized humans, have come up with some pretty strange sources of negative emotions. Worrying about and being saddened by purely psychological events that are displaced over space and time. But we westernized humans have also come up with some strange sources of positive emotions. Once, during a concert of cathedral organ music, as I sat there amid that tsunami of sound, getting gooseflesh, I was struck with a thought. Way back when, for a medieval peasant, this must have been the loudest human-made sound they would ever experience, something that would be awe-inspiring in ways we can no longer imagine. No wonder they signed up for the religion being proffered. And now we are constantly pummeled with sounds that dwarf quaint cathedral organs. Once, hunter-gatherers might chance upon a gold mine, honey from a wild beehive, and thus would briefly satisfy one of our most hardwired food cravings. Now we have hundreds of carefully engineered, designed, and marketed commercial foods, filled with rapidly absorbed processed sugars, that cause a burst of sensation that can't be matched by some lowly natural food. Once we had lives that, amid considerable privation and negatives, also offered a huge array of subtle and often hard-won pleasures. And now we have drugs that cause spasms of pleasure and dopamine 1,000-fold higher than anything stimulated in our drug-free world. Peter Sterling, of allostasis fame, has written brilliantly about how our sources of pleasure have become so narrowed and artificially strong. His thinking centers around the fact that our anticipatory pleasure pathway is stimulated by many different things. For this to work, the pathway must really habituate, must desensitize to any given source that has stimulated it, so that it is prepared to respond to the next stimulant. But unnaturally strong explosions of synthetic experience and sensation and pleasure evoke unnaturally strong degrees of habituation. This has two consequences. As the first, soon we hardly notice any more the fleeting whispers of pleasure caused by leaves in autumn, or by the lingering glance of the right person, or by the promise of reward that will come after a long, difficult, and worthy task. The other consequence is that, after a while, we even habituate to those artificial deluges of intensity and momentness. If we were nothing but machines of local homeostatic regulation, as we consume more, we would desire less. But instead, our tragedy is that we just become hungrier, more and faster and stronger. Now isn't as good as it used to be, and won't suffice tomorrow. Chapter 17. The View from the Bottom. Toward the end of the first chapter, I voiced a caveat. When I discuss a way in which stress can make you sick, that is merely shorthand for discussing how stress can make you more likely to get diseases that make you sick. That was basically a first pass at a reconciliation between two very different camps that think about poor health. At one extreme, you have the mainstream medical crowd that is concerned with reductive biology. For them, poor health revolves around issues of bacteria, viruses, genetic mutations, and so on. At the other extreme are the folks anchored in mind-body issues, for whom poor health is about psychological stress, lack of control and efficacy, and so on. A lot of this book has as one of its goals tried to develop further links between those two viewpoints. This has come in the form of showing how sensitive reductive biology can be to some of those psychological factors, and exploring the mechanisms that account for this. And it has come in the form of criticizing the extremes of both camps. On the one hand, trying to make clear how limiting it is to believe that humans can ever be reduced to a DNA sequence, and on the other, trying to indicate the damaging idiocy of denying the realities of human physiology and disease. The ideal resolution harks back to the wisdom of Herbert Wiener, as discussed in Chapter 8, that disease, even the most reductive of diseases, cannot be appreciated without considering the person who is ill. Terrific, we're finally getting somewhere. But this analysis, and most sections of this book up until now, have left out a third leg in this stool. The idea that poor health also has something to do with poor jobs in a shrinking economy, or a diet funded by food stamps with too many meals consisting of Coke and Cheetos, or living in a crummy, overcrowded apartment close to a toxic waste dump, or without enough heat in winter, let alone living on the streets or in a refugee camp or a war zone. If we can't consider disease outside the context of the person who is ill, we also can't consider it outside the context of the society in which that person has gotten ill, and that person's place in that society. I recently found support for this view in an unexpected corner. Neuroanatomy is the study of the connections between different areas of the nervous system, and it can sometimes seem like a mind-numbing form of stamp collecting. Some multisyllabically named part of the brain sends its axons in a projection with another multisyllabic name to 18 multisyllabic target sites, whereas in the next county over in the brain. During a period of my errant youth, I took particular pleasure in knowing as much neuroanatomy as possible. The more obscure, the better. One of my favorite names was that given to a tiny space that exists between two layers of the meninges, the tough fibrous wrapping found around the brain. It was called the Virchow-Robin space, and my ability to toss off that name won me the esteem of my fellow neuroanatomy dorks. I never figured out who Robin was, but Virchow was Rudolf Virchow, a 19th century German pathologist and anatomist. Man, to be honored by having your name attached to some microscopic space between two layers of saran brain wrap. This guy must have been the king of reductive nuts and bolts science to merit that. I bet he even wore a monocle, which he'd remove before peering down a microscope. And then I found out a bit about Rudolf Virchow. As a young physician, he came of age with two shattering events: a massive typhus outbreak in 1847 that he attempted to combat firsthand, and the doomed European revolutions of 1848. The first was the perfect case for teaching that disease can be as much about appalling living conditions as it is about microorganisms. The second taught just how effectively the machinery of power can subjugate those in appalling living conditions. In its aftermath, he emerged not just as someone who was a scientist plus a physician, plus a public health pioneer, plus a progressive politician. That would be plenty unique. But in addition, through a creative synthesis, he saw all those roles as manifestations of a single whole. Medicine is a social science, and politics nothing but medicine on a large scale, he wrote. And physicians are the natural attorneys of the poor. This is an extraordinarily large vision for a man getting microscopic spaces named for him. And unless one happens to be a very atypical physician these days, this vision must also seem extraordinarily quaint, as sadly quaint as Picasso thinking he could throw some paint on a canvas, call it Guernica, and do something to halt fascism. The history of status thymicolymphaticus, the imaginary disease of a supposedly enlarged thymus gland in infants, detailed at the end of Chapter 8, taught us that your place in society can leave its imprint on the corpse you eventually become. The purpose of this chapter is to show how your place in society, and the sort of society it is, can leave an imprint on patterns of disease while you are alive, and to show that part of understanding this imprint incorporates the notion of stress. This will be preparatory for an important notion to be discussed in the final chapter on stress management, that certain techniques for reducing stress work differently depending on where you dwell in your society's hierarchy. A strategy that I've employed in a number of chapters is to introduce some phenomenon in the context of animals, often social primates. This has been in order to show some principle in a simplified form before turning to the complexity of humans. I do the same in this chapter, beginning with a discussion of what social rank has to do with health and stress-related diseases among animals. But this time, there is a paradoxical twist that by the end of this chapter should seem depressing as hell. This time, it is we humans who provide a brutally simple version, and our non-human primate cousins the nuance and subtlety. Pecking orders among beasts with tails. While pecking orders, dominance hierarchies, might have first been discerned among hens, they exist in all sorts of species. Resources, no matter how plentiful, are rarely divvied up evenly. Instead of every contested item being fought for with bloodied tooth and claw, dominance hierarchies emerge. As formalized systems of inequities, these are great substitutes for continual aggression between animals smart enough to know their place. Hierarchical competition has been taken to heights of animal complexity by primates. Consider baboons, the kind running around savannas in big social groups of 100 or so beasts. In some cases, the hierarchy can be fluid, with ranks changing all the time. In other cases, rank is hereditary and lifelong. In some cases, rank can depend on the situation. A outranks B when it comes to a contested food item, but the order is reversed if it is competition for someone of the opposite sex. There can be circularities in hierarchies. A defeats B, defeats C, defeats A. Ranking can involve coalitional support. B gets trounced by A, unless receiving some well-timed help from C, in which case A is sent packing. The actual confrontation between two animals can include anything ranging from a near-fatal brawl to a highly dominant individual doing nothing more than shifting menacingly and giving subordinates the willies. Regardless of the particulars, if you're going to be a savanna baboon, you probably don't want to be a low-ranking one. You sit there for 2 minutes digging some root out of the ground to eat, clean it off, and anyone higher ranking can rip it off from you. You spend hours sweet-talking someone into grooming you, getting rid of those bothersome thorns and nettles and parasites in your hair, and the grooming session can be broken up by someone dominant just for the sheer pleasure of hassling you. Or you could be sitting there minding your own business bird-watching, and some high-ranking guy having a bad day decides to make you pay for it by slashing you with his canines. Such third-party displacement aggression accounts for a huge percentage of baboon violence. A middle-aged ranking male gets trounced in a fight, turns and chases a sub-adult male, who lunges at an adult female, who bites a juvenile who slaps an infant. For a subordinate animal, life is filled with a disproportionate share not only of physical stressors, but of psychological stressors as well. Lack of control, of predictability, of outlets for frustration. It's not surprising, then, that among subordinate male baboons, resting levels of glucocorticoids are significantly higher than among dominant individuals. For a subordinate, everyday basal circumstances are stressful. And that's just the start of subordinates' problems with glucocorticoids. When a real stressor comes along, their glucocorticoid response is smaller and slower than in dominant individuals. And when it's all past, their recovery appears to be delayed. All these are features that count as an inefficient stress response. More problems for subordinate individuals. Elevated resting blood pressure, sluggish cardiovascular response to real stressors, a sluggish recovery, suppressed levels of the good HDL cholesterol. Among male subordinates, testosterone levels that are more easily suppressed by stress than in dominant males, fewer circulating white blood cells, and lower circulating levels of something called insulin-like growth factor I, which helps heal wounds. As should be clear by now, all of these are indices of bodies that are chronically stressed. A chronically activated stress response, elevated glucocorticoid levels, or resting blood pressure that is too high, or an enhanced risk of atherosclerosis, appears to be a marker of being low-ranking in lots of other animal species as well. This occurs in primates ranging from standard-issue monkeys like rhesus to beasts called prosimians, such as mouse lemurs. Same for rats, mice, hamsters, guinea pigs, wolves, rabbits, pigs, even fish, even sugar gliders, whatever they might be. A critical question. I'm writing as if being low-ranking and subject to all those physical and psychological stressors chronically activates the stress response. Could it be the other way around? Could having a second-rate stress response set you up for being low-ranking? You can answer this question with studies of captive animals, where you can artificially form a social group. Monitor glucocorticoid levels, blood pressure, and so on when the group is first formed, and again once rankings have emerged, and the comparison will tell you in which direction the causality works. Do physiological differences predict who is going to wind up with which rank, or is it the other way around? The answer overwhelmingly is that rank emerges first and drives the distinctive stress profile. So we've developed a pretty clear picture. Social subordination equals being chronically stressed equals an overactive stress response equals more stress-related disease. Now it's time to see why that's simplistic and wrong. The first hint is hardly a subtle one. When you stand up at some scientific meeting and tell about the health-related miseries of your subordinate baboons or tree shrews or sugar gliders, invariably some other endocrinologist who studies the subject in some other species gets up and says, "Well, my subordinate animals don't have high blood pressure or elevated glucocorticoid levels." There are lots of species in which social subordination is not associated with an overactive stress response. Why should that be? Why should being subordinate not be so bad in that species? The answer is, in that species, it's not so bad being subordinate, or possibly it's actually a drag being dominant. An example of the first is seen with a South American monkey called the marmoset. Being subordinate among them does not involve the misery of physical and psychological stressors. It isn't a case of subjugation being forcibly imposed on you by big, mean, dominant animals. Instead, it is a relaxed waiting strategy. Marmosets live in small social groups of related cooperative breeders, where being subordinate typically means you are helping out your more dominant older sibling or cousin and waiting your turn to graduate into that role. Commensurate with this picture, David Abbott at the Wisconsin Regional Primate Research Center has shown that subordinate marmosets don't have overactive stress responses. Wild dogs and dwarf mongooses provide examples of the second situation, in which subordination isn't so bad. Being dominant in those species doesn't mean a life of luxury, effortlessly getting the best of the pickings and occasionally endowing an art museum. None of that status quo stuff. Instead, being dominant requires the constant reassertion of high rank through overt aggression. One is tested again and again. As Scott and Nancy Creel at Montana State University have shown, it's not the subordinate animals among those species who have the elevated basal glucocorticoid levels. It's the dominant ones. Recently, Abbott and I drew on the collaborative efforts of a large number of colleagues who have studied rank stress physiology issues in non-human primates. We formalized what features of a primate society predict whether it is the dominant or the subordinate animals who have the elevated stress responses. To the experts on each primate species, we posed the same questions. In the species that you study, what are the rewards of being dominant? How much of a role does aggression play in maintaining dominance? How much grief does a subordinate individual have to take? What sources of coping and support, including the presence of relatives, do subordinates of that species have available to them? What covert alternatives to competition are available? If subordinates cheat at the rules, how likely are they to get caught, and how bad is the punishment? How often does the hierarchy change? Amid 17 questions asked concerning the dozen different species for which there are decent amounts of data available, the best predictors of elevated glucocorticoid levels among subordinate animals turn out to be if they are frequently harassed by dominant individuals, and if they lack the opportunities for social support. So, rank means different things in different species. It turns out that rank can also mean different things in different social groups within the same species. Primatologists these days talk about primate culture, and this is not an anthropomorphic term. For example, chimps in one part of the rainforest can have a very different culture from the folks 4 valleys over. Different frequencies of social behaviors, use of similar vocalizations but with different meanings. In other words, something approaching the concept of a dialect. Different types of tool use. And intergroup differences influence the rank-stress relationship. One example is found among female rhesus monkeys, where subordinates normally take a lot of grief and have elevated basal glucocorticoid levels. Except in one social group that was studied, which for some reason had high rates of reconciliatory behaviors among animals after fights. The same is found in a baboon troop that just happened to be a relatively benign place to be a low-ranking individual. Another example concerns male baboons where, as noted, subordinates normally have the elevated glucocorticoid levels. Except during a severe drought, when the dominant males were so busy looking for food that they didn't have the time or energy to hassle everyone else, implying, ironically, that for a subordinate animal, an environmental stressor can be a blessing, insofar as it saves you from a more severe social stressor. A critical intergroup difference in the stress response concerns the stability of the dominance hierarchy. Consider an animal who is, say, number 10 in the hierarchy. In a stable system, that individual is getting trounced 95% of the time by number 9, but in turn thrashes number 11 95% of the time. In contrast, if number 10 were winning only 51% of interactions with number 11, that suggests that the two may be close to switching positions. In a stable hierarchy, 95% of the interactions up and down the ranks reinforce the status quo. Under those conditions, dominant individuals are stably entrenched and have all the psychological perks of their position, control, predictability, and so on. And under those conditions, among the various primate species I've discussed, it is the dominant individuals who have the healthiest stress responses. In contrast, there are rare periods when the hierarchy becomes unstable. Some key individual has died. Someone influential has transferred into the group. Some pivotal coalitional partnership has formed or come apart. And a revolution results, with animals changing ranks left and right. Under those conditions, it is typically the dominant individuals who are in the very center of the hurricane of instability, subject to the most fighting, the most challenges, and who are most affected by the seesawing of coalitional politics. During such unstable periods among those same primate species, the dominant individuals no longer have the healthiest stress responses. So while rank is an important predictor of individual differences in the stress response, the meaning of that rank, the psychological baggage that accompanies it in a particular society, is at least as important. Another critical variable is an animal's personal experience of both its rank and society. For example, consider a period when an immensely aggressive male has joined a troop of baboons and is raising hell, attacking animals unprovoked left and right. One might predict stress responses throughout the troop, thanks to this destabilizing brute. But instead, the pattern reflects the individual experience of animals. For those lucky enough never to be attacked by this character, there were no changes in immune function. In contrast, among those attacked, the more frequently that particular baboon suffered at this guy's teeth, the more immunosuppressed she was. Thus, you ask the question, what are the effects of an aggressive, stressful individual on immune function in a social group? The answer is, it depends. It's not the abstract state of living in a stressful society which is immunosuppressive. Instead, it is the concrete state of how often your own nose is being rubbed in that instability. As a final variable, it is not just rank that is an important predictor of the stress response, not just the society in which the rank occurs, or how a member of the society experiences both. It's also personality, the topic of Chapter 15. As we saw, some primates see glasses as half empty and life as full of provocations, and they can't take advantage of outlets or social support. Those are the individuals with overactive stress responses. For them, their rank, their society, their personal experiences might all be wonderfully salutary, but if their personality keeps them from perceiving those advantages, their hormone levels and arteries and immune systems are going to pay a price. All things considered, this presents a pretty subtle picture of what social rank has to do with stress-related disease among primates. It's reasonable to expect the picture to be that much more complicated and subtle when considering humans. Time for a surprise. Do humans have ranks? I personally was always picked last for the wiffle ball team as a kid, being short, uncoordinated, and typically preoccupied with some book I was lugging around. Thus, having been perpetually ensconced at the bottom of that pecking order, I am skeptical about the notion of ranking systems for humans. Part of the problem is definitional, in that some supposed studies of human dominance are actually examining type A features. People defined as dominant are ones who, in interviews, have hostile competitive contents to their answers, or who speak quickly and interrupt the interviewer. This is not dominance in a way that any zoologist would endorse. Other studies have examined the physiological correlates of individual differences in humans who are competing directly against one another in a way that looks like dominance. Some have examined, for example, the hormonal response in college wrestlers, depending on whether they won or lost their match. Others have examined the endocrine correlates of rank competition in the military. One of the most fruitful areas has been to examine ranks in the corporate world. Chapter 13 showed how the executive stress syndrome is mostly a myth. People at the top give ulcers rather than get them. Most studies have shown that it is middle management that succumbs to the stress-related diseases. This is thought to reflect the killer combination that these folks are often burdened with, namely, high work demands but little autonomy, responsibility without control. Collectively, these studies have produced some experimentally reliable correlations. I'm just a bit dubious as to what they mean. For starters, I'm not sure what a couple of minutes of competitive wrestling between two highly conditioned 20-year-olds teaches us about which 60-year-old gets clogged arteries. At the other end, I wonder what the larger meaning is of rankings among business executives. While primate hierarchies can ultimately indicate how hard you have to work for your calories, corporate hierarchies are ultimately about how hard you have to work for, say, a plasma TV. Another reason for my skepticism is that for 99% of human history, societies were most probably strikingly unhierarchical. This is based on the fact that contemporary hunter-gatherer bands are remarkably egalitarian. But my skepticism is most strongly anchored in two reasons, having to do with the complexity of the human psyche. First, humans can belong to a number of different ranking systems simultaneously, and ideally are excelling in at least one of them, and thus may be giving the greatest psychological weight to that one. So, the lowly subordinate in the mailroom of the big corporation may, after hours, be deriving tremendous prestige and self-esteem from being the deacon of his church, or the captain of her weekend softball team, or maybe at the top of the class at the adult extension school. One person's highly empowering dominance hierarchy may be a mere 9-to-5 irrelevancy to the person in the next cubicle, and this will greatly skew results. And most important, people put all sorts of spin inside their heads about ranks. Consider a marathon being observed by a Martian scientist studying physiology and rank in humans. The obvious thing to do is keep track of the order in which people finish the race. Runner 1 dominates 5, who clearly dominates 5,000. But what if runner 5,000 is a couch potato who took up running just a few months ago, who half expected to keel over from a coronary by mile 13, and instead finished? Sure, hours after the crowds wandered off, but finished, exhausted and glowing. And what if runner 5 had spent the previous week reading in the sports section that someone of their world-class quality should certainly finish in the top 3, maybe even blow away the field? No Martian on Earth could predict correctly who is going to feel exultantly dominant afterwards. People are as likely to race against themselves, their own previous best time, as against some external yardstick. This can be seen in the corporate world as well. An artificial example. The kid in the mailroom is doing a fabulous job and is rewarded implausibly with a $50,000 a year salary. A senior vice president screws up big time and is punished even more implausibly with a $50,001 a year salary. By the perspective of that Martian, or even by a hierarchically minded wildebeest, it's obvious that the vice president is in better shape to acquire the nuts and berries needed for survival. But you can guess who is going to be going to work contentedly and who is going to be making angry phone calls to a headhunter from the cell phone in the BMW. Humans can play internal, rationalizing games with rank based on their knowledge of what determined their placement. Consider the following fascinating example. Guys who win at some sort of competitive interaction typically show at least a small rise in their circulating testosterone levels, unless they consider the win to have come from sheer luck. When you put all those qualifiers together, I think the net result is some pretty shaky ground when it comes to considering human rank and its relevance to the stress response. Except in one realm. If you want to figure out the human equivalent of being a low-ranking social animal, an equivalent that carries with it atypically high rates of physical and psychological stressors, which is ecologically meaningful in that it's not just about how many hours you have to work to buy an iPod, which is likely to overwhelm most of the rationalizations and alternative hierarchies that one can muster. Check out a poor human. Socioeconomic status, stress, and disuse. If you want to see an example of chronic stress, study poverty. Being poor involves lots of physical stressors, manual labor, and a greater risk of work-related accidents. Maybe even 2 or 3 exhausting jobs, complete with chronic sleep deprivation. Maybe walking to work, walking to the laundromat, walking back from the market with a heavy bag of groceries instead of driving an air-conditioned car. Maybe too little money to afford a new mattress that might help that aching back, or some more hot water in the shower for that arthritic throb. And of course, maybe some hunger thrown in as well. The list goes on and on. Naturally, being poor brings disproportionate amounts of psychological stressors as well. Lack of control, lack of predictability, numbing work on an assembly line, an occupational career spent taking orders or going from one temporary stint to the next. The first one laid off when economic times are bad. And studies show that the deleterious effects of unemployment on health begin not at the time the person is laid off, but when the mere threat of it first occurs. Wondering if the money will stretch to the end of the month. Wondering if the rickety car will get you to tomorrow's job interview on time. How's this for an implication of lack of control? One study of the working poor showed that they were less likely to comply with their doctor's orders to take antihypertensive diuretics, drugs that lower blood pressure by making you urinate, because they weren't allowed to go to the bathroom at work as often as they needed to when taking the drugs. As a next factor, being poor means that you often can't cope with stressors very efficiently. Because you have no resources in reserve, you can never plan for the future and can only respond to the present crisis. And when you do, your solutions in the present come with a whopping great price later on. Metaphorically, or maybe not so metaphorically, you're always paying the rent with money from a loan shark. Everything has to be reactive, in the moment, which increases the odds that you'll be in even worse shape to deal with the next stressor. Growing strong from adversity is mostly a luxury for those who are better off. Along with all of that stress and reduced means of coping, poverty brings with it a marked lack of outlets. Feeling a little stressed with life and considering a relaxing vacation, buying an exercycle, or taking some classical guitar lessons to get a little peace of mind? Probably not. Or how about quitting that stressful job and taking some time off at home to figure out what you're doing with your life? Not when there's an extended family counting on your paycheck and no money in the bank. Feeling like at least jogging regularly to get some exercise and let off some steam? Statistically, a poor person is far more likely to live in a crime-riddled neighborhood, and jogging may wind up being a hair-raising stressor. Finally, along with long hours of work and kids to take care of, comes a serious lack of social support. If everyone you know is working 2 or 3 jobs, you and your loved ones, despite the best of intentions, aren't going to be having much time to sit around being supportive. Thus, poverty generally equals more stressors. And though the studies are mixed as to whether or not the poor have more major catastrophic stressors, they have plenty more chronic daily stressors. All these hardships suggest that low socioeconomic status, SES, typically measured by a combination of income, occupation, housing conditions, and education, should be associated with chronic activation of the stress response. Only a few studies have looked at this, but they support this view. One concerned school kids in Montreal, a city with fairly stable communities and low crime. In 6- and 8-year-old children, there was already a tendency for lower SES kids to have elevated glucocorticoid levels. By age 10, there was a stepwise gradient, with low SES kids averaging almost double the circulating glucocorticoids as the highest SES kids. Another example concerns people in Lithuania. In 1978, men in Lithuania, then part of the USSR, had the same mortality rate for coronary heart disease as did men in nearby Sweden. By 1994, following the disintegration of the Soviet Union, Lithuanians had 4 times the Swedish rate. In 1994, Sweden, SES was not related to glucocorticoid levels, whereas in 1994 Lithuania, it was strongly related. Findings like these suggest that being poor is associated with more stress-related diseases. As a first pass, let's just ask whether low SES is associated with more diseases, period. And is it ever? The health risk of poverty turns out to be a huge effect, the biggest risk factor there is in all of behavioral medicine. In other words, if you have a bunch of people of the same gender, age, and ethnicity, and you want to make some predictions about who is going to live how long, the single most useful fact to know is each person's SES. If you want to increase the odds of living a long and healthy life, don't be poor. Poverty is associated with increased risks of cardiovascular disease, respiratory disease, ulcers, rheumatoid disorders, psychiatric diseases, and a number of types of cancer, just to name a few. It is associated with higher rates of people judging themselves to be of poor health, of infant mortality, and of mortality due to all causes. Moreover, lower SES predicts lower birth weight after controlling for body size, and we know from Chapter 6 the lifelong effects of low birth weight. In other words, be born poor but hit the lottery when you're 3 weeks old, spend the rest of your life double dating with Donald Trump, and you're still going to have a statistical increase in some realms of disease risk for the rest of your life. Is the relationship between SES and health just some little statistical hiccup in the data? No. It can be a huge effect. In the case of some of those diseases sensitive to SES, if you cling to the lowest rungs of the socioeconomic ladder, it can mean 10 times the prevalence compared with those perched on top. Or, stated another way, this translates into a 5 to 10 year difference in life expectancy in some countries when comparing the poorest and wealthiest, and decades worth of differences when comparing subgroups of the poorest and wealthiest. Findings such as these can go back centuries. For example, one study of men in England and Wales demonstrated a steep SES gradient in mortality in every decade of the 20th century. This has a critical implication that has been pointed out by Robert Evans of the University of British Columbia. The diseases that people were dying of most frequently a century ago are dramatically different from the most common ones now. Different causes of death, but same SES gradient, same relationship between SES and health, which tells you that the gradient arises less from disease than from social class. Thus, writes Evans, the roots of the SES health gradient lie beyond the reach of medical therapy. So, SES and health are tightly linked. What direction is the causality? Maybe being poor sets you up for poor health. But maybe it's the other way around, where being sickly sets you up for spiraling down into poverty. The latter certainly happens, but most of the relationship is due to the former. This is demonstrated by showing that your SES at one point in life predicts important features of your health later on. For example, poverty early in life has adverse effects on health forever after, harking back to Chapter 6 and the fetal origins of adult disease. One remarkable study involved a group of elderly nuns. They took their vows as young adults and spent the rest of their lives sharing the same diet, same health care, same housing, and so on. Despite controlling for all these variables, in old age their patterns of disease, of dementia, and of longevity were still predicted by the SES status they had when they became nuns more than half a century before. Thus, SES influences health, and the greater cumulative percentage of your life you've spent poor, the more of an adverse impact on health. Why should SES influence health? A century ago in the United States, or today in a developing country, the answer would be obvious. It would be about poor people getting more infectious diseases, less food, and having an astronomically higher infant mortality rate. But with our shift toward the modern prevalence of slow degenerative diseases, the answers have shifted as well. The puzzle of healthcare access. Let's start with the most plausible explanation. In the United States, poor people, with or without health insurance, don't have the same access to medical care as do the wealthy. This includes fewer preventive checkups with doctors, a longer lag time for testing when something bothersome has been noted, and less adequate care when something has actually been discovered, especially if the medical care involves an expensive, fancy technique. As one example of this, a 1967 study showed that the poorer you are judged to be, based on the neighborhood you live in, your home, your appearance, the less likely paramedics are to try to revive you on the way to the hospital. In more recent studies, for the same severity of a stroke, SES influenced your likelihood of receiving physical, occupational, or speech therapy, and how long you waited until undergoing surgery to repair the damaged blood vessel that caused the stroke. This sure seems like it should explain the SES gradient, make the healthcare system equitable, socialize that medicine, and away would go that gradient. But it can't be only about differential healthcare access, or even mostly about it. For starters, consider countries in which poverty is robustly associated with increased prevalence of disease. Australia, Belgium, Denmark, Finland, France, Italy, Japan, the Netherlands, New Zealand, the former Soviet Union, Spain, Sweden, the United Kingdom, and, of course, the US of A. Socialize the medical care system, socialize the whole country, turn it into a worker's paradise, and you still get the gradient. In a place like England, the SES gradient has gotten worse over this century, despite the imposition of universal health care allowing everyone equal health care access. You could cynically and correctly point out that systems of wonderfully egalitarian health care access are probably egalitarian in theory only. Even the Swedish healthcare system is likely to be at least a smidgen more attentive to the wealthy industrialist, sick doctor, or famous jock than to some no-account poor person cluttering up a clinic. Some people always get more of their share of equality than others. But in at least one study of people enrolled in a prepaid health plan, where medical facilities were available to all participants, poorer people had more cardiovascular disease, despite making more use of the medical resources. A second vote against the importance of differential health care access is because the relationship forms the term I've been using, namely a gradient. It's not the case that only poor people are less healthy than everyone else. Instead, for every step lower in the SES ladder, there is worse health, and the lower you get in the SES hierarchy, the bigger is each step of worsening health. This was a point made screamingly clear in the most celebrated study in the field, the Whitehall studies of Michael Marmot of University College of London. Marmot considered a system where gradations in SES status are so clear that occupational rank practically comes stamped on people's foreheads. The British civil service system, which ranges from unskilled blue-collar workers to high-powered executives. Compare the highest and lowest rungs, and there's a fourfold difference in rates of cardiac disease mortality. Remember, this is in a system where everyone has roughly equal health care access, is paid a living wage, and, very important in the context of the effects of unpredictability, is highly likely to continue to be able to earn that living wage. A final vote against the health care access argument. The gradient exists for diseases that have nothing to do with access. Take a young person and each day, scrupulously, give her a good medical examination. Check her vitals, peruse her blood, run her on a treadmill, give her a stern lecture about good health habits, and then, for good measure, centrifuge her a bit, and she is still just as much at risk for some diseases as if she hadn't gotten all that attention. Poor people are still more likely to get those access-proof diseases. Theodore Pincus of Vanderbilt University has carefully documented the existence of an SES gradient for two of those diseases, juvenile diabetes and rheumatoid arthritis. Thus, the leading figures in this field all seem to rule out healthcare access as a major part of the story. This is not to rule it out completely, let alone suggest that we not bother trying to establish universal healthcare access. As evidence, sweaty capitalist America has the worst gradient, while the socialized Scandinavian countries have the weakest. But they still have hefty gradients despite their socialism. The main cause has to be somewhere else. Thus, we move on to the next most plausible explanation. Risk factors and protective factors. Poor people in westernized societies are more likely to drink and smoke excessively. Sufficiently so that it's been remarked that smoking is soon going to be almost exclusively a low SES activity. These excesses take us back to the last chapter and having trouble just saying no when there are few yeses. Moreover, the poor are more likely to have an unhealthy diet. In the developing world, being poor means having trouble affording food, while in the westernized world, it means having trouble affording healthy food. Thanks to industrialization, fewer jobs in our society involve physical exertion, and when combined with the costs of membership in some Tony health club, the poor get less exercise. They are more likely to be obese, and in an Appleish way. They are less likely to use a seatbelt, wear a motorcycle helmet, own a car with airbags. They are more likely to live near a toxic dump, be mugged, have inadequate heat in the winter, live in crowded conditions, thereby increasing exposure to infectious diseases. The list seems endless, and they all adversely impact health. Being poor is statistically likely to come with another risk factor: being poorly educated. Thus, maybe poor people don't understand, don't know about the risk factors they are being exposed to, or the health-promoting factors they are lacking. Even if it is within their power to do something, they aren't informed. As one example that boggles me, substantial numbers of people are apparently not aware that cigarettes do bad things to you. And the studies show that these aren't folks too busy working on their doctoral dissertations to note some public health trivia. Other studies indicate that, for example, poor women are the least likely to know of the need for pap smears, thus increasing their risk for cervical cancer. The intertwining of poverty and poor education probably explains the high rates of poor people who, despite their poverty, could still be eating somewhat more healthfully, using seatbelts or crash helmets and so on, but don't. And it probably helps to explain why poor people are less likely to comply with some treatment regime prescribed for them that they can actually afford. They are less likely to have understood the instructions or to think that following them is important. Moreover, a high degree of education generalizes to better problem-solving skills across the board. Statistically, being better educated predicts that your community of friends and relatives is better educated as well, with those attendant advantages. However, the SES gradient isn't much about risk factors and protective factors. To show this requires some powerful statistical techniques in which you see if an effect still exists after you control for one or more of these factors. For example, the lower your SES, the greater your risk of lung cancer. But the lower your SES, the greater the likelihood of smoking. So control for smoking, comparing only people who smoke. Does the incidence of lung cancer still increase with declining SES? Take it one step further. For the same amount of smoking, does lung cancer incidence still increase? For the same amount of smoking and drinking, and so on. These types of analyses show that these risk factors matter. As Robert Evans has written, drinking sewage is probably unwise even for Bill Gates. They just don't matter that much. For example, in the Whitehall studies, smoking, cholesterol levels, blood pressure, and level of exercise explain away only about a third of the SES gradient. For the same risk factors and same lack of protective factors, throw in poverty and you're more likely to get sick. So, differential exposure to risk factors or protective factors does not explain a whole lot. This point is brought home in another way. Compare countries that differ in wealth. One can assume that being in a wealthier country gives you more opportunities to buy protective factors and to avoid risk factors. For example, you find the least pollution in very poor and very wealthy countries. The former because they are non-industrial, and the latter because they either do it cleanly or farm it out to someone else. Yet, when you consider the wealthiest quarter or so countries on Earth, there is no relationship between a country's wealth and the health of its citizens. This is a point heavily emphasized by Stephen Bezruchka of the University of Washington in considering the United States. Despite the most expensive and sophisticated healthcare system in the world, there's an unconscionable number of less wealthy nations whose citizens live longer, healthier lives than our own. So, out go major roles for healthcare access and risk factors. This is where things get tense at the scientific conferences. Much of this book has been about how a certain style of mainstream medicine, overly focused on how disease is exclusively about viruses, bacteria, and mutations, has grudgingly had to make room for the relevance of psychological factors, including stress. In a similar way, among the social epidemiologists who think about the SES health gradients, the mainstream view has long focused on healthcare access and risk factors, and thus they too have had to make room for psychological factors, including stress. Big time. Stress and the SES gradient. As discussed, the poor certainly have a hugely disproportionate share of both daily and major stressors. If you've gotten this far into this book and aren't wondering whether stress has something to do with the SES health gradient, you should get your money back. Does it? In the last edition of this book, I argued for a major role for stress based on 3 points. First, the poor have all those chronic daily stressors. Second, when one examines the SES gradient for individual diseases, the strongest gradients occur for diseases with the greatest sensitivity to stress, such as heart disease, diabetes, metabolic syndrome, and psychiatric disorders. Finally, once you've rounded up the usual suspects, healthcare access and risk factors, and ruled them out as being of prime importance, what else is there to pin the SES gradient on? Sunspots? Kind of flimsy. With that sort of evidence, the social epidemiologists were willing to let in some of those psychologists and stress psychologists, but through the back door, and, cook, find them something to eat in the kitchen, if you please. So that was the stress argument a half-decade back. But since then, striking new findings make the stress argument very solid. Being poor versus feeling poor. A central concept of this book is that stress is heavily rooted in psychology once you are dealing with organisms who aren't being chased by predators, and who have adequate shelter and sufficient calories to sustain good health. Once those basic needs are met, it is an inevitable fact that if everyone is poor, and I mean everyone, then no one is. In order to understand why stress and psychological factors have so much to do with the SES health gradient, we have to begin with the obvious fact that it is never the case that everyone is poor, thereby making no one poor. This brings us to a critical point in this field. The SES health gradient is not really about a distribution that bottoms out at being poor. It's not about being poor. It's about feeling poor, which is to say, it's about feeling poorer than others around you. Beautiful work regarding this has been carried out by Nancy Adler of the University of California at San Francisco. Instead of just looking at the relationship between SES and health, Adler looks at what health has to do with what someone thinks and feels their SES is, their subjective SES. Show someone a ladder with 10 rungs on it and ask them, in society, where on this ladder would you rank yourself in terms of how well you're doing? Simple. First off, if people were purely accurate and rational, the answers across a group should average out to the middle of the ladder's rungs. But cultural distortions come in. Expansive, self-congratulatory European Americans average out at higher than the middle rung, what Adler calls her Lake Wobegon effect, where all the children are above average. In contrast, Chinese Americans, from a culture with less chest-thumping individualism, average out to below the middle rung. So you have to correct for those biases. In addition, given that you're asking how people feel about something, you need to control for people who have an illness of feeling, namely depression. Once you've done that, look at what health measures have to do with one's subjective SES. Amazingly, it is at least as good a predictor of these health measures as is one's actual SES, and in some cases it is even better. Cardiovascular measures, metabolism measures, glucocorticoid levels, obesity in kids. Feeling poor in our socioeconomic world predicts poor health. This isn't really all that surprising. We can be an immensely competitive, covetous, invidious species, and not particularly rational in how we make those comparisons. Here's an example from a realm unrelated to this subject. Show a bunch of women volunteers a series of pictures of attractive female models, and afterward, they feel in a worse mood, with lower self-esteem than before seeing the pictures. And even more depressingly, show those same pictures to men, and afterward what declines is their stated satisfaction with their wives. So it's not about being poor, it's about feeling poor. What's the difference? Adler shows that subjective SES is built around education, income, and occupational position. In other words, the building blocks of subjective SES, plus satisfaction with standard of living and feeling of financial security about the future. Those last two measures are critical. Income may tell you something, but certainly not everything about SES. Satisfaction with standard of living is the world of people who are poor and happy, and zillionaires who are still grasping for more. All that messy stuff that dominates this book. And what is feelings about financial security tapping into? Anxiety. So, SES reality plus your satisfaction with that SES, plus your confidence about how predictable your SES is, are collectively better predictors of health than SES alone. This is not a hard and fast rule, and Adler's most recent work shows that subjective SES is not necessarily that great of a predictor in certain ethnic groups. Stay tuned for more, no doubt. But overall, this strikes me as immensely impressive. When you're past the realm of worrying about having adequate shelter and food, being poor is not as bad for you as feeling poor. Poverty versus poverty amid plenty. In many ways, an even more accurate tagline for this whole phenomenon is, it's about being made to feel poor. This point is made clearer when considering the second body of research in this area, championed by Richard Wilkinson of the University of Nottingham in England. Wilkinson took a top-down approach, looking at the "how are you doing" ladder from the societal level. Let's consider how answers to "how are you doing" can be distributed along the ladder. Suppose there is a business with 10 employees. Each earns $5.50 an hour. Thus, the company is paying out a total of $55 an hour in salary, and the average income is $5.50 per hour. With that distribution, the wealthiest employee is making $5.50 an hour, or 10% of the total income. $5.50 divided by $55. Meanwhile, in the next business, there are also 10 employees. One earns $1 an hour, the next $2 an hour, the next $3, and so on. Once again, the company pays a total of $55 an hour in salary, and the average salary is again $5.50 per hour. But now the wealthiest employee, earning $10 an hour, takes home 18% of the total income. $10 divided by $55. Now in the third company, 9 of the employees earn $1 an hour, and the 10th earns $46 an hour. Again, the company pays a total of $55 an hour, and the average salary is $5.50 an hour. And here, the wealthiest employee takes home 84% of the total income, $46 divided by $55. What we have here are businesses of increasingly unequal incomes. What Wilkinson and others have shown is that poverty is not only a predictor of poor health, but independent of absolute income, so is poverty amid plenty. The more income inequality there is in a society, the worse the health and mortality rates. This has been shown repeatedly, and at multiple levels. For example, income inequality predicts higher infant mortality rates across a bunch of European countries. Income inequality predicts mortality rates across all ages, except the elderly, in the United States, whether you consider this at the level of states or cities. In a world of science often filled with wishy-washy data, the effect is extremely reliable. Income inequality across American states is a really strong predictor of mortality rates among working men. When you compare the most egalitarian state, New Hampshire, with the least egalitarian, Louisiana, the latter has about a 60% higher mortality rate. Finally, Canada is both markedly more egalitarian and healthier than the United States, despite being a poorer country. Amid extraordinary findings like that, the relationship between income inequality and poor health doesn't seem to be universal. Note how flat the curve is for Canada. Moreover, you don't find it when considering adults throughout Western Europe, particularly in countries with well-established social welfare systems like Denmark. In other words, you probably can't pick up this effect when comparing individual parishes in Copenhagen, because the overall pattern is so egalitarian in a place like that. But it's a reasonably robust relationship in the United Kingdom, while the flagship for the health-income inequality relationship is the United States, where the top 1% of the SES ladder controls nearly 40% of the wealth. And it's a huge effect, and persists even after controlling for race. These studies of nations, states, and cities raise the issue of whom someone is comparing themselves to when they think of where they are on a how are you doing ladder. Adler tries to get at this by asking her question twice. First, you're asked to place yourself on the ladder with respect to society as a whole, and second, with respect to your immediate community. The top-down Wilkinson types get at this by comparing the predictive power of data at the national, state, and city levels. Neither literature has given a clear answer yet, but both seem to suggest that it is one's immediate community that is most important. As Tip O'Neill, the consummate politician, used to say, all politics is local. This is obviously the case in traditional settings where all people know about is the immediate community of their village. Look at how many chickens he has. I'm such a loser. But thanks to urbanization, mobility, and the media that makes for a global village, something absolutely unprecedented can now occur. We can now be made to feel poor or poorly about ourselves by people we don't even know. You can feel impoverished by the clothes of someone you pass in a midtown crowd, by the unseen driver of a new car on the freeway, by Bill Gates on the evening news, even by a fictional character in a movie. Our perceived SES may arise mostly out of our local community, but our modern world makes it possible to have our noses rubbed in it by a local community that stretches around the globe. Income equality seems really important for making sense of the SES health gradient. But maybe it isn't that important. Maybe the inequality business is just a red herring built around the fact that places with big inequalities tend to be poor places as well. In other words, back to the key thing being poverty instead of poverty amid plenty. But control for absolute income and the inequality data still stand. There's a second potential problem. Warning: ignore this paragraph if you're math-phobic. As a synopsis of the plot, the income inequality hypothesis is menaced by math villains, but is saved in a cliffhanger finish. Moving up the SES ladder is associated with better health, by whatever measure you are using, but as noted, each incremental step gets smaller. A mathematical way of stating this is that the SES health relationship forms an asymptote. Going from very poor to lower middle class involves a steep rise in health that then tends to flatten out as you go into the upper SES range. So if you examine wealthy nations, you are examining countries where SES averages out to somewhere in the flat part of the curve. Therefore, compare two equally wealthy nations, that is to say, which have the same average SES on the flat part of the curve, that differ in income inequality. By definition, the nation with the greater inequality will have more data points coming from the steeply declining part of the curve, and thus must have a lower average level of health. In this scenario, the income inequality phenomenon doesn't really reflect some feature of society as a whole, but merely emerges as a mathematical inevitability from individual data points. However, some fairly fancy mathematical modeling studies show that this artifact can't explain all of the health-income inequality relationship in the United States. But alas, there might be a third problem. Suppose in some society the poor health of the poor was more sensitive to socioeconomic factors than the good health of the rich. Now, suppose you make income distribution in that society more equitable by transferring some wealth from the wealthy to the poor. Maybe by doing that, you make the health of the wealthy a little worse and the health of the poor a lot better. A little worse in the few wealthy plus a lot better in the numerous poor, and overall you've got a healthier society. That wouldn't be very interesting in the context of stress and psychological factors. But Wilkinson makes an extraordinary point. In societies that have more income equality, both the poor and the wealthy are healthier than their counterparts in a less equal society with the same average income. There is something more profound happening here. How does income inequality and feeling poor translate into bad health? Income inequality and feeling poor could give rise to bad health through a number of routes. One, pioneered by Ichiro Kawachi of Harvard University, focuses on how income inequality makes for a psychologically crappier, more stressful life for everyone. He draws heavily upon a concept in sociology called social capital. While financial capital says something about the depth and range of financial resources you can draw on in troubled times, social capital refers to the same in the social realm. By definition, social capital occurs at the level of a community, rather than at the level of individuals or individual social networks. What makes for social capital? A community in which there is a lot of volunteerism and numerous organizations that people can join which make them feel like they're part of something bigger than themselves. Where people don't lock their doors. Where people in the community would stop kids from vandalizing a car even if they don't know whose car it is. Where kids don't try to vandalize cars. What Kawachi shows is that the more income inequality in a society, the lower the social capital, and the lower the social capital, the worse the health. Obviously, social capital can be measured in a lot of ways, and is still evolving as a hard-nosed measure. But broadly, it incorporates elements of trust, reciprocity, lack of hostility, heavy participation in organizations for a common good, ranging from achieving fun, a bowling league, to more serious things, tenant organizations or a union, and those organizations accomplishing something. Most studies get at it with two measures. How people answer a question like, do you think most people would try to take advantage of you if they got a chance, or would they try to be fair? and how many organizations people belong to. Measures like those tell you that on the levels of states, provinces, cities, and neighborhoods, low social capital tends to mean poor health, poor self-reported health, and high mortality rates. Findings such as these make perfect sense to Wilkinson. In his writing, he emphasizes that trust requires reciprocity, and reciprocity requires equality. In contrast, hierarchy is about domination, not symmetry and equality. By definition, you can't have a society with both dramatic income inequality and lots of social capital. These findings would also have made sense to the late Aaron Antonovsky, who was one of the first to study the SES health gradient. He stressed how damaging it is to health and psyche to be an invisible member of society. To recognize the extent of which the poor exist without feedback, just consider the varied ways that most of us have developed for looking through homeless people as we walk past them. So, income inequality, minimal trust, lack of social cohesion all go together. Which causes which, and which is most predictive of poor health? To figure this out, you need some fancy statistical techniques called path analysis. An example we're comfortable with by now from earlier chapters. Chronic stress makes for more heart disease. Stress can do this by directly increasing blood pressure. But stress also makes lots of people eat less healthfully. How much is the path from stress to heart disease directly via blood pressure, and how much by the indirect route of changing diet? That's the sort of thing that a path analysis can tell you. And Kawachi's work shows that the strongest route from income inequality, after controlling for absolute income, to poor health is via the social capital measures. How does lots of social capital turn into better health throughout a community? Less social isolation, more rapid diffusion of health information, potentially social constraints on publicly unhealthy behaviors, less psychological stress, better organized groups demanding better public services, and related to that, another great measure of social capital is how many people in a community bother to vote. So, it sounds like a solution to life's ills, including some stress-related ills, is to get into a community with lots of social capital. However, as will be touched on in the next chapter, this isn't always a great thing. Sometimes, communities get tremendous amounts of social capital by having all of their members goose-step to the same thoughts and beliefs and behaviors, and don't cotton much to anyone different. Research by Kawachi and others shows another feature of income inequality that translates into more physical and psychological stress. The more economically unequal a society, the more crime, assault, robbery, and particularly homicide, and the more gun ownership. Critically, income inequality is consistently a better predictor of crime than poverty per se. This has been demonstrated on the level of states, provinces, cities, neighborhoods, even individual city blocks. And just as we saw in Chapter 13, when we looked at the prevalence of displacement aggression, poverty amid plenty predicts more crime, but not against the wealthy. The have-nots turn upon the have-nots. Meanwhile, Robert Evans, University of British Columbia, John Lynch, and George Kaplan, the latter two both of the University of Michigan, offer another route linking income inequality to poor health, once again via stress. This pathway is one that, once you grasp it, is so demoralizing that you immediately want to man the barricades and sing revolutionary songs from Les Mis. It goes as follows. If you want to improve health and quality of life and decrease the stress, for the average person in a society, you do so by spending money on public goods. Better public transit, safer streets, cleaner water, better public schools, universal health care. The bigger the income inequality is in a society, the greater the financial distance between the wealthy and the average. The bigger the distance between the wealthy and the average, the less benefit the wealthy will feel from expenditures on the public good. Instead, they would derive much more benefit by spending the same taxed money on their private good, a better chauffeur, a gated community, bottled water, private schools, private health insurance. As Evans writes, the more unequal are incomes in a society, the more pronounced will be the disadvantages to its better-off members from public expenditure, and the more resources will those members have available to them to mount effective political opposition. He notes how this secession of the wealthy pushes toward private affluence and public squalor. And more public squalor means more of the daily stressors and allostatic load that drives down health for everyone. For the wealthy, this is because of the costs of walling themselves off from the rest of society. And for the rest of society, this is because they have to live in it. So this is a route by which an unequal society makes for a more stressful reality. But this route certainly makes for more psychological stress as well. If the skew in society biases the increasingly wealthy toward wanting to avoid the public expenditures that would improve everyone else's quality of life, well, that might have some bad effects on trust, hostility, crime, and so on. So we've got income inequality, low social cohesion and social capital, class tensions, and lots of crime, all forming an unhealthy cluster. Let's see a grim example of how these pieces come together. By the late 1980s, life expectancy in Eastern Bloc countries was less than in every Western European country. As analyzed by Evans, these were societies in which there was a fair equity of income distribution, but a highly unequal distribution of freedoms of movement, speech, practice of beliefs, and so on. And what has happened to Russia since the dissolution of the Soviet Union? A massive increase in income inequality and crime, a decline in absolute wealth, and an overall decline in life expectancy that is unprecedented in an industrialized society. One more grim example of how this works. America. Enormous wealth, enormous income inequality, high crime, the most heavily armed nation on earth, and markedly low levels of social capital. It is virtually the constitutional right of an American to be mobile and anonymous, show your independence, move across the country for any job opportunity. He lives across the street from his parents? Isn't that a little, stunted? Get a new accent, get a new culture, get a new name, unlist your phone number, reboot your life, all of which are the antitheses of developing social capital. This helps to explain something subtle about the health-income inequality relationship. Compare the United States and Canada. As shown, the former has more income inequality and worse health. But restrict your analysis to a subset of atypical American systems chosen to match the low inequality of Canada. And those U.S. cities still have worse health and a steeper SES health gradient. Some detailed analyses show what this is about. It's not just that America is a markedly unequal society when it comes to income. It's that even for the same degree of worsening income inequality, social capital is driven down further in the United States. Our American credo is that people are willing to tolerate a society with miserably low levels of social capital, so long as there can be massive income inequality, with the hope that they will soon be sitting at the top of this steep pyramid. Over the last quarter century, poverty and income inequality have steadily risen, and every social capital measure of trust, community participation, and voter participation has declined. And what about American health? We have disparity between the wealth of our nation and the health of our citizens that is also unprecedented, and getting worse. This is pretty depressing stuff, given its implications. Adler, writing around the time when universal health insurance first became a front-page issue, as was the question of whether Hillary's hairstyle made her a more or less effective advocate for it, concluded that such universal coverage would have a minor impact on SES-related inequalities in health. Her conclusion is anything but reactionary. Instead, it says that if you want to change the SES gradient, it's going to take something a whole lot bigger than rigging up insurance so that everyone can drop in regularly on a friendly small-town dock out of Norman Rockwell. Poverty, and the poor health of the poor, is about much more than simply not having enough money. It's about the stressors caused in a society that tolerates leaving so many of its members so far behind. This is relevant to an even larger depressing thought. I initially reviewed what social rank has to do with health in non-human primates. Do low-ranking monkeys have a disproportionate share of disease, more stress-related disease? And the answer was, well, it's actually not that simple. It depends on the sort of society the animal lives in, its personal experience of that society, its coping skills, its personality, the availability of social support. Change some of those variables and the rank health gradient can shift in the exact opposite direction. This is the sort of finding that primatologists revel in. Look how complicated and subtle my animals are. The second half of this chapter looked at humans. Do poor humans have a disproportionate share of disease? The answer was yes, yes, over and over, regardless of gender or age or race. In societies with universal health care and those without. In societies that are ethnically homogeneous and those rife with ethnic tensions. In societies in which illiteracy is widespread and those in which it has been virtually banished. In those in which infant mortality has been plummeting, and in some wealthy industrialized societies in which rates have inexcusably been climbing. And in societies in which the central mythology is a capitalist credo of living well is the best revenge, and those in which it is a socialist anthem of from each according to his ability, to each according to his needs. What does this dichotomy between our animal cousins and us signify? The primate relationship is nuanced and filled with qualifiers. The human relationship is a sledgehammer that obliterates every societal difference. Are we humans actually less complicated and sophisticated than non-human primates? Not even the most chauvinistic primatologists holding out for their beasts would vote for that conclusion. I think it suggests something else. Agriculture is a fairly recent human invention, and in many ways it was one of the great stupid moves of all time. Hunter-gatherers have thousands of wild sources of food to subsist on. Agriculture changed all that, generating an overwhelming reliance on a few dozen domesticated food sources, making you extremely vulnerable to the next famine, the next locust infestation, the next potato blight. Agriculture allowed for the stockpiling of surplus resources, and thus, inevitably, the unequal stockpiling of them. Stratification of society and the invention of classes. Thus, it allowed for the invention of poverty. I think that the punchline of the primate-human difference is that when humans invented poverty, they came up with a way of subjugating the low-ranking like nothing ever before seen in the primate world. Chapter 18. Managing Stress. By now, if you are not depressed by all the bad news in the preceding chapters, you probably haven't been paying attention. Stress can wreak havoc with your metabolism, raise your blood pressure, burst your white blood cells, make you flatulent, ruin your sex life, and if that's not enough, possibly damage your brain. Why don't we throw in the towel right now? There is hope. Although it may sneak onto the scene in a quiet, subtle way, it is there. This frequently hits me at gerontology conferences. I'm sitting there, listening to the umpteenth lecture with the same general tone. The kidney expert speaking about how that organ disintegrates with age, the immunology expert on how immunity declines, and so on. There is always a bar graph set to 100% of something or other for young subjects, with a bar showing that the elderly have only 75% of the kidney-related something or other of young subjects, 63% of the muscle-related something or other, and so on. Now, there's a critical feature to those bar graphs. Research typically involves the study of populations, rather than single individuals one at a time. All those individuals never have the exact same level of something or other. Instead, the bars in a graph represent the average for each age. See Figure 20 in your PDF companion. Suppose one group of 3 subjects has scores of 19, 20, and 21, for an average of 20. Another group may have scores of 10, 20, and 30. They would also have an average score of 20, but the variability of those scores would be much larger. By the convention of science, the bars also contain a measure of how much variability there is within each age group. The size of the T above the bar indicates what percentage of the subject in the group had scores within X distance of the average. One thing that is utterly reliable is that the amount of variability increases with age. The conditions of the elderly are always much more variable than those of the young subjects. What a drag, you say as a researcher, because with that variance your statistics are not as neat, and you have to include more subjects in your aged population to get a reliable average. But really think about that fact for a minute. Look at the size of the bars for the young and old subjects. Look at the size of the T-shaped variance symbols. Do some quick calculations, and suddenly the extraordinary realization hits you. To generate a bar with that large of a variance term amid the population of, say, 50 subjects, there have to be 6 subjects where something or other is improving with age. Their kidney filtration rates have gotten better. Their blood pressures have decreased. They do better on memory tests. Suddenly, you're not sitting there semi-bored in the conference, waiting for the break to grab some of those unhealthy cinnamon buns. You're on the edge of your seat. Who are those 6? What are they doing right? And with all that scientific detachment abandoned, how can I do that too? This pattern used to be a statistical irritant to gerontologists. Now it's the trendiest subject in the field. Successful aging. Not everyone falls apart miserably with age. Not every organ system poops out. Not everything is bad news. The same pattern occurs in many other realms in which life tests us. 10 men are released from years spent as political hostages. 9 come out troubled, estranged from friends and family, with nightmares, difficulties readapting to everyday life. Some of those 9 will never function well again. Yet invariably there is one guy who comes out saying, "Yeah, the beatings were awful. The times they put a gun to my head and cocked the trigger were the worst of my life. Of course, I would never want to do it again. But it wasn't until I was in captivity that I realized what is really important, that I decided to devote the rest of my life to X. I'm almost grateful. How did he do it? What explains the extraordinarily rare Holocaust survivor who came out nearly as mentally healthy as when she went in? Consider the physiological studies of people carrying out dangerous, stressful tasks. Parachuting, learning to land on an aircraft carrier in choppy seas, carrying out underwater demolition. The studies show the same pattern. Most people have massive stress responses, and a subset are physiologically unflustered. And then there's that hair-raising, push-the-envelope, unpredictable world of supermarket lines. You've picked the slow one, and your simmering irritation is made worse by the person behind you, who looks perfectly happy standing there, daydreaming. Despite the endless ways in which stress can disrupt, we do not all collapse into puddles of stress-related disease and psychiatric dysfunction. Of course, we are not all exposed to identical external stressors, but given the same stressors, even the same major stressors, we vary tremendously in how our bodies and psyches cope. This final chapter asks the questions born of hope. Who makes up that subset that can cope? How do they do it? And how can we? Chapter 15 suggested that some personalities and temperaments aren't well suited to dealing with stress, and it is easy to imagine the opposite case, that some are. That's true. But this chapter shows that having the right personality doesn't explain all successful coping. There's even hope for the rest of us. We begin by more systematically examining cases of individuals who just happen to be fabulous at dealing with stress. Tales from the Trenches. Some folks who are amazing at dealing with stress. Successful aging. Probably the best place to start is with successful aging, a subject that was covered at length in Chapter 12. Amid a lot of good news in that chapter, one particularly bleak set of findings had to do with glucocorticoids. Old rats, recall, secrete too much of these hormones. They have elevated levels during basal, non-stressful situations, and difficulty shutting off secretion at the end of stress. I discussed the evidence that this could arise from damage to the hippocampus, the part of the brain that, in addition to playing a role in learning and memory, helps inhibit glucocorticoid secretion. Then, to complete the distressing story, it was revealed that glucocorticoids could hasten the death of hippocampal neurons. Furthermore, the tendency of glucocorticoids to damage the hippocampus increases the oversecretion of glucocorticoids, which in turn leads to more hippocampal damage, more glucocorticoids, spiraling downward. I proposed that feed-forward cascade model around 20 years ago. It seemed to describe a basic and inevitable feature of aging in the rat, one that seemed important, at least from my provincial perspective, having just spent 80 hours a week studying it in graduate school. I was pretty proud of myself. Then an old friend, Michael Meany of McGill University, did an experiment that deflated that grandiosity. Meany and colleagues studied that cascade in old rats, but they did something clever first. Before starting the studies, they tested the memory capacity of the rats. As is usual, on the average, these old rats had memory problems compared with young controls. But as usual, a subset were doing just fine with no memory impairment whatsoever. Meany and crew split the group of old rats into the impaired and the unimpaired. The latter turned out to show no evidence at all of that degenerative feed-forward cascade. They had normal glucocorticoid levels basally and after stress. Their hippocampi had not lost neurons or lost receptors for glucocorticoids. All those awful degenerative features turned out not to be an inevitable part of the aging process. All those rats had to do was age successfully. What was this subset of rats doing right? Oddly, it might have had something to do with their childhoods. If a rat is handled during the first few weeks of its life, it secretes less glucocorticoids as an adult. This generated a syllogism. If neonatal handling decreases the amount of glucocorticoids secreted as an adult, and such secretion in an adult influences the rate of hippocampal degeneration in old age, then handling a rat in the first few weeks of its life should alter the way it ages years later. Meany's lab and I teamed up to test this, and found exactly that. Do nothing more dramatic than pick up a rat and handle it 15 minutes a day for the first few weeks of its life. Put it back in its cage with the unhandled controls. Come back 2 years later. And the handled rat is spared the entire feed-forward cascade of hippocampal damage, memory loss, and elevated glucocorticoid levels. Real rats in the real world don't get handled by graduate students. Is there a natural world equivalent of neonatal handling in the laboratory? Meany went on to show that rat mothers who spend more time licking and grooming their pups in those critical first few weeks induce the same handling phenomenon. It seems particularly pleasing that this grim cascade of stress-related degeneration in old age can be derailed by subtle mothering years earlier. No doubt there are other genetic and experiential factors that bias a rat toward successful or unsuccessful aging, a subject that Meany still pursues. Of greatest importance for our purposes now, however, is simply that this degeneration is not inevitable. If the fates of inbred laboratory rats are this variable, how humans fare is likely to be even more diverse. Which humans age successfully? To review some of the material in Chapter 12, plain old aging itself is more successful than many would guess. Levels of self-assessed contentment do not decline with age. While social networks decrease in size, they don't decline in quality. In the United States, the average 85-year-old spends little time in an institution, a year and a half for women, half a year for men. The average person in that age range, taking 3 to 8 medications a day, nevertheless typically categorizes herself as healthy. And another very good thing. Despite the inherent mathematical impossibility, the average aged person considers herself to be healthier and better off than the average aged person. Amid that good news, who are the people who age particularly successfully? As we saw in the last chapter, one factor is making sure you pick parents who are not poor. But there are other factors as well. The psychologist George Vaillant has been looking at this for years, beginning with his famous Harvard aging study. In 1941, a Harvard dean picked out a couple of hundred undergraduates, all male back then naturally, who would be studied for the rest of their lives. For starters, at age 65, these men had half the mortality rate of the rest of their Harvard peers, already a successfully aging crowd. Who were the students picked by that dean? Students whom he considered to be sound. Oh, hell, you're thinking. I'm a 50-year-old woman trying to figure out how to age successfully, and the prescription is to act in a way so that a 1940s Boston Brahmin with a pipe and tweed jacket would consider me to be a sound 20-year-old fellow? Fortunately, Vaillant's research gives us more to work with than that. Among this population, which subset has had the greatest health, contentment, and longevity in old age? A subset with an array of traits, apparent before age 50. No smoking, minimal alcohol use, lots of exercise, normal body weight, absence of depression, a warm, stable marriage, and a mature, resilient coping style, which seems built around extroversion, social connectiveness, and low neuroticism. Of course, none of this tells you where someone gets the capacity for a mature, resilient coping style, or the social means to have a stable marriage. Nor does it control for the possibility that men who, for example, have been drinking excessively have done so because they've had to deal with more than their share of miserable stressors. Despite these confounds, findings like these have emerged from other studies, and with more representative populations than Harvard graduates. Another literature shows the tremendous gerontological benefits of being respected and needed in old age. This has been shown in many settings, but is best appreciated with our society's equivalents of village elders, the dramatically successful aging of Supreme Court justices and conductors. It certainly fits with everything we learned about in Chapter 13. You're 85, and you get to influence your nation's laws for a century to come, or spend your days aerobically exercising by waving your baton about and determining whether a whole orchestra full of adults gets a potty break before or after another run through Wagner's Ring Cycle. The study of successful aging is a young field, and some mammoth longitudinal studies are underway that will produce a treasure trove of data, not only about what traits predict successful aging, but where those traits come from. In the meantime, though, the point for this chapter is to see that there are lots of folks out there who successfully navigate one of the most stressful passages of life. Coping with catastrophic illness. In the early 1960s, when scientists were just beginning to investigate whether psychological stress triggers the same hormonal changes that physical stressors do, a group of psychiatrists conducted what has become a classic study. It concerned the parents of children dying of cancer and the high glucocorticoid levels that those parents secreted. There was great variance in this measure. Some of the parents secreted immense quantities of glucocorticoids. Others were in the normal range. The investigators, in in-depth psychiatric interviews, explored which parents were holding up best to this horrible stressor, and identified a number of coping styles associated with lower glucocorticoid levels. One important variable was the ability of parents to displace a major worry onto something less threatening. A father has been standing vigil by his sick child for weeks. It's clear to everyone that he needs to get away for a few days, to gain some distance, as he is near a breaking point. Plans are made for him to leave, and just before he does, he is feeling great anxiety. Why? At one extreme is the parent who says, "I've seen how rapidly medical crises can develop at this stage. What if my daughter suddenly gets very sick and dies while I'm away? What if she dies without me?" At the other extreme is the parent who can repackage the anxiety into something more manageable. "Well, I'm just worried that she'll be lonely without me, that the nurses won't have time to read her favorite stories." The latter style was associated with lower glucocorticoid levels. A second variable had to do with denial. When a child went into remission, which frequently happened, did the parent look at him and say to the doctor, "It's over with, there's nothing to worry about, we don't even want to hear the word remission, he's going to be fine"? Or did she peer anxiously at the child, wondering if every cough, every pain, every instant of fatigue was a sign that the disease had returned? During periods of remission, parents who denied that relapse and death were likely, and instead focused on the seemingly healthy moment, had lower glucocorticoid levels. As we will see shortly, this facet of the study had a very different postscript. A final variable was whether the parent had a structure of religious rationalization to explain the illness. At one extreme was the parent who, while obviously profoundly distressed by her child's cancer, was deeply religious and perceived the cancer to be God's test of her family. She even reported something resembling an increase in her self-esteem. "God does not choose just anyone for a task like this. He chose us because he knew we were special and could handle this." At the other extreme was the parent who said, in effect, "Don't tell me that God works in mysterious ways. In fact, I don't want to hear about God." The researchers found that if you can look at your child having cancer and decide that God is choosing you for this special task, you are likely to have less of a stress response. The larger issue of religious belief in health will be considered shortly. Differences in vulnerability to learned helplessness. In Chapter 14, I described the learned helplessness model and its relevance to depression. I emphasized how generalized the model appears to be. Animals of many different species show some version of giving up on life in the face of something aversive and out of their control. Yet when you look at research papers about learned helplessness, there is the usual, bar graphs with T-shaped variance bars indicating large differences in response. For example, of the laboratory dogs put through one learned helplessness paradigm, about 1/3 wind up being resistant to the phenomenon. This is the same idea as the 1 out of 10 hostages who comes out of captivity a mentally healthier person than when he went in. Some folks and some animals are much more resistant to learned helplessness than average. Who are the lucky ones? Why are some dogs relatively resistant to learned helplessness? An important clue. Dogs born and raised in laboratories, bred only for research purposes, are more likely to succumb to learned helplessness than those who have come to the lab by way of the pound. Martin Seligman offers this explanation. If a dog has been out in the real world, experiencing life and fending for itself, as the dogs who wind up in a pound are likely to have done, it has learned about how many controllable things there are in life. When the experience with an uncontrollable stressor occurs, the dog, in effect, is more likely to conclude that this is awful, but it isn't the entire world. It resists globalizing the stressor into learned helplessness. In a similar vein, humans with more of an internalized locus of control, the perception that they are the masters of their own destiny, are more resistant in experimental models of learned helplessness. More stress management lessons from the baboons. Chapters 15 and 17 introduced social primates, and some critical variables that shaped social success for them. Dominance rank, the society in which rank occurs, the personal experience of both, and perhaps most important, the role played by personality. In their Machiavellian world, we saw there is more to social success and health for a male than just a lot of muscle or some big sharp canines. Just as important are social and political skills, the ability to build coalitions, and the ability to walk away from provocations. The personality traits associated with low glucocorticoid levels certainly made sense in the context of effective handling of psychological stressors. The abilities to differentiate threatening from neutral interactions with rivals, to exert some control over social conflicts, to differentiate good news from bad, to displace frustration, and above all else, the ability to make social connections, grooming, being groomed, playing with infants. So how do these variables play out over time as these animals age? Baboons are long-lived animals, sticking around the savannah for anywhere from 15 to 25 years, which means you don't get to follow an animal from its first awkward bloom of puberty into old age very readily. 25 years into this project, I'm just beginning to get a sense of the life histories of some of these animals and the development of their individual differences. As a first finding, males with the low glucocorticoid personalities were likely to remain in the high-ranking cohort significantly longer than rank-matched males with high glucocorticoid profiles. About 3 times longer. Among other things, that probably means that the low glucocorticoid guys are out-reproducing the other team. From the standpoint of evolution, passing on copies of your genes, all that jazz, this is a big difference. It suggests that if you were to go away for a couple of zillion millennia, allow that differential selection to play out, and then return to finish your doctoral dissertation, your average baboon would be a descendant of these low glucocorticoid guys, and the baboon social world would involve a lot of impulse control and gratification postponement, maybe even toilet training. And what about the old ages of these individual baboons that are alive today? The most dramatic difference I've uncovered concerns the variable of social affiliation. Your average male baboon has a pretty lousy old age, once he's gotten a paunch and some worn canines and dropped down to the cellar of the hierarchy. Look at the typical pattern of dominance interactions among the males. Usually, number 3 in the hierarchy is having most of his interactions with numbers 2 and 4, while number 15 is mostly concerned with 14 and 16. Except, of course, when 3 is having a bad day and needs to displace aggression on someone way down. Most interactions then usually occur between animals of adjacent ranks. However, amid that pattern, you'll note that the top-ranking half-dozen or so animals, nevertheless, are spending a lot of time subjecting poor number 17 to a lot of humiliating dominance displays, displacing him from whatever he is eating, making him get up whenever he settles into a nice shady spot, just generally giving him a hard time. What's that about? Number 17 turns out to have been very high-ranking back when the current dominant animals were terrified adolescents. They remember and can't believe they can make this decrepit ex-king grovel anytime they feel like it. So, as he ages, your average male baboon gets a lot of grief from the current generation of thugs, and this often leads to a particularly painful way of passing your golden years. The treatment gets so bad that the male picks up and transfers to a different troop. That's a stressful, hazardous journey, with an extremely high mortality rate for even a prime-aged animal, moving across novel terrain, chancing predators on your own. All that to wind up in a new troop, subject to an extreme version of that too frequently true truism about primate old age, namely, aging is a time of life spent among strangers. Clearly, for a baboon in that position, being low-ranking, aged, and ignored among strangers is better than being low-ranking, aged, and remembered by a vengeful generation. But what about males who, in their prime, had a low glucocorticoid personality, spending lots of time affiliated with females, grooming, sitting in contact, playing with kids? They just keep doing the same thing. They get hassled by the current rulers, but it doesn't seem to count as much as the social connectedness to these baboons. They don't transfer troops and continue the same pattern of grooming and socialization for the rest of their lives. That seems like a pretty good definition of successful aging for any primate. applying principles of dealing with psychological stress. Some success stories. Parents somehow shouldering the burden of their child's fatal illness. A low-ranking baboon who has a network of friends. A dog resisting learned helplessness. These are striking examples of individuals who, faced with a less-than-ideal situation, nevertheless excel at coping. That's great, but what if you don't already happen to be that sort of individual? When it comes to rats that wish to age successfully, the useful bit of advice a previous section generates is to make sure you pick the right sort of infancy. When it comes to humans who wish to cope with stress and achieve successful aging, you should be sure to pick the right parent's genes, and the right parent's socioeconomic status as well. The other cases of successfully coping with stress may not be any more encouraging to the rest of us. What if we happen not to be the sort of baboon who looks at the bright side? The person who holds on to hope when others become hopeless? The parent of the child with cancer who somehow psychologically manages the unmanageable? There are many stories of individuals who have supreme gifts of coping. For us ungifted ones, are there ways to change the world around us and to alter our perceptions of it so that psychological stress becomes at least a bit less stressful? The rest of the chapter is devoted to ways in which to change our coping styles. But a first thing to emphasize is that we can change the way we cope, both physiologically and psychologically. As the most obvious example, physical conditioning brought about by regular exercise will lower blood pressure and resting heart rate and increase lung capacity, just to mention a few of its effects. Among type A people, psychotherapy can change not only behaviors, but also cholesterol profiles, risk of heart attack, and risk of dying, independent of changes in diet or other physiological regulators of cholesterol. As another example, the pain and stressfulness of childbirth can be modulated by relaxation techniques, such as Lamaze. Sheer repetition of certain activities can change the connection between your behavior and activation of your stress response. In one classic study discussed earlier, Norwegian soldiers learning to parachute were examined over the course of months of training. At the time of their first jump, they were all terrified. They felt like vats of jello, and their bodies reflected it. Glucocorticoids and epinephrine levels were elevated, testosterone levels were suppressed, all for hours before and after the jump. As they repeated the experience, mastered it, stopped being terrified, their hormone secretion patterns changed. By the end of training, they were no longer turning on their stress response hours before and after the jump, only at the actual time. They were able to confine their stress response to an appropriate moment, when there was a physical stressor. The entire psychological component of the stress response had been habituated away. All of these examples show that the workings of the stress response can change over time. We grow, learn, adapt, get bored, develop an interest, drift apart, mature, harden, forget. We are malleable beasts. What are the buttons we can use to manipulate the system in a way that will benefit us? The issues raised in the chapter on the psychology of stress are obviously critical. Control, predictability, social support, outlets for frustration. Seligman and colleagues, for example, have reported some laboratory success in buffering people from learned helplessness when confronted with an unsolvable task. If subjects are first given empowering exercises, various tasks that they can readily master and control. But this is a fairly artificial setting. Some classic studies have manipulated similar psychological variables in the real world, even some of the grimmest parts of the real world. Here are two examples with startling results. Self-medication and chronic pain syndromes. Whenever something painful happens to me, amid all the distress, I am surprised at being reminded of how painful pain is. That thought is always followed by another. What if I hurt like this all the time? Chronic pain syndromes are extraordinarily debilitating. Diabetic neuropathies, crushed spinal nerve roots, severe burns, recovery after surgery can all be immensely painful. This poses a medical problem, insofar as it is often difficult to give enough drugs to control the pain without causing addiction or putting the person in danger of an overdose. As any nurse will attest, this also poses a management problem, as the chronic pain patient spends half the day hitting the call button, wanting to know when his next painkiller is coming, and the nurse has to spend half the day explaining that it is not yet time. A memory that will always make me shudder. At one point, my father was hospitalized for something. In the room next door was an elderly man who, seemingly around the clock, every 30 seconds, would plaintively shout in a heavy Yiddish accent, "Nurse! Nurse! It hurts! It hurts! Nurse!" The first day it was horrifying. The second day it was irritating. By the third day, it had all the impact of the rhythmic chirping of crickets. A while back, some researchers got an utterly mad idea, the thought of frothing lunatics. Why not give the painkillers to the patients and let them decide when they need medication? You can just imagine the apoplexy that mainstream medicine had over that one. Patients will overdose, become addicts. You can't let patients do that. It was tried with cancer patients and post-surgical patients, and it turned out that the patients did just fine when they self-medicated. In fact, the total amount of painkillers consumed decreased. Why should consumption go down? Because when you are lying there in bed, in pain, uncertain of the time, uncertain if the nurse has heard your call or will have time to respond, uncertain of everything, you are asking for painkillers not only to stop the pain, but also to stop the uncertainty. Reinstitute control and predictability. Give the patient the knowledge that the medication is there for the instant that the pain becomes too severe, and the pain often becomes far more manageable. Increasing control in nursing homes. I can imagine few settings that better reveal the nature of psychological stress than a nursing home. Under the best of circumstances, the elderly tend to have a less active, less assertive coping style than young people. When confronted by stressors, the latter are more likely to try to confront and solve the problem, while the former are more likely to distance themselves from the stressor or adjust their attitude toward it. The nursing home setting worsens these tendencies toward withdrawal and passivity. It's a world in which you are often isolated from the social support network of a lifetime, and in which you have little control over your daily activities, your finances, often your own body. A world of few outlets for frustration, in which you are often treated like a child, infantilized. Your easiest prediction is, life will get worse. A number of psychologists have ventured into this world to try to apply some of the ideas about control and self-efficacy outlined in Chapter 13. In one study, for example, residents of a nursing home were given more responsibility for everyday decision-making. They were made responsible for choosing their meals for the next day, signing up in advance for social activities, picking out and caring for a plant for their room, instead of having one placed there and cared for by the nurses. "Oh, here, I'll water that, dear. Why don't you just get back into bed?" People became more active, initiating more social interactions, and described themselves in questionnaires as happier. Their health improved, as rated by doctors unaware of whether they were in the increased responsibility group or the control group. Most remarkable of all, the death rate in the former group was half that of the latter. In other studies, different variables of control were manipulated. Almost unanimously, these studies show that a moderate increase in control produces all the salutary effects just described. In a few studies, physiological measures were even taken, showing changes like reductions in glucocorticoid levels or improved immune function. The forms that increased control could take were many. In one study, the baseline group was left alone, while the experimental group was organized into a residents' council that made decisions about life in the nursing home. In the latter group, health improved and individuals showed more voluntary participation in social activities. In another study, residents in a nursing home were being involuntarily moved to a different residence because of the financial collapse of the first institution. The baseline group was moved in the normal manner, while the experimental group was given extensive lectures on the new home and given control of a wide variety of issues connected with the move, the day of the move, the decor of the room they would live in, and so on. When the move occurred, there were far fewer medical complications for the latter group. The infantilizing effects of loss of control were shown explicitly in another study, in which residents were given a variety of tasks to do. When the staff present encouraged them, performance improved. When the staff present helped them, performance declined. Another example of these principles. This study concerned visits by college students to people in nursing homes. One nursing home group, the baseline group, received no student visitors. In a second group, students would arrive at unpredictable times to chat. There were various improvements in functioning and health in this group, testifying to the positive effects of increased social contact. In the third and fourth groups, control and predictability were introduced. In the third group, the residents could decide when the visit occurred, whereas in the fourth they could not control it, but at least were told when the visit would take place. Functioning and health improved even more in both of those groups, compared with the second. Control and predictability help, even in settings where you think it won't make a dent in someone's unhappiness. Stress management. Reading the label carefully. These studies generate some simple answers to coping with stress that are far from simple to implement in everyday life. They emphasize the importance of manipulating feelings of control, predictability, outlets for frustration, social connectedness, and the perception of whether things are worsening or improving. In effect, the nursing home and pain studies are encouraging dispatches from the front lines in this war on coping. Their simple, empowering, liberating message. If manipulating such psychological variables can work in these trying circumstances, it certainly should for the more trivial psychological stressors that fill our daily lives. This is the message that fills stress management seminars, therapy sessions, and the many books on the topic. Uniformly, they emphasize finding means to gain at least some degree of control in difficult situations, viewing bad situations as discrete events rather than permanent or pervasive ones, finding appropriate outlets for frustration, and means of social support and solace in difficult times. That's great, but it is vital to realize that the story is not that simple. It is critical that one not walk away with the conclusion that in order to manage and minimize psychological stressors, the solution is always to have more of a sense of control, more predictability, more outlets, more social affiliation. These principles of stress management work only in certain circumstances, and only for certain types of people with certain types of problems. I was reminded of this a while back. Thanks to this book's having transformed me from being a supposed expert about rats' neurons to being a supposed one about human stress, I was talking to a magazine writer about the subject. She wrote for a women's magazine, the type with articles about how to maintain that full, satisfying sex life while being the CEO of a Fortune 500 company. We were talking about stress and stress management, and I was giving an outline of some of the ideas in the chapter on psychological stress. All was going well, and toward the end the writer asked me a personal question to include in the article. What are my outlets for dealing with stress? I made the mistake of answering honestly. I love my work. I try to exercise daily, and I have a fabulous marriage. Suddenly, this hard-nosed New York writer blew up at me. I can't write about your wonderful marriage. Don't tell me about your wonderful marriage. Do you know who my readers are? They're 45-year-old professionals who are unlikely to ever get married and want to be told how great that is. It struck me that she was, perhaps, in this category as well. It also struck me, as I slunk back to my rats and test tubes afterward, what an idiot I had been. You don't counsel war refugees to watch out about too much cholesterol or saturated fats in their diet. You don't tell an overwhelmed single mother living in some inner-city hellhole about the stress-reducing effects of a daily hobby. And you sure don't tell the readership of a magazine like this how swell it is to have a soulmate for life. More control, more predictability, more outlets, more social support is not some sort of mantra to be handed out indiscriminately, along with a smile button. This lesson is taught with enormous power by two studies that we have already heard about, which seem superficially to be success stories in stress management, but turned out not to be. Back to the parents of children with cancer who were in remission. Eventually, all the children came out of remission and died. When that occurred, how did the parents fare? There were those who all along had accepted the possibility, even probability, of a relapse, and there were those who staunchly denied the possibility. As noted, during the period of remission, the latter parents tended to be the low glucocorticoid secretors. But when their illusions were shattered and the disease returned, they had the largest increases in glucocorticoid concentrations. An equally poignant version of this unfortunate ending comes from a nursing home study. Recall the one in which residents were visited once a week by students, either unannounced, at an appointed time predetermined by the student, or at a time of the resident's choice. As noted, the sociality did everyone some good, but the people in the last two groups, with the increased predictability and control, did even better. Wonderful. End of study. Celebration. Everyone delighted with the clear-cut and positive results, papers to be published, lectures to be given. Student participants visit the people in the nursing home for a last time, offer an awkward, "You know that the study is over now. I won't be coming back again, but, it's been great getting to know you." What happens then? Do the people whose functioning, happiness, and health improved now decline back to pre-experiment levels? No. They drop even further, winding up worse than before the study. This makes perfect sense. Think of how it is to get 25 shocks an hour when yesterday you got 10. Think of what it feels like to have your child come out of remission after you spent the last year denying the possibility that it could ever happen. And think about those nursing home residents. It is one thing to be in a nursing home, lonely, isolated, visited once a month by your bored children. It is even worse to be in that situation, and having had a chance to spend time with bright, eager young people who seemed interested in you, to find out now they aren't coming anymore. All but the most heroically strong among us would slip another step lower in the face of this loss. It is true that hope, no matter how irrational, can sustain us in the darkest of times, but nothing can break us more effectively than hope given and then taken away capriciously. Manipulating these psychological variables is a powerful but double-edged sword. When do these principles of injecting a sense of control, of predictability, of outlets, of sociality work, and when are they disastrous to apply? There are some rules. Let's look at some specific stress management approaches and when they work, keeping those rules in mind. Exercise. I start with exercise because this is the stress reduction approach I rely on frequently, and I'm deeply hoping that putting it first will mean that I'll live to be very old and healthy. Exercise is great to counter stress for a number of reasons. First, it decreases your risk of various metabolic and cardiovascular diseases, and therefore decreases the opportunity for stress to worsen those diseases. Next, exercise generally makes you feel good. There's a confound in this, in that most people who do a lot of exercise, particularly in the form of competitive athletics, have unneurotic, extroverted, optimistic personalities to begin with. Marathon runners are exceptions to this. However, do a properly controlled study, even with neurotic introverts, and exercise improves mood. This probably has something to do with exercise causing the secretion of beta-endorphin. In addition, there's the sense of self-efficacy and achievement, that good stuff you try to recall when your thigh muscles are killing you in the middle of the aerobics class. And most of all, the stress response is about preparing your body for a sudden explosion of muscular activity. You reduce tension if you actually turn on the stress response for that purpose, instead of merely stewing in the middle of some time-wasting meeting. Finally, There's some evidence that exercise makes for a smaller stress response to various psychological stressors. That's great. Now for some qualifiers. Exercise enhances mood and blunts the stress response only for a few hours to a day after the exercise session. Exercise is stress-reducing so long as it is something you actually want to do. Let rats voluntarily run in a running wheel and their health improves in all sorts of ways. Force them to, even while playing great dance music, and their health worsens. The studies are quite clear that aerobic exercise is better than anaerobic exercise for health. Aerobic exercise is the sustained type that, while you're doing it, doesn't leave you so out of breath that you can't talk. Exercise needs to occur on a regular basis and for a sustained period. While whole careers are consumed figuring out exactly what schedule of aerobic exercise works best, how often, for how long, it's pretty clear that you need to exercise a minimum of 20 or 30 minutes at a time, a few times a week, to really get the health benefits. Don't overdo it. Remember the lessons of Chapter 7. Too much can be at least as bad as too little. Meditation. When done on a regular, sustained basis, that is to say, something close to daily for 15-30 minutes at a time, meditation seems to be pretty good for your health, decreasing glucocorticoid levels, sympathetic tone, and all the bad stuff that too much of either can cause. Now the caveats. First, the studies are clear in showing physiological benefits while someone is meditating. It's less clear that those good effects, for example lowering blood pressure, persist for long afterward. Next, when the good effects of meditation do persist, there may be a subject bias going. Suppose you want to study the effects of meditation on blood pressure. What do? You randomly assign some people to the control group, making sure they never meditate, and some to the group that now meditate an hour a day. But in most studies, there isn't random assignment. In other words, you study blood pressure in people who have already chosen to be regular meditators, and compare them to non-meditators. It's not random who chooses to meditate. Maybe the physiological traits were there before they started meditating. Maybe those traits even had something to do with their choosing to meditate. Some good studies have avoided this confound, but most have not. Finally, there are lots of different types of meditation. Don't trust anyone who says that their special brand has been proven scientifically to be better for your health than the other flavors. Watch your wallet. Get more control, more predictability in your life. Maybe. More predictive information about impending stressors can be very stress-reducing, but not always. As noted in Chapter 13, it does little good to get predictive information about common events, because these are basically inevitable, or ones we know to be rare, because you weren't anxious about them in the first place. It does little good to get predictive information a few seconds before something bad happens, because there isn't time to derive the psychological advantages of being able to relax a bit, or way in advance of the event, because who's worrying anyway? In some situations, predictive information can even make things worse. For example, when the information tells you little. This turfs us back to our post-9/11 world of go about your normal business but be extra careful. Orange alerts. An overabundance of information can be stressful as well. One of the places I dreaded most in graduate school was the new journal desk in the library, where all the science journals received the previous week were displayed, thousands of pages of them. Everyone would circle around it, teetering on the edge of panic attacks. All that available information seemed to taunt us with how out of control we felt. Stupid, left behind, out of touch, and overwhelmed. Manipulating a sense of control is playing with the variable in psychological stress that is most likely to be double-edged. Too much of a sense of control can be crippling, whether the sense is accurate or not. An example. When he was a medical student, a friend embarked on his surgery rotation. That first day, nervous, with no idea what to expect, he went to his assigned operating room, and stood at the back of a crowd of doctors and nurses doing a kidney transplant. Hours into it, the chief surgeon suddenly turned to him. "Ah, you're the new medical student. Good. Come here. Grab this retractor. Hold it right here. Steady. Good boy." Surgery continued. My friend was ignored as he precariously maintained the uncomfortable position the surgeon had put him in, leaning forward at an angle, one arm thrust amid the crowd, holding the instrument, unable to see what was going on. Hours passed. He grew woozy, faint from the tension of holding still. He found himself teetering, eyes beginning to close, when the surgeon loomed before him. "Don't move a muscle, because you're going to screw up everything." Galvanized, panicked, half ill, he barely held on, only to discover that the "you're going to screw up everything" scenario was a stupid hazing trick done to every new med student. He had been holding an instrument over some irrelevant part of the body the entire time, fooled into feeling utterly responsible for the survival of the patient. P.S. He chose another medical specialty. As another example, recall the discussion in Chapter 8 on how tenuous a link there is between stress and cancer. It is clearly a travesty to lead cancer patients or their families to believe, misinterpreting the power of the few positive studies in this field, that there is more possibility for control over the causes and courses of cancers than actually exists. Doing so is simply teaching the victims of cancer and their families that the disease is their own fault, which is neither true nor conducive to reducing stress in an already stressful situation. So, control is not always a good thing psychologically, and a principle of good stress management cannot be simply to increase the perceived amount of control in one's life. It depends on what that perception implies, as we saw in Chapter 13. Is it stress-reducing to feel a sense of control when something bad happens? If you think, "Whew, that was bad, but imagine how much worse it would have been if I hadn't been in charge," a sense of control is clearly working to buffer you from feeling more stressed. However, if you think, "What a disaster, and it's all my fault, I should have prevented it," a sense of control is working to your detriment. This dichotomy can be roughly translated into the following rule for when something stressful occurs. The more disastrous a stressor is, the worse it is to believe you had some control over the outcome, because you are inevitably led to think about how much better things would have turned out if only you had done something more. A sense of control works best for milder stressors. Remember, this advice concerns the sense of control you perceive yourself as having, as opposed to how much control you actually have. Having an illusory sense of control in a bad setting can be so pathogenic that one version of it gets a special name in the health psychology literature. It could have been included in Chapter 15, but I saved it until now. As described by Sherman James of Duke University, it is called John Henryism. The name refers to the American folk hero who, hammering a 6-foot-long steel drill, tried to outrace a steam drill tunneling through a mountain. John Henry beat the machine, only to fall dead from the superhuman effort. As James defines it, John Henryism involves the belief that any and all demands can be vanquished, so long as you work hard enough. On questionnaires, John Henry individuals strongly agree with statements such as, "When things don't go the way I want them, it just makes me work even harder," or, "Once I make up my mind to do something, I stay with it until the job is completely done." This is the epitome of individuals with an internal locus of control. They believe that, with enough effort and determination, they can regulate all outcomes. What's so wrong with that? Nothing, if you have the good fortune to live in the privileged meritocratic world, in which one's efforts truly do have something to do with the rewards one gets, and in a comfortable middle-class world, an internal locus of control does wonders. For example, always attributing events in life to your own efforts, an internal locus of control, is highly predictive of lifelong health among that population of individuals who are the epitome of the privileged stratum of society, Vaillant's cohort of Harvard graduates. However, in a world of people born into poverty, of limited educational or occupational opportunities, of prejudice and racism, it can be a disaster to be a John Henry. To decide that those insurmountable odds could have been surmounted if only you worked even harder. John Henryism is associated with a marked risk of hypertension and cardiovascular disease. Strikingly, James's pioneering work has shown that the dangers of John Henryism occur predominantly among the very people who most resemble the mythic John Henry himself, working-class African Americans, a personality type that leads you to believe you can control the aversely uncontrollable. There's an old parable about the difference between heaven and hell. Heaven, we are told, consists of spending all of eternity in the study of the holy books. In contrast, hell consists of spending all of eternity in the study of the holy books. To a certain extent, our perceptions and interpretations of events can determine whether the same external circumstances constitute heaven or hell, and the second half of this book has explored the means to convert the latter to the former. But the key is, to a certain extent. The realm of stress management is mostly about techniques to help deal with challenges that are less than disastrous. It is pretty effective in that sphere. But it just won't work to generate a cult of subjectivity in which these techniques are blithely offered as a solution to the hell of a homeless street person, a refugee, someone prejudged to be one of society's untouchables, or a terminal cancer patient. Occasionally there is the person in a situation like that, with coping powers to make one gasp and wonder, who does indeed benefit from these techniques. Celebrate them. But that's never grounds for turning to the person next to them in the same boat and offering that as a feel-good incentive just to get with the program. Bad science, bad clinical practice, and ultimately, bad ethics. If any hell really could be converted into a heaven, then you could make the world a better place merely by rousing yourself from your lounge chair to inform a victim of some horror whose fault it is if they are unhappy. Social support. This far into this book, this one should be a no-brainer. Social support makes stressors less successful, so go get some. Unfortunately, it's not so simple. To begin with, social affiliation is not always the solution to stressful psychological turmoil. We can easily think of people who would be the last ones on earth we would want to be stuck with when we are troubled. We can easily think of troubled circumstances where being with anyone would make us feel worse. Physiological studies have demonstrated this as well. Take a rodent or a primate that has been housed alone and put it into a social group. The typical result is a massive stress response. In the case of monkeys, this can go on for weeks or months, while they tensely go about figuring out who dominates whom in the group's social hierarchy. In another demonstration of this principle, infant monkeys were separated from their mothers. Predictably, they had pretty sizable stress responses, with elevations in glucocorticoid levels. The elevation could be prevented if the infant was placed in a group of monkeys, but only if the infant already knew those animals. There is little to be derived in the way of comfort from strangers. Even once animals are no longer strangers, on average half of those in any group will be socially dominant to any given individual, and having more dominant animals around is not necessarily a comfort during trouble. Even intimate social affiliation is not always helpful. We saw in Psychoimmunity, Chapter 8, that being married is associated with all sorts of better health outcomes. Some of it is due to the old reverse causality trick. Unhealthy people are less likely to get married. Some is due to the fact that marriage often increases the material well-being of people and gives you someone to remind and cajole you into cutting back on some lifestyle risk factors. After controlling for those factors, marriage, on average, is associated with improved health. But that chapter also noted an obvious but important exception to this general rule. For women, being in a bad marriage is associated with immune suppression. So a close, intimate relationship with the wrong person can be anything but stress-reducing. Expanding outward, it is also helpful to have a strong network of friends, and, as we saw in the last chapter, to be in a community teeming with social capital. What's the potential downside of that? Something I alluded to. Amid all that nice utopian social capital business lurks the inconvenient fact that a tightly cohesive cooperative community with shared values may be all about homogeneity, conformity, and xenophobia. Maybe even brown shirts and jackboots. So social capital isn't always warm and fuzzy. Throughout this section, I have been emphasizing getting social support from the right person, the right network of friends, the right community. Often, one of the strongest stress-reducing qualities of social support is the act of giving social support, to be needed. The 12th century philosopher Maimonides constructed a hierarchy of the best ways to do charitable acts, and at the top was when the charitable person gives anonymously to an anonymous recipient. That's a great abstract goal, but often there is a staggering power in seeing the face that you have helped. In a world of stressful lack of control, an amazing source of control we all have is the ability to make the world a better place, one act at a time. Religion and spirituality. The idea that religiosity or spirituality protects against disease, particularly against stress-related disease, is immensely controversial. I've encountered some of the key researchers in this field and have noticed that their read of the literature often coincides with their personal religious views. For that reason, I think it would be helpful to put my cards on the table before tackling this subject. I had a highly orthodox religious upbringing and believed devoutly, except that now I am an atheist, have no room in my life for spirituality of any kind, and believe that religion is phenomenally damaging. Except that I wish I could be religious. Except that it makes no sense to me, and I'm baffled by people who believe. Except that I'm also moved by them. So I'm confused. On to the science. A huge literature shows that religious belief, religious practice, spirituality, and being prayed for can maintain good health. That is to say, decreases the incidence of disease, decreases the mortality rates caused by disease, put those two effects together and you have extended lifespan, and accelerates recovery from disease. So what's the controversy? First, some definitional issues. What's religiosity versus spirituality? The former is about an institutionalized system with a historical precedent and a lot of adherents. The latter is more personal. As pointed out by Ken Pargament of Bowling Green University, the former has also come to mean formal, outward-oriented, doctrinal, authoritarian, and inhibiting of expression, while the latter often implies subjective, emotional, inward-oriented, and freely expressive. When comparing religious people with people who define themselves as spiritual but without a religious affiliation, the former tend to be older, less educated, and lower in socioeconomic status, with a higher percentage of men. So religiosity and spirituality can be very different things. But despite that, the health literature says roughly similar things about both, so I'm going to use them interchangeably here. What's the controversy? Amid all those studies showing health benefits, it's whether there really are any benefits. Why so much uncertainty? For starters, because many of the studies are loony, or involve mistakes that should have been sorted out in the middle school science fair. But even among the serious studies, it is very hard to carry out research in this area with approaches that would count as the gold standard in the science business. For starters, most studies are retrospective. Moreover, people are usually assessing their own level of religiosity, including objective measures like how often they attend religious services, and folks are notoriously inaccurate at this sort of recall. Another problem is one that should easily be avoided, but rarely is. This is a subtle issue of statistics, and goes something like this. Measure a zillion things related to religiosity, most of them overlapping, and measure a zillion things related to health, ditto. Then see if anything in the first category predicts anything in the second. Even if there is no relationship at all between religiosity and health, With enough correlations, something pops up as significant by sheer chance, and voila, stop the presses. You've just proved that religion makes you healthy. Finally, and most important in this area of science, you can't randomly assign people to different study groups. You folks become atheists, and you guys start deeply believing in God, and we'll meet back here in 10 years to check everyone's blood pressure. So, religiosity is a tough subject to do real science on, something the best people readily point out. Consider two leading thinkers in this field, Richard Sloan of Columbia University and Carl Thorson of Stanford University. I'll be citing them a lot because each is an enormously rigorous scientist, and one is a strong advocate of the health benefits of religiosity, while the other is as strong a critic. Read their reviews of the subject, and both devote half the space to savaging the, heck out of the literature, pointing out that the vast majority of studies in the field are plain awful and should be ignored. Once you've separated the wheat from the voluminous chaff, what's there? Interestingly, Sloan and Thorson agree on the next point. That is, when you consider objective medical measures, like numbers of days hospitalization for an illness, there's not a shred of evidence that praying for someone improves her health, independent of her knowing that she has the social support of someone rooting for her to the higher powers. This was something already concluded by the 19th century scientist Francis Galton, who pointed out that despite having their health prayed for by overflowing churchfuls of loyal peasants each Sunday, European royals lived no longer than anyone else. Another thing that folks like Sloan and Thorson agree upon is that when you do see a legitimate link between religiosity and good health, you don't know which came first. Being religious may make you healthy, and being healthy may make you religious. They also agree that when you do see a link, even one in which religiosity gives rise to good health, you still don't know if it has anything to do with the religiosity. This is because being religious typically gets you a religious community, and thus social support, meaningful social roles, good role models, social capital, all that good stuff. And because in a large percentage of religions, religiosity usually means fewer of those drinking and smoking and carousing risk factors. So those need to be controlled for. And once you've done that, remarkably, Thorson and Sloan are still mostly in agreement, which is that religiosity does predict good health to some extent in a few areas of medicine. Thorson has done the most detailed analysis of this in some hard-nosed reviews of the field. He finds that regular attendance at religious services is reasonably predictive of a decreased mortality rate and of a decreased risk of cardiovascular disease and depression. However, he also finds that religiosity doesn't predict much of anything about cancer progression, cancer mortality rates, medical disability, and speed of recovery from an illness. Moreover, deeply religious people, by their own assessment, derive no more of what health benefits there are than the less deeply religious. His conclusion is that there's suggestive but not definitive evidence that religiosity in and of itself improves health, but the effects are pretty limited, and they're more about healthy people staying healthy than sick people staying alive and recovering faster. Here is where Sloan becomes a strong critic. He reaches pretty much the same conclusion, but is most impressed by how small these effects are, and feels that the whole subject doesn't remotely deserve the attention it has gotten. In contrast, advocates respond by saying, these aren't much smaller effects than in other, more mainstream areas of medicine, and they're big factors in some subsets of people. And thus everyone argues back and forth until the conference session is over with, and it's time for all the scientists to go to lunch. To the extent that religiosity is good for health, once you control for social support and decreased risk factors, why is it healthful? For lots of reasons that have everything to do with stress, and with the type of deities you believe in. To start, you can have a deity whose rules are mysterious. This is the original Judeo-Christian Yahweh, a point emphasized by Thomas Cahill in his book The Gift of the Jews. Prior to the monotheistic Yahweh, the gods made sense, in that they had familiar, if suprahuman, appetites. They didn't just want a lamb shank. They wanted the best lamb shank, wanted to seduce all the wood nymphs, and so on. But the early Jews invented a God with none of those desires, who was so utterly unfathomable, unknowable, as to be pants-wettingly terrifying. So even if his actions are mysterious, when he intervenes you at least get the stress-reducing advantages of attribution. It may not be clear what the deity is up to, but you at least know who is responsible for the locust swarm or the winning lottery ticket. There is purpose lurking, as an antidote to the existential void. Next, if it is an intervening deity with discernible rules, the deity provides the comfort of both attribution and predictive information. Carry out ritual X or Y is going to happen. And thus, when things go wrong, there is an explanation. If it happens that things have really gone wrong just to you, there is the opportunity to reframe the event, in the extraordinary way achieved by some of the parents of children with cancer. God has entrusted you with a burden that he can't entrust to just anyone. If it is a deity who does all these things and will respond to your personal and specific entreaties, especially if the deity preferentially responds to people who look, talk, eat, dress, pray like you, there is an added layer of control introduced. And if on top of all that, the deity is viewed as benign, the stress-reducing advantages must be extraordinary. If you can view cancer and Alzheimer's disease, the Holocaust and ethnic cleansing, if you can view the inevitable cessation of the beating of the hearts of all your loved ones, all in the context of a loving plan, that must constitute the greatest source of support imaginable. 2 additional areas of agreement. Both Sloan and Thoresen are made very nervous by the idea that findings in this field will lead to physicians advising their patients to become religious. Both note that amid this very measured good news, religiosity can make health, mental or otherwise, a lot worse. As noted by Sharon Packer of the New School for Social Research, religion can be very good at reducing stressors, but is often the inventor of those stressors in the first place. Picking the right strategy at the right time. Cognitive flexibility. In the face of some stressor, coping can take a variety of forms. You can problem solve, tackling the cognitive task of figuring out if it makes more sense to try to alter the stressor or alter your perception of it. Or you can focus on emotions. It can be stress-reducing to merely admit that you're hurting emotionally from this stressor. You can focus on relationships and social support as a means of feeling less stressed. People obviously vary as to which style they gravitate toward. For example, an endless source of tension in heterosexual relationships is that women, on average, tend toward emotion or relationship-based coping styles, whereas men tend toward problem-solving approaches. But regardless of which is your most natural coping style, a key point is that different styles tend to work better in different circumstances. As an idiotic example, suppose there's a big exam looming. One version of coping with it is to study. Another is to reframe the meaning of a bad grade. There's more to life than this class. I'm still a good person who is good at other things. Obviously, before the exam, the stress reduction by studying strategy should dominate, while you should hold off on the stress reduction by reframing approach until after the exam. As a more meaningful example, consider a major illness in the family, complete with a bunch of brutally difficult decisions looming, versus a death in the family. Typically, problem-solving approaches work better in the illness scenario. Emotion and relationship-based coping works better in the case of a death. Another version of this need for switching strategies crops up in the work of Martin Seligman. Amid all the good press that an inner locus of control gets, we just saw from the John Henryism example how counterproductive it can be. Seligman's work has demonstrated how useful and healthy it is to be able to switch loci of control. When something good happens, you want to believe that this outcome arose from your efforts and has broad, long-lasting implications for you. When the outcome is bad, you want to believe that it was due to something out of your control and is just a transient event with very local, limited implications. Implicit in switching to the optimal strategy for the particular circumstance is having the cognitive flexibility to switch strategies, period. This was something emphasized by Antonovsky, one of the pioneers of SES and health research. For him, what was the predictor of health in a person? Coping responses built around fixed rules and flexible strategies. This requires that we fight a reflex common to most of us. If something bad is happening, and our attempts to cope are not working, one of our most common responses is to, well, go back in there and just try twice as hard to cope in the usual way. Although that sometimes does the trick, that's rare. During times of stress, finding the resources to try something new is really hard, and is often just what's needed. What was he going on about with that? Here's an additional idea that doesn't even feel half-baked yet. One of the themes of this book is the goal of contrasts. Physical stressor, you want to activate a stress response. Psychological stressor, you don't. Basal conditions, as little glucocorticoid secretion as possible. Real stressor, as much as possible. Onset of stress, rapid activation. End of stress, rapid recovery. Consider a schematic version of this, based on those Norwegian soldiers learning to parachute. The first time they jumped, their blood pressure was through the roof at the time of the jump. Part B. But in addition, it was up for hours before with anticipatory terror. Part A. And for hours after, still weak-kneed. Part C. By the zillionth time they jumped, what was the profile like? The same massive stress response during the jump, Part B, but 2 seconds before and after, nothing. The parachuters are just thinking about what they're going to have for lunch. This is what conditioning is about. Sharpening the contrasts between on and off, between foreground and background, increasing the signal-to-noise ratio. Framed in the context of this book, when someone has gotten a zillion jumps worth of experience, they turn on the stress response only during the actual stressor. As discussed earlier, what have been winnowed away by that experience are parts A and C, the psychological stress response. This is great, but what I'm grasping at is an idea about a subtler goal. This thinking owes a lot to conversations with Manula Waldron of Ohio State University, an engineering professor who also happens to be a hospital chaplain. This feels embarrassingly Zenish for me to spout, being a short, hypomanic guy with a Brooklyn accent. But here goes. Maybe the goal isn't to maximize the contrast between a low baseline and a high level of activation. Maybe the idea is to have both simultaneously. Huh? Maybe the goal would be for your baseline to be something more than the mere absence of activation, a mere default, but to instead be an energized calm, a proactive choice, and for the ceiling to consist of some sort of equilibrium and equanimity threading throughout the crazed arousal. I have felt this a few times playing soccer, inept as I am at it, where there's a moment when, successful outcome or not, every physiological system is going like mad, and my body does something that my mind didn't even dream of, and the 2 seconds when that happens seem to take a lot longer than it should have. But this business about the calm amid the arousal isn't just another way of talking about good stress, a stimulating challenge as opposed to a threat. Even when the stressor is bad and your heart is racing in crisis, the goal should be to somehow make the fraction of a second between each heartbeat into an instant that expands in time and allows you to regroup. There. I have no idea what I'm talking about, but I think there might be something important lurking there. Enough said. Just do it. The 80-20 quality of stress management. There's this idea in a number of disciplines called the 80-20 rule. In retail business, it takes the form of 20% of the customers account for 80% of the complaints. In criminology, it's 20% of the criminals account for 80% of the crime. or 20% of the research and design team accounts for 80% of the new ideas. The numbers are not meant to be literal. It's just a way of stating that causality is not equally distributed in a population of causal agents. I would apply the 80-20 rule to stress management. 80% of the stress reduction is accomplished with the first 20% of effort. What do I mean by this? Suppose you're a type A nightmare, this hostile, curt, tightly wound misery to those around you. No number of times that friends and loved ones sit you down, warmly look you in the eyes, and then yell at you about your being a pain in the ass will cause anything to change. No number of doctor visits with elevated blood pressure readings are going to make a difference. It's not going to happen until you've decided to change, and really decided, not just decided to try to make everyone else stop hassling you over some non-existent problem. This is an essential truth for mental health professionals. The whole family that's in therapy is desperately trying to get the one individual to make some changes, and nothing is going to happen if all he's doing is staring sullenly at the Siggy Freud action figure on the shrink's bookshelf. But once you sincerely want to change, the mere act of making an effort can do wonders. For example, clinically depressed people feel significantly better simply by scheduling a first appointment to see a therapist. It means they've recognized there's a problem. It means they've fought their way up through the psychomotor quagmire to actually do something. It means they've turned a corner. This has obvious relevance for stress management. This section has examined characteristics of the most effective forms of stress management. But don't get crazed, holding off on doing something until you figure out the perfect approach for you. On a certain level, it doesn't matter what management technique you use, beyond it not being abusive to those around you. If your special stress reduction trick is to stand on a busy street corner in a toga reciting Teletubbies monologues, you're going to benefit from that, simply because you've decided that making a change is enough of a priority that you're willing to say no to all the things that can't be said no to in order to do that tinky-winky soliloquy. Don't save your stress management for the weekend or for when you're on hold on the phone for 30 seconds. Take the time out to do it almost daily. And if you manage that, change has become important enough to you that you're already a lot of the way there. Maybe not really 80%, but at least a great start. A summing up. So, what have we learned? In the face of terrible news beyond control, beyond prevention, beyond healing, those who are able to find the means to deny tend to cope best. Such denial is not only permitted, it may be the only means of sanity. Truth and mental health often go hand in hand, but not necessarily in situations like these. In the face of lesser problems, one should hope, but protectively and rationally. Find ways to view even the most stressful of situations as holding the promise of improvement, but do not deny the possibility that things will not improve. Balance these two opposing trends carefully. Hope for the best and let that dominate most of your emotions, but at the same time let one small piece of you prepare for the worst. Those who cope with stress successfully tend to seek control in the face of present stressors, but do not try to control things that have already come to pass. They do not try to control future events that are uncontrollable, and do not try to fix things that are not broken or that are broken beyond repair. When faced with the large wall of a stressor, it is great if there emerges one singular solution that makes the wall crumble. But often, a solution instead will be a series of footholds of control, each one small but still capable of giving support, that will allow you to scale the wall. It is generally helpful to seek predictable, accurate information. However, such information is not useful if it comes too soon or too late, if it is unnecessary, if there is so much information that it is stressful in and of itself, or if the information is about news far worse than one wants to know. Find that outlet for your frustrations and do it regularly. Make the outlet benign to those around you. One should not give ulcers in order to avoid getting them. Read the fine print and the ingredient list on each new form of supposed anti-stress salvation. Be skeptical of hype. Figure out what works for you. It is important to find sources of social affiliation and support. Even in our obsessively individualistic society, most of us yearn to feel part of something larger than ourselves. But one should not mistake true affiliation and support for mere socializing. A person can feel vastly lonely in a vast crowd, or when faced with a supposed intimate who has proved to be a stranger. Be patient. Most of us spend a lifetime learning how to be truly good friends and spouses. Some of these ideas are encompassed in Reinhold Niebuhr's famous prayer, adopted by Alcoholics Anonymous. God grant me the serenity to accept the things I cannot change, courage to change the things I can, and wisdom to know the difference. Have the wisdom to pick your battles, and once you have, the flexibility and resiliency of strategies to use in those battles is summarized in something I once heard in a Quaker meeting. In the face of strong winds, let me be a blade of grass. In the face of strong walls, let me be a gale of wind. Sometimes, coping with stress consists of blowing down walls, but sometimes it consists of being a blade of grass, buffeted and bent by the wind, but still standing when the wind is long gone. Stress is not everywhere. Every twinge of dysfunction in our bodies is not a manifestation of stress-related disease. It is true that the real world is full of bad things that we can finesse away by altering our outlook and psychological makeup, but it is also full of awful things that cannot be eliminated by a change in attitude, no matter how heroically, fervently, complexly, or ritualistically we may wish. Once we are actually sick with the illness, the fantasy of which keeps us anxiously awake at 2 a.m, the things that will save us have little to do with the content of this book. Once we have that cardiac arrest, once a tumor has metastasized, once our brain has been badly deprived of oxygen, little about our psychological outlook is likely to help. We have entered the realm where someone else, a highly trained physician, must use the most high-tech of appropriate medical interventions. These caveats must be emphasized repeatedly in teaching what cures to seek and what attributions to make when confronted with many diseases. But amid this caution, there remains a whole realm of health and disease that is sensitive to the quality of our minds, our thoughts and emotions and behaviors. And sometimes